You have entered the realm of one of the most fascinating hypotheses in contemporary physics, the possibility that our cosmos is a hologram. This theory proposes that the whole universe may be defined by two-dimensional information recorded on its border, which sounds weird but is really a legitimate scientific proposal. Picture the cosmos as an expansive three-dimensional arena. If you believe the holographic principle, all the data in this space, just like the data on your computer's hard drive, can be projected from the flat surface that encapsulates the cosmos. The idea of a holographic cosmos was first proposed in the field of black hole physics, when shocking findings indicated that, instead of being lost forever within a black hole, the information that is absorbed is actually distributed out in 2 dimensions on its event horizon. Thanks to this, scientists discovered a fantastical possibility. Could this idea, which is valid for black holes, also be valid for the whole universe? Do you think the world we see in 3 dimensions is really an illusion that arises from a more basic 2-dimensional reality? This may be better understood if you picture a holographic picture on a credit card. In reality, the picture is encoded on a flat 2-dimensional surface, yet it seems 3-dimensional. Similarly, the 2-dimensional cosmic horizon may be the source from which our 3-dimensional reality is projected. By bringing together general relativity and quantum mechanics, 2 of the most powerful theories in physics, this theory achieves a mathematical beauty that is really remarkable. Both of these pillars of contemporary science have always disagreed with one another, providing valid descriptions of the cosmos under various conditions but never coming together to form a single framework. In a holographic universe, quantum bits might paint space and time, with matter, energy, and gravity all being representations of the underlying bits of information etched into the fabric of the cosmos. According to physicists, this extreme perspective may provide light on the universe's most baffling mysteries, such as the dark energy that is accelerating its expansion. In addition, the holographic universe model sheds light on the very essence of reality, revealing the intricate structure of space and time, which might ultimately lead to a fuller comprehension of the universe's beginnings and destiny. It tests our senses and expands our notion of reality. Just as a hologram's constituent parts store the picture of the whole, so too does every corner of the cosmos, according to the holographic principle. This concept also has connections to metaphysics and philosophy, 2 fields that have argued over fundamental concerns about consciousness and the nature of reality for ages. Could the 2-dimensional information contained at the space border be the basis for our perception of a 3-dimensional reality, which is only an illusion that our brains create? Scientists are now conducting quantum gravity experiments and studying the cosmic microwave background, the universe-filling afterglow of the Big Bang, to push the holographic principle to its boundaries. The ramifications for computing and technology are enormous. Theoretical breakthroughs from holographic theory have the potential to radically alter future information storage and processing methods, similar to how a comprehension of quantum mechanical rules paved the path for the creation of the transistor and laser. Envision computers that run on concepts drawn from a 2-dimensional quantum field theory, rather than the 3-dimensional transistors used today. A new era of computing possibilities might dawn as a result of this, ushering in massive improvements in processing power and efficiency. Questions about whether or not the cosmos is a hologram are not just theoretical. This pursuit has the potential to change our view of the universe and everything in it, from the smallest building blocks of matter to the enormous invisible forces at work. Progression in this area not only helps us determine the veracity of the holographic principle, but it also raises the possibility of uncovering an additional reality layer that supports both the visible and unseen cosmos. Remember to have an open mind as we explore this issue further. Though somewhat fantastical at first glance, the concepts we are investigating have their roots in rigorous mathematics, extensive experimentation, and decades of scientific study. It is possible that the holographic principle holds the key to the universe's many unsolved riddles. Physical structures that can diffract light into images are known as holograms. Either the encoded material or the final picture might be called a hologram. Even without the use of corrective lenses, a holographic picture may provide the impression of depth. Holography refers to both the science and art of creating holograms. The process usually involves illuminating the object with a laser and then recording the reflected light on a media with interference patterns. Holograms are unique in that the whole recorded light field is used to create the picture. This implies that a hologram may be divided into smaller parts, and when lighted, each of those fragments can still show the full image, albeit in a smaller and lower quality than the original. The first step in creating a hologram is dividing a laser beam in half. The object is illuminated by the first beam, which is called the object beam. At the recording medium's surface, the light that has reflected off the item meets a second beam, called the reference beam. A pattern of interference is produced when the two beams meet. On the holographic material, this pattern is preserved. This pattern will be preserved as a holographic picture due to the recording medium's physical and chemical characteristics. Looking at a hologram is like looking at the real thing. The light field is reconstructed from the scattered light from interference fringes, creating an image that shifts slightly depending on your perspective, just like the real thing. What's amazing about holography is that it can replicate a light field nearly perfectly, giving the impression of 3 dimensions, in contrast to traditional photography, which only captures a 2-dimensional depiction of the scene. The storing and retrieval of data is only one of many uses for holographic technology, which also has several creative and promotional uses. Because they can't be recreated without the original master hologram, holograms may also serve as security measures. The use of holography for data storage is among its most famous uses. In comparison to more traditional optical storage systems, this one makes extensive use of the recording medium's capacity to store data, significantly improving data density. New holographic video conferencing technology allows users to see a 3-dimensional picture of the other people in the room, simulating a more in-person conference experience. Holograms are also employed in the field of telecommunications. Displaying objects or artifacts in 3 dimensions without physical touch with holograms is an eye-catching method that is used in retail and exhibits. Items that are fragile or easily broken when handled can benefit greatly from this use. Items that are fragile or easily broken when handled can benefit greatly from this use. Another rapidly expanding area is holographic art, in which artists use holography to create eye-catching works that provide a fresh viewpoint, dimension, and interactivity depending on the viewer's vantage point. You may also apply the idea of holography to audio. In order to provide an immersive audio experience, holographic sound systems use wave field synthesis to create a sound field that closely resembles the original performance. Holographic interferometry, for example, measures changes in the physical characteristics of stressed materials. Holography is one of several sensing and measuring methods employed in science. As a medical imaging technology, holography has the ability to provide 3-dimensional pictures of the human body in real time, making it easier for physicians to identify and evaluate problems without intrusive treatments. Holography is starting to make waves in augmented reality systems. It projects holographic pictures into the user's field of view, creating a more immersive and participatory AR experience. The future of interactive displays and augmented reality stands to be radically altered by the advent of real-time changing holograms, which will provide users with novel means of interacting with digital material. Holography may seem complicated, but its underlying premise is really rather simple. It takes use of the fact that light travels in waves in order to capture and recreate the light waves that an item emits. Holography is a one-of-a-kind imaging technique because of its precise light field recording and reproduction capabilities. Holography is an intriguing area of science and engineering that has great promise for the future, since its possible uses are growing in tandem with the advancements in technology. Holograms are photographic records of light fields that, when projected onto a surface, provide an illusion of complete 3-dimensionality, allowing the viewer to see the holographed object or person without the need for corrective lenses. If one is not using corrective lenses or other intermediate optics, the picture will shift depending on where and how one is looking. The picture seems 3-dimensional, because it adapts to the viewer's location and orientation in the same manner as if the item were still there. In and of itself, the holographic recording is not a picture. Its structure is seemingly random, with variations in intensity, density, or profile. With the right lighting, the hologram may replicate the scene's original light field. A three-dimensional object is seen by the viewer's brain after it processes this light field. The holographic likeness of a person or an item, such as a miniature vehicle or a monument, is a prime illustration of the technology. Exhibits and museums often make use of these to display things in a three-dimensional manner, enabling visitors to see details from various perspectives with the simple motion of their hand. Holograms are a common security feature that credit card issuers use on their cards. For example, a hologram depicting a spinning globe or a bird in flight may seem different depending on the light's angle of incidence, making it harder to fake. Holographic sights on contemporary weapons are yet another example. To compensate for variations in the shooter's eye location, this sight employs a holographic display to overlay a reticle picture onto the target seen via the sight, enabling more precise shooting. Improved targeting that accounts for variations in the angle of sight of the shooter. Holograms also have a strong following in the entertainment industry, especially during performances when legendary performers who have passed away are resurrected. Fans may enjoy live concerts even after the artist has passed away thanks to these shows, which employ a large-scale holographic hologram to mimic the artist's look and movement. Holographic displays are a marketing tool that may be used to draw attention to items at trade exhibits or in shop windows. These exhibits provide a novel and interesting method to present products by displaying them in great detail or by demonstrating how they work. Holograms may be a great tool in science teaching because they allow us to depict intricate three-dimensional objects like molecules or the human body, which students find more accessible and simpler to grasp than two-dimensional representations. Some nations have tried out holographic leaders who deliver lectures from many places at once as holograms. These leaders might be politicians or CEOs. A sense of presence and engagement may be achieved using this technology, even when the individual is not physically there. By encoding data in 3 dimensions, holographic memory offers a significant capacity boost over conventional storage systems. Exciting possibilities for future data management exist with this technology, which is currently in the developing stage. The usage of holographic technology in augmented reality systems is on the rise, allowing users to project interactive three-dimensional objects into real-world settings and control them with gestures. This software combines the physical and digital realms to improve the gaming, design, and remote teamwork experiences for its users. The goal of telepresence systems, which use holographic technology, is to make distant meetings seem more natural and engaging by creating realistic three-dimensional images of conference participants. In holographic art, the artist manipulates light, glass, and mirrors to produce an optical illusion that changes in appearance depending on how the observer stands in relation to the piece. As an alternative to more conventional forms of creative expression, it provides artists with fresh opportunities to experiment with space and light. When it comes to customer service, holographic assistants are becoming more common in retail settings. These assistants can answer questions, provide clients information, and even show them around the shop. It is possible to create these holographic workers to speak different languages and do different types of customer support jobs. Holographic models and apparel lines have recently made an appearance at fashion shows, providing designers with a new approach to present their work that may better capture the attention-grabbing details of motion and texture that would otherwise go unnoticed in static displays. Digital billboards in densely populated cities are increasingly showing holographic ads, which provide a more engaging and attractive manner to attract consumers' attention than traditional two-dimensional ads. Virtual reality environments frequently use holographic elements to create more immersive and realistic user experiences. This is especially true in simulations used for training in fields like aviation and medicine. Holograms of different human organs and other parts of the body can be utilized for detailed study and surgical practice in medical training, eliminating the need for real human bodies. These examples demonstrate the transformative potential of holographic technology and its applications across many fields, from security and entertainment to education and healthcare. By capturing the light reflected off an object and then reassembling it, holographic technology creates the illusion of depth. The first step is to use a laser beam that has been divided into two parts, one for the item and one for the reference. A photographic plate or digital sensor may be used as a holographic medium once the item has been illuminated by the beam of light. Meanwhile, the reference beam is aimed in such a way that it also hits the recording medium. When the reference beam and the object's light interact directly, an interference pattern is formed. To create a three-dimensional picture, it is necessary to capture not only the light's intensity but also its phase, and this interference pattern does precisely that. For the purpose of maintaining the object's depth information, phase refers to the location of the light wave's peaks and troughs. With the reference beam, or a comparable laser beam shining only on the hologram, the interference pattern will cause the light to be refracted, allowing the original light waves to be reconstructed. Uses refraction to restore the original light waves emitted by the item. The holographic picture is really this restored light. As you navigate the hologram, the depth cues change, creating the illusion of 3 dimensions, just as when you're really touching the thing. Holograms get their distinctive 3-dimensional look from this phenomenon, which may be experienced even without the use of special glasses. A major advantage of holographic technology is the massive quantities of data it can store in a very tiny area. A hologram may store many bits of data at a single location. Holography is being investigated as a potential next-generation data storage method because of its quality. Holography may be used for more than just visual purposes. You may use it with audio as well. In order to create an immersive audio experience, holographic sound systems are designed to replicate sound precisely as it would be heard from a real source. A hologram may be made using either an analog or digital approach. In contrast to digital holography, which uses high-resolution digital sensors and computers to capture and reconstruct holographic images, analog holography relies on photographic plates to record holograms. However, digital holography offers more flexibility in terms of image manipulation, such as the ability to adjust focus magnification and aspect ratio after recording. Holographic technology is also essential in enhancing product and document security. Holographic labels, for example, are utilized in many industries to prevent counterfeiting and forgery because they are extremely difficult to reproduce without the original master hologram. Detailed 3-dimensional pictures of interior systems and organs are being created by medical professionals using holography. These pictures are especially helpful for complicated procedures because they allow surgeons to make more accurate diagnoses and treatment plans. The goal of holographic video conferencing research and development in the field of telecommunications is to create virtual in-person meetings by projecting photorealistic holograms of participants into various venues. This innovation has the potential to completely alter our methods of distant communication by creating the illusion that all participants are physically there. Holographic technology has enormous promise as a teaching tool. It paves the way for the development of dynamic 3-dimensional visual aids that may improve education, particularly in fields where visualizing concepts has a profound effect on comprehension, such as astronomy, chemistry, and biology. Holographic displays have also found their way into marketing and retail as a means to captivate and involve consumers. Products may be shown in stunning 3-dimensional detail on these screens, which makes them more enticing and simpler to grasp for buyers. Artists have taken to holography as a medium, creating interactive and immersive works of art. Depending on the angle from which one looks at these pieces of art, they take on new forms and meanings. Holographic features are being used more and more in AR and VR systems to make the user experience more immersive. These innovations provide more immersive experiences by combining digital and real-world elements in interesting ways. The adaptability of holographic technology has led to its unexpected use in fields like landscape architecture and agricultural planning, where the visualization of land use changes or expansive development projects is invaluable. Holography is breaking new ground in every industry, including entertainment. It enables the production of intricate, three-dimensional visual effects that can be effortlessly incorporated into both animated and live-action films, giving viewers a more captivating and lifelike experience. The ever-expanding possibilities of holographic technology are altering the way we engage with the digital world and offering fresh breakthroughs in a wide range of industries. At the most basic level of physical theory, known as quantum mechanics, the behavior of matter is described in terms of the energy levels of atoms and subatomic particles. Its main contribution to classical mechanics is the concept of superposition, which says that a system may exist in more than one state simultaneously until one of them is seen. However, between 1907 and 1915, Albert Einstein created general relativity, a theory of gravity. The general theory of relativity states that masses distort space-time, which causes the gravitational influence between them to be detected. Planetary motion and the physics of black holes are two examples of large-scale processes that have been greatly aided by this theory. Probabilities are fundamental to quantum mechanics. About dark holes. Probabilities are fundamental to quantum mechanics. How likely it is that an item will be found at a certain location or condition is described using mathematical functions. Because of this random quality, things like quantum tunneling may happen when particles go past obstacles that they normally shouldn't. The field equations provide the most rigorous mathematical formulation of general relativity. They explain how mass and energy alter the structure of spacetime and, in turn, how this altered spacetime governs the motion of mass and energy. Its predictions of cosmological events, including as black holes and expansion, revolutionized our understanding of the structure of the cosmos. Among the most formidable obstacles in the field of physics is the integration of general relativity with quantum mechanics. When explaining the cosmos on the microscopic scale, quantum physics shines, but when it comes to the macroscopic scale, general relativity reigns supreme. Their seeming mismatch at certain intersections, such within black holes or at the Big Bang's instant, indicates a knowledge vacuum. A key tenet of quantum physics is the uncertainty principle, which states that the accuracy with which a particle's location is known is directly inversely proportional to the precision with which its momentum can be measured. By introducing a degree of basic uncertainty into the subatomic realm, this principle questions the determinism of classical physics. According to the theory of general relativity, the magnitude of the gravitational field determines the pace at which time passes. Experimental evidence that clocks operate more slowly in the vicinity of a large object lends credence to the idea of gravitational time dilation. Big thing in quantum physics. Entanglement is a phenomena in quantum mechanics that occurs when two or more groups of particles interact in such a manner that their individual quantum states cannot be described apart from each other, regardless of how far apart the particles are. As a reflection of his unease with the idea, Einstein characterized this occurrence as eerie distant activity. The consequences of general relativity impact our understanding of the universe's dynamics, and these effects reach the cosmic scale. Since Edwin Hubble's observations validated the theory's prediction of expanding cosmos, it has served as a foundation for cosmological models. Another fundamental idea in quantum mechanics that goes against conventional wisdom is the wave-particle duality. What this means is that, depending on the measurement, every quantum entity may behave like a particle or like a wave. The classic double-slit experiment exemplifies this duality by demonstrating that light may exhibit wave and particle properties simultaneously. Gravitational waves, which are geometrical representations of spacetime, have been predicted by general relativity. It took the LIGO partnership until 2015, a full century after Einstein made his original prediction, to make the first direct detection of them. Chemistry and many contemporary technologies, including semiconductors and lasers, are profoundly affected by quantum physics. It sheds light on the workings of the atomic and molecular structures, the nature of chemical bonding, and the photoelectric effect. Technologies such as GPS navigation rely on general relativity to compensate for the time dilation effects caused by the satellite's velocities and the lower gravitational field at their vantage points relative to Earth's surface. Although they are based on very distinct assumptions, both theories are cornerstones of contemporary physics. The domain of black holes best illustrates this duality. There, the concepts of singularity and event horizon present formidable theoretical obstacles that can be adequately addressed by a combination of general relativity and quantum mechanics, but not by either theory alone. Introducing fields that traverse space and time, quantum field theory is a development of quantum mechanics. In this view, particles act as stimuli for these fields. This model has been crucial in developing the standard model of particle physics, and it effectively describes all known basic forces except gravity. Another important result of general relativity is the equivalence principle, which asserts that a body's gravitational mass, which controls the strength of the interactions between them, and its inertial mass, which controls its reaction to external forces, are basically the same. This notion has been rigorously tested and shown to be basic to the theory. An example of a notion introduced by quantum mechanics that is both philosophically and technically difficult is the collapse of the wave function, which occurs when a quantum system abruptly transitions from a superposition state to a specific state. This departure from classical reasoning is common in quantum physics. Some of the most stunning and refined physical solutions, like the Schwartz, have been derived from general relativity. The space-time around a spherical object, such a planet or a black hole, is described by the child solution. The advancement of black hole physics relied on this answer. To fully appreciate the significance of any theory, one must be familiar with its area. On the microscopic scale, we have quantum physics, and on the cosmic scale, we have general relativity. As far as modern physics is concerned, one of the holy grails is the hunt for a quantum gravity theory that can reconcile these scales. Experiments using particle accelerators and astronomical observations, among others, are continuing to test the limitations of general relativity and quantum physics, which is helping us enhance our knowledge of the universe's basic workings. The study of energy and matter at the most microscopic sizes, down to the level of individual atoms and subatomic particles, is known as quantum mechanics. Incorporating ideas that seem paradoxical in daily life, its principles provide a challenge to the classical mechanics that dominated science for decades. The duality of waves and particles is a fundamental concept in quantum physics. Every quantic entity or particle may be defined in terms of either a particle or a wave according to this concept. Exampled below are electrons, which, depending on the experimental conditions, may display either behavior. Werner Heisenberg's uncertainty principle is another foundational idea. It asserts that it is physically impossible to know two physical variables, such as location and momentum, to an arbitrarily fine degree at the same time. The more exact a measurement of one characteristic is, the less controllable or known the other attribute becomes. Until it is measured, a quantum system may exist in numerous states simultaneously. This phenomenon is called superposition. An electron in a quantum state, for instance, might inhabit several energy levels at once until it is collapsed to a particular state by observation. When two or more sets of particles interact in an entangled manner, it becomes impossible to characterize the quantum states of the individual particles apart from the states of the other sets, regardless of how far apart they are physically located. As a result, relationships are established between the system's measurable physical characteristics. One interesting quantum phenomena is quantum tunneling, which allows particles to travel through a barrier that they would normally not be able to. This effect is fundamental to many physical processes, including stellar nuclear fusion, and it finds use in cutting-edge technology such as scanning tunneling microscopes and tunnel diodes. Energy charge and rotational momentum are two examples of characteristics that are quantized in quantum physics. This means that they can only take on discrete values rather than any value at all. Niels Bohr also offered the notion of complementarity, which is an important idea. It states that things have supplementary characteristics that can't be seen or quantified at the same time. To grasp the duality of matter and light, this idea is fundamental. The mathematical formulation of quantum mechanics gives it its probabilistic aspect. The description of systems is not in terms of discrete states, but of a probability distribution of states. A wave function, which stores the probabilities of all system configurations, describes this probability. When quantum systems interact with their surroundings in a certain manner, a phenomenon known as quantum decoherence occurs. This happens when the superposition of states decays into classical probabilities, thus making the system behave conventionally under specific circumstances. In quantum mechanics, Born's rule is a fundamental principle that uses the mathematics of wave functions to determine the probability distributions of position, momentum, and other particle properties. Quantum rules, such as the Pauli exclusion principle, indicate that identical fermions, electrons and similar particles, cannot occupy the same quantum state at the same time. Multiple physical phenomena are explained by this theory. For example, the periodic table and the behavior of electrons in atoms are both clarified. One phenomenon that defies explanation by conventional physics is quantum interference, which occurs when quantum waves combine, reinforce, or cancel one another out, resulting in unique patterns. Quantum cryptography and computation are based on this idea. The foundational equation of non-relativistic quantum mechanics is the Schrödinger equation, which was developed by Erwin Schrödinger. It uses wave functions to explain the temporal evolution of a physical system's quantum state. In quantum field theory, particles are seen as excited states of an underlying field, with quantum numbers identifying each state. This theory extends quantum mechanics to fields. Building the current model of particle physics requires this structure. Like angular momentum in conventional physics, quantum particles have a basic attribute called spin. Quantum physics uses the concept of intrinsic angular momentum for spin, rather than the physical concept of spinning motion. Unlike conventional computers, quantum computers are able to process data by using quantum mechanics. It is able to do calculations by using quantum phenomena such as superposition, entanglement, and quantum interference. It is not feasible to produce a perfect replica of any given unknown quantum state according to the no-cloning theorem of quantum mechanics. Quantum cryptography and communication are greatly affected by this theory. According to quantum theory, seemingly empty space is really teeming with virtual particles that appear and disappear at will. Quantum field fluctuations and the Casimir phenomenon may be understood with the help of this virtual particle idea. An important finding in quantum mechanics, Bell's theorem states that there are bounds on the correlations that may be seen between entangled particles if the universe is characterized by local realism, a theory consistent with Einstein's theory of relativity. The mainstream model of quantum mechanics is supported by experimental evidence that these correlations go against Bell's inequality. Albert Einstein's theory of general relativity transformed our perception of space, time, and gravity. Fundamentally, the theory argues that contrary to what Newtonian physics proposes, gravity is really the curvature of space-time that results from the interaction of mass and energy, and not a force between masses. One of general relativity's key concepts is the equivalence principle, which states that acceleration has the same effect as gravity. According to this concept, in a gravitational field, the rate of fall is the same for all objects, independent of their mass and composition. The mathematical foundation of general relativity, Einstein's field equations explain how energy and matter affect space-time curvature, and how this curvature controls the motion of these two quantities. The idea of space-time merges the three spatial dimensions with the one temporal dimension to form a continuous four-dimensional plane. The theory of general relativity states that the laws of motion for physical objects are determined by the curvature of space-time, which may be induced by matter and energy. Time does not, according to general relativity, move at a constant pace. Both speed and the force of gravity may influence it. Time goes more slowly for an object in a dense gravitational field, or one that is moving quickly relative to a huge body or a resting item. The existence of black holes, space areas with such a tremendous gravitational pull that not even light can escape them, is one of the most intriguing predictions of general relativity. The collapsed cores of big stars are the building blocks of black holes. The phenomena of gravitational lensing, in which light is bent around large objects, is also predicted by general relativity. From our vantage point, astronomers are able to see stars and galaxies that are hidden behind large objects because of this effect. Gravitational waves, which are light-speed ripples in space-time, are also introduced by the theory. Black hole collisions and stellar explosions, two of the most intense and violent phenomena in the cosmos, are the sources of these waves. Countless tests and observations have shown general relativity true. These include the sun's light bending, accurate measurements of planetary orbits, and most recently, the direct discovery of gravitational waves by LIGO and other observatories. The hypothesis shapes our knowledge of the expansion of the universe and the dynamics of galaxies and clusters of galaxies, and it has far-reaching consequences for the cosmological model. According to the theory of general relativity, the Big Bang was the beginning of space and time, and both will undergo continuous change in the future. The answers to Einstein's field equations explain the expansion of the cosmos, which is not static but rather ongoing. Clocks aboard aircraft and satellites have reliably recorded the impact of time dilation in high gravitational fields, further supporting the idea that time runs slower near huge things, which is another consequence of general relativity. According to the idea, the total mass density of the universe determines the possible universe geometries. The outcome of the universe's expansion, its ultimate cessation of expansion, or its final collapse into itself is determined by these geometries. Because general relativity is not linear, space-time dynamics are rich and complicated. Understanding wormholes and time travel, for example, requires solving Einstein's equations, which are, of course, theoretical at this point. Gravity Probe B and other space-based investigations have confirmed a prediction of general relativity, that spinning planets, like Earth or a neutron star, may pull the space-time around them. This process is known as frame dragging. How simultaneity is understood is also altered by the theory. What seems to be simultaneous events in one reference frame could not be in another, particularly if the observers are in separate gravitational fields or are in motion with respect to one another. For global positioning system technology, general relativity is also vital. Because of their speed and the fact that Earth's gravitational field is less at high altitudes than it is at ground level, the GPS satellites in the constellation must take both of these factors into consideration. One of the predictions of general relativity is the Shapiro delay, which occurs when signals approach a big object and take longer to travel owing to the curvature of spacetime. Famous examples of gravitational lensing predicted by general relativity include Einstein's cross. It happens when a distant object, such a quasar, has its light distorted into numerous pictures visible from Earth by a large galaxy in the background. General relativity has been successful, but it has not yet been united with quantum mechanics, the second major framework of contemporary physics. One of the great unfinished business in theoretical physics is this unification, which could provide light on the nature's underlying rules. The two cornerstones of contemporary physics, general relativity and quantum mechanics, have long been at war over how to explain certain features of the cosmos. This disagreement stems from the fact that general relativity is better at depicting the universe at vast sizes, including the force of gravity, but quantum mechanics is very good at explaining events at very tiny scales. Include the force of gravity in their description of the universe at bigger sizes. In a black hole, there is a striking contradiction between general relativity and quantum physics. In the heart of a black hole, there is a singularity where general relativity states that all mass is condensed into one point, creating an infinite curvature of spacetime due to the zero volume and infinite density of that point. On the other hand, such singularities cannot exist in quantum mechanics, since this theory suggests that physical quantities may have an endless number of values. As a probabilistic theory, quantum mechanics attempts to foretell the probability of particles being in certain states. On the other hand, general relativity uses the equations of spacetime curvature to make explicit predictions about future events. The two theories are fundamentally at odds with each other philosophically and mathematically due to their differing approaches to determinism and uncertainty. Disagreement stems from the two theories' divergent views on time. According to general relativity, mass and energy have the ability to bend spacetime, which is a fabric consisting of time and three spatial dimensions. On the other hand, time is seen in quantum physics as an amorphous background parameter that is independent of physical forces like gravity. In quantum physics, the idea of gravity is still a mystery. Gravity remains unquantified, in contrast to other basic forces that have been well explained by quantum field theory. This is a major missing piece that prevents general relativity and quantum physics from being fully integrated. The foundation of quantum mechanics, quantum field theory, deals with infinities that occur in its computations by using the idea of renormalization. The theory becomes non-renormalizable, nevertheless, when these methods are applied to the gravitational force as given by general relativity. Because of this, the standard approaches of governing infinities in quantum theories fail when applied to gravity. In contrast to the quantum principle that states all fields, including gravity, should be quantized, the central idea of space-time geometry and general relativity is at odds with this idea. Quantum theory states that space-time must be made up of discrete quantized units, even if under relativity, space-time is a smooth continuum. Problems might also arise from experimental evidence. According to quantum theory, space-time must consist of discrete quantized units. Problems might also arise from experimental evidence. Remarks of general relativity, like as the curvature of light caused by gravity, have also been verified with remarkable accuracy, as have effects predicted by quantum theories. So far, no experiment has been successful in exploring the zone, close to the Planck scale, where quantum and gravitational effects coexist. The construction of a quantum theory of gravity, which is required to settle these disputes, is often illustrated by the problem of black hole information loss. Another major problem is how cosmological phenomena are handled. For example, the Big Bang theory, which is based on general relativity, proposes a singularity at the beginning of the universe, which is at odds with quantum mechanics. Quantum gravity theories have tried to incorporate a quantum process that leads to the Big Bang in place of this singularity, but no one has come to a unanimous agreement. General relativity's assumptions about the nature of space-time are further called into question by the idea of quantum entanglement. It would seem that the relativistic limit, which states that no information can travel faster than light, is violated if, as quantum mechanics implies, particles can instantly change each other's states across huge distances. Innovative yet untested ideas such as string theory and loop quantum gravity have emerged from efforts to formulate a theory of quantum gravity. Despite the revolutionary alterations to space, time, and matter that these theories suggest, we still lack concrete, testable predictions to back them up. The discrete quantum states of quantum physics are inherently at odds with general relativity's dependence on spacetime as a smooth, continuous entity. When it comes to comprehending the reality's texture, this disparity illustrates the conceptual divide between the two theories. The conceptual and scientific challenges of bringing general relativity and quantum physics together need a radical change in our understanding of the relationships between events occurring on both the greatest and tiniest scales. If these disagreements can be resolved, a new physics revolution may be ushered in, maybe on par with the ones that occurred with Einstein's original relativity theory or the birth of quantum mechanics. Although the success of each theory in its particular domain proves that they do in fact explain certain features of the world, the fact that they cannot come to terms with one another implies that a more comprehensive and basic comprehension of the cosmos remains elusive. With the promise of new technology and insights into the cosmos, as well as solutions to theoretical puzzles, the pursuit of a unifying theory is one of the most fascinating and difficult areas of contemporary physics. Theoretical physicists, cosmic evolutionists, black hole scientists, and anybody interested in the building blocks of matter must keep digging into quantum gravity. To go into this uncharted territory, experimental physicists will need to adopt novel strategies and maybe develop cutting-edge technology that can probe the interplay between general relativity and quantum mechanics on scales and under circumstances never before achieved. At last, the long-sought-after settling of disputes between general relativity and quantum mechanics on sizes and under circumstances never before achieved. In the end, a whole new way of looking at the cosmos will be needed to settle the disputes between general relativity and quantum mechanics, not to mention some tweaks to current theories. At the event horizons of black holes, the threshold beyond which nothing, not even light, can escape, the conflicts between general relativity and quantum mechanics become most apparent. In these very gravitational settings, the two theories' underlying assumptions clash, exposing fundamental discrepancies in our cosmic knowledge. A surface characterized by an escape velocity equal to the speed of light is called the event horizon in general relativity. This boundary is the point at which space-time curvature becomes infinitesimally severe, drawing everything that passes it into the black hole's singularity at its core. But quantum physics brings us the idea of information preservation, which means that data can't really be lost or destroyed. For black holes, this is a major issue since it goes against a cornerstone of quantum mechanics. That information is lost as it falls beyond the event horizon. The black hole information paradox is a result of this disparity. There is a basic contradiction between general relativity and quantum physics, since the latter states that information must be preserved while the former states that information might be irretrievably lost within a black hole. Black holes are quantum objects. Solving this conundrum will need learning more about their physics and the fate of information after it passes the event horizon. According to quantum field theory, quantum fluctuations close to the event horizon cause black holes to release radiation, which is now referred to as Hawking radiation. Classical ideas of black holes as objects only affected by gravity are challenged by this radiation, which suggests that black holes also possess a temperature and entropy. The black hole's energy is eventually evaporated as a result of Hawking radiation. On the other hand, this raises concerns about data retention, as it implies that data encoded in matter that falls into a black hole may be erased when the black hole evaporates. This disagreement calls into question our grasp of general relativity and quantum physics' underlying concepts. It makes us reevaluate what data does in the cosmos and how black holes work. One possible explanation for the black hole information paradox is the black hole complementarity theory, which states that while information seems to be lost from the viewpoint of an observer falling into the black hole, it is really maintained from the perspective of an outsider looking in. On the other hand, some have proposed updating either general relativity or quantum mechanics, while others have proposed introducing new theories that can bring the two theories' competing concepts together at the event horizon of black holes. Persistent endeavors to comprehend black holes, their function in the cosmos, and its consequences for our comprehension of basic physics have kept the study of black hole physics among the most vibrant domains of theoretical physics. In addition to answering some of the most fundamental problems in theoretical physics, like what is space, time, and information, solving the conflicts at black hole event horizons is critical for expanding our knowledge of the cosmos. Investigating black holes may provide light on the beginnings, end, and basic rules of the universe, which might change our view of those topics significantly. Observations of black hole mergers using gravitational wave astronomy provide up new avenues for testing the predictions of quantum mechanics and general relativity in highly gravitational settings, which might lead to a solution to the black hole information dilemma. A unifying theory of quantum gravity based on a synthesis of general relativity and quantum mechanics is ultimately necessary to resolve the conflicts at black hole event horizons. This is one of the greatest difficulties in modern theoretical physics. Conflicts at black hole event horizons will keep pushing the boundaries of our knowledge of reality and theoretical physics in quest of a unifying theory until that time comes. When general relativity and quantum physics meet, as they do in the case of black holes, a basic conundrum known as the information paradox emerges. It questions our knowledge of the behavior of information in the cosmos and centers on what happens to data when it falls into a black hole. There is no way to generate or delete information, according to classical physics, as it is believed to be preserved. Many scientific hypotheses rely on this concept, and it is fundamental to our knowledge of the physical universe. When we think about the very gravitational settings close to black holes, where quantum physics and general relativity clash, the behavior of information becomes murkier. When matter collapses into a black hole, it disappears beyond the event horizon and into the singularity at the core of the whole, as stated by general relativity. Once it goes beyond the event horizon, it disappears into the black hole's singularity. This goes against the idea of information conservation, as it means that any data contained in that matter is likewise gone. Contrarily, information conservation is a cornerstone of quantum physics. According to quantum theory, data about a system is permanently stored in its state and cannot be erased. The black hole information conundrum arises from the conflict between these two basic notions. When it seems like information is lost the moment it goes into a black hole, how can it be preserved, according to general relativity? Learning more about black holes and how quantum systems behave in very gravitational settings can help us solve the information dilemma. The concept of black hole complementarity has been put up as a possible explanation for the paradox. According to this theory, information is retained when seen from the outside of the black hole, but seems to be lost when seen from the inside when an observer is pulled into the black hole. A different approach would be to provide new theories that can reconcile the contradictory rules of general relativity and quantum mechanics when applied to black holes, or to make adjustments to the existing theories. Research into the information paradox has prompted fresh ideas in theoretical physics and greatly improved our knowledge of black hole physics. New possibilities to test the predictions of quantum mechanics and general relativity in severe gravitational settings have emerged from observations of black holes, notably those produced by gravitational wave astronomy. In addition to helping us better comprehend black holes, overcoming the information paradox will allow us to tackle some of theoretical physics' most fundamental concerns about space, time, and information. Investigating the information paradox may provide light on the Big Bang, the universe's ultimate destiny, and the rules that govern its behavior, all of which might dramatically alter our current knowledge of these topics. One of the greatest issues in theoretical physics today is figuring out how to reconcile quantum gravity with general relativity and quantum mechanics in order to solve the information paradox. The information paradox will keep intriguing researchers in theoretical physics and testing our assumptions about the universe until a satisfactory explanation is found. Jean Michel and Pierre-Simon Laplace initially proposed the idea of dark stars in the late 18th century. They postulated that a star would become invisible and have an escape velocity greater than the speed of light, resulting in what we now call a black hole. However, it wasn't until Albert Einstein's theory of general relativity offered a rigorous mathematical framework for understanding black holes in the early 20th century. According to Einstein's calculations, there must be things in the universe with such intense gravity that not even light can escape. We now refer to them as black holes. In the 1960s, physicist John Wheeler popularized the idea of black holes and helped bring them into the mainstream of astronomy. Wheeler also invented the term black hole itself. A singularity at the heart of a black hole and its infinite density were the primary points of interest in the early theories concerning these objects. These characteristics prompted inquiries into the dynamics of space, time, matter, and energy in the neighborhood of black holes, as well as the characteristics of these entities themselves. Their event horizon, the line beyond which nothing can escape, is one of the most fascinating features of black holes. There have been many discussions and hypotheses on black holes and their function in the cosmos, stemming from speculations over what is beyond the event horizon. In their early attempts to explain black holes, several theoretical frameworks looked to general relativity and classical physics. On the other hand, as our knowledge of quantum mechanics has grown, it has become crystal evident that black holes pose a major threat to our established physical theories. Our knowledge of black holes was expanded in the 1970s with the discovery of Hawking radiation by physicist Stephen Hawking. Black holes, according to Hawking radiation, may eventually evaporate because to the particles and energy they generate. The implications of this finding for what happens to data when it falls into a black hole are unclear. Information cannot be destroyed, even in the event of a black hole, according to quantum theory. Quantum physics states that data cannot be deleted. However, According to the black hole information paradox, data might theoretically vanish into thin air if a black hole were to totally evaporate. Alterations to quantum physics or general relativity, or the development of new theories that might combine the concepts of both, were the first targets of efforts to address the information conundrum. As a possible explanation for the information paradox, the theory of black hole complementarity posits that, while seeming to be lost to an observer plunging into the black hole, information is actually retained from the viewpoint of an outsider. An alternative theory suggests that the black hole's particles have information encoded in their delicate connections with one another, or that new conservation rules should be included into quantum mechanics. In spite of these first efforts, the information paradox continues to be a formidable obstacle in the field of theoretical physics, necessitating a more thorough understanding of black hole dynamics and the operation of quantum systems in very gravitational settings. New insights into the information paradox and fresh inquiries into the universe's and black holes' essential nature have resulted from recent advancements in theoretical physics, such the ADS-CFT correspondence and the firewall paradox. Gravitational wave astronomy and other black hole observations open up new avenues for testing the predictions of general relativity and quantum mechanics in highly gravitational settings, which might lead to a solution to the information conundrum. New ideas and discoveries are constantly emerging from the study of black holes and the information paradox, which is a thriving field of theoretical physics. One possible solution to the information conundrum might be to combine quantum gravity with general relativity and quantum mechanics. The possibility that everything we experience is an illusion or a hologram has long been a topic of philosophical discussion among humans. The concept of a simulated reality, or a cosmos that is not what it seems to be, was central to the cosmological beliefs of many ancient civilizations. This included the Mayans, the Egyptians, and the Hindus. The idea of Maya in Hindu philosophy implies that everything in this universe is a projection of God's awareness, an illusion. According to this Maya, everything in the universe is a manifestation of God's awareness. According to this theory, the cosmos is only a surface representation of more basic, invisible truths. In a similar vein, Plato and other ancient Greek philosophers pondered the nature of reality and the prospect that the material world we see is really a projection of something deeper and more basic. With the advent of quantum physics and its consequences for our knowledge of space, time, and matter, the idea of the cosmos as a hologram became popular in contemporary times. Physicist David Bohm was an early believer in the holographic universe idea, which holds that the cosmos is like a hologram and that its constituent parts carry knowledge about the whole. This theory proposed a more integrated and comprehensive picture of the cosmos, which went against conventional wisdom. A physicist named Leonard Susskind and his colleagues refined the holographic principle in the 1990s. This concept states that any two-dimensional surface may encode all the information contained in a three-dimensional volume. According to this theory, our cosmos might be like a holographic projection, where a two-dimensional image of space seems to be floating above a three-dimensional reality. Black holes may not store their information inside, but on their event horizons, according to the holographic principle, which has far-reaching consequences for our knowledge of these objects. Space and time as we know them are called into question by this concept, which also calls into question the very essence of reality itself. Recent developments in theoretical physics, such as quantum gravity and string theory, provide credence to the holographic universe idea by raising the possibility that space-time is emergent rather than fundamental. For instance, according to string theory, little vibrating strings rather than particles are the basic units of the cosmos. These strings may generate three-dimensional structures, which can be used to formulate the holographic principle mathematically. Research on black holes lends credence to the holographic universe idea as well. Specifically, that the entropy of these objects is directly related to the area of their event horizons, not their volume. This points to a strong relationship between the shape of black holes and the data they hold. The holographic world idea has been strengthened by new findings in quantum information theory, which explain quantum entanglement and its use in higher dimensional information encoding. Our current world may be more complex and interdependent than we realize, according to the holographic universe idea, which questions our accepted wisdom. It makes us reevaluate our assumptions about the universe, time, and the very essence of being. A captivating view on reality and our role in the world is offered by the holographic universe idea, which is still hypothetical and the topic of continuing study and discussion. The holographic universe theory has captivated thinkers throughout history, from ancient cultures to contemporary scientists, and has prompted fresh inquiries into the nature of reality and our role in it. In the end, it doesn't matter whether the world is real or not. Thinking about it pushes us to learn more about the limits of our comprehension and the secrets of the universe. Amazingly, according to the holographic principle, a two-dimensional surface may contain the information content of a three-dimensional volume. This idea comes from theoretical physics. This concept calls into question our long-held assumptions about the nature of reality, time, and space. Originating in attempts to bring together quantum mechanics and general relativity, two cornerstones of modern physics that appear incompatible at certain scales, the holographic principle suggests that space-time itself may be essentially holographic, with the appearance of three-dimensional space emerging from a lower-dimensional reality. This theory has far-reaching consequences for our knowledge of black holes, leading some to speculate that the information they hold is encoded on their event horizons rather than inside them. Space and time as we know them are called into question by this concept, which also calls into question quantum physics and gravity. The holographic principle states that, contrary to popular belief, the amount of information contained inside a given area is directly correlated with its surface area and not its volume. This allows for the description of a higher dimensional volume to be contained entirely in a lower dimensional surface. String theory, quantum gravity, and black hole entropy research are just a few of the theoretical physics domains that uncover evidence for the holographic principle. According to these domains, space-time could not be basic, but rather emergent, with higher dimensional structures recording the information contained in lower dimensional regions. For instance, according to string theory, little, vibrating strings, rather than particles, constitute the building elements of the cosmos. These strings may generate three-dimensional structures, which can be used to formulate the holographic principle mathematically. Furthermore, the holographic principle clarifies that the entropy of black holes is directly related to their event horizon's surface area and not their volume. This points to a strong relationship between the shape of black holes and the data they hold. The holographic principle has been strengthened by new findings in quantum information theory, which explain quantum entanglement and its use in higher dimensional information encoding. The holographic principle is still very much a working hypothesis, but it does provide an intriguing new way of looking at the universe and our role in it. The holographic universe theory has captivated thinkers throughout history, from ancient cultures to contemporary scientists, and has prompted fresh inquiries into the nature of reality and our role in it. Fresh perspectives on the essential character of reality and our role in it. Whether or if the world is really holographic, thinking about these kinds of issues pushes us to learn more about the universe and its secrets. According to the holographic principle, a two-dimensional boundary may completely store the information content of a three-dimensional volume. This implies that the data recorded on the surface of a given area may represent all the events that take place inside that space. Think of a hologram as an example to help you grasp this concept. A photographic plate or other two-dimensional surface may encode a three-dimensional picture in a hologram, store information in a flat format like an image. A laser beam makes the hologram's three-dimensional picture seem to leap out of the flat surface. It is also possible to think of the data characterizing a space volume as being projected onto its border, according to the holographic principle. This enclosing volume has all the necessary information to be described by this border, which is commonly called a screen or a brain. The holographic concept, as applied to black holes, states that the data about the energy and matter that enters a black hole is not annihilated but rather stored on its event horizon, the limit beyond which nothing can be saved, the line that no one or object can cross. This concept questions the long-held belief in information conservation and raises the possibility that investigating a black hole's event horizon might provide clues about the object's contents. String theory, which proposes that little vibrating strings rather than particles are the basic building elements of the world, lends credence to the holographic principle, among other branches of theoretical physics. The mathematical foundations of string theory give birth to the holographic principle by definition. Theoretically, string theory suggests that there could be more than just time and space in the cosmos. We could not be aware of its other dimensions because they have been compressed or buried. With the help of these additional dimensions, we may encode three-dimensional data onto two-dimensional surfaces using the holographic principle, which operates in a higher dimensional realm. Black hole entropy research is another theoretical field that backs the holographic principle. The entropy of a system is a measure of its disorder or unpredictability. The event horizons of black holes contain entropy. The area of the event horizon, not the volume, is the one that determines the entropy of a black hole, as stated by the holographic principle. Like a hologram, this would indicate that the black hole's contents are encoded on its surface. The holographic principle has been strengthened by new findings in quantum information theory, which explain quantum entanglement and its use in higher dimensional information encoding. In sum, the holographic principle provides a fresh perspective on the universe and our role in it. The significance of information in the structure and dynamics of the cosmos is highlighted, leading one to believe that it is more complex and interrelated than previously believed. Although the holographic principle is still theoretical and is the topic of heated controversy, it has contributed much to our knowledge of quantum gravity, black holes, and space-time itself. New understandings about space, time, and the universe's basic rules may be revealed by delving into the ramifications of the holographic principle. It challenges our preconceived beliefs of reality and encourages us to accept the universe's governing rules, as well as the possibility that the cosmos is more mysterious and beautiful than we could have ever dreamed. Two renowned physicists, Leonard Susskind and Gerard 't Hooft, laid the groundwork for the modern holographic concept. Our perceptions of time, space, and reality itself have been impacted by their work on the holographic principle. In the late 1990s, Leonard Suskind's interest in black holes and the information paradox led him to become involved in developing the holographic principle. He, along with other physicists, started to investigate the ramifications of the holographic principle after realizing it may be crucial in answering this contradiction. Gerhard 't Hooft's research into black holes and quantum field theory led to his contributions to the holographic principle. His research on black hole quantum behavior was crucial in developing the holographic principle and its use in this area of study. 't Hooft and Susskind were crucial in clarifying the holographic principle and what it means for our knowledge of the cosmos. Their research laid the groundwork for a new way of thinking about space, time, and data. Progression in theoretical physics, such as quantum gravity and string theory, impacted Susskind and 't Hooft's creation of the holographic principle. In order to develop and investigate the holographic principle, these fields of study provide the necessary mathematical instruments and theoretical framework. For example, Susskind and T. Thanks to Hooft's help, our knowledge of information paradoxes and black holes has grown substantially. Their findings provided fresh insight into the basic characteristics of space and time by elucidating the connection between black hole geometry and the information they hold. Their work on the holographic principle has influenced theoretical physics for decades, opening up new fields of study and encouraging researchers to probe the very fabric of reality. Researchers are still trying to figure out what exactly the holographic principle means, so it's clearly a very fruitful field of study. There are deeper implications for our knowledge of the cosmos, stemming from Susskind and 't Hooft's work on the holographic principle. Their discoveries about black holes and the data they hold have influenced how we think about the universe, quantum mechanics, and the rules of nature. Their work together exemplifies the value of teamwork in expanding our knowledge of the cosmos and the strength of scientific inquiry. Susskind and 't Hooft have inspired physicists of the future and contributed to expanding human understanding via their efforts. In sum, our current cosmic knowledge owes a great debt to the work of Susskind and Tehoeft, who developed the holographic concept. Their contributions have provided fresh understandings of space, time, and reality's foundational elements, and they continue to motivate and guide studies in theoretical physics. The holographic principle changes everything about how we see the cosmos and what it means to be real. The holographic principle, which states that a whole volume of space's information may be entirely inscribed on its border, questions our long-held beliefs about the nature of space, time, and the universe's most basic components. As a possible solution to the black hole information conundrum, the holographic principle has far-reaching consequences. If you believe the holographic principle, all data that goes into a black hole is actually recorded on its event horizon, the threshold beyond which nothing can escape, rather than lost. A possible solution to one of the most perplexing paradoxes in theoretical physics might be found in the concept that, by analyzing the event horizon of a black hole, information about the contents of the hole could be recovered. Additionally, the holographic principle clarifies that the entropy of a black hole is directly related to its event horizon region and not its volume. This points to a strong relationship between the shape of black holes and the data they hold. The holographic principle offers a fresh viewpoint on the nature of space and time, and it has far-reaching consequences for our knowledge of the cosmos beyond its effects on black hole physics. The cosmos could be more complex and multifaceted than we had imagined, with information at the heart of its structure and dynamics. A more basic reality recorded on lower dimensional surfaces may give rise to space and time, as stated by the holographic principle. Space and time, according to this theory, are not static concepts, but rather more malleable and interdependent than we had thought. In addition, two cornerstones of contemporary physics, quantum mechanics and gravity, are affected by the holographic principle. We may be able to consolidate our knowledge of the basic forces of nature if the holographic principle is correct in its suggestion of a strong relationship between these two ideas. The holographic principle sheds light on quantum entanglement as well, a phenomena in which two or more particles become so coupled that their states are reliant on each other regardless of their physical separation. Quantum entanglement may be an expression of the more fundamental structure of reality recorded on two-dimensional surfaces, as stated by the holographic principle. This calls into question long-held assumptions about the cosmos and quantum physics. Additionally, cosmology and the Big Bang may be better understood in light of the holographic principle. The holographic principle sheds fresh light on the Big Bang and the early cosmos by proposing that the information content of the universe is encoded on its border. In sum, the holographic principle affects our knowledge of the cosmos and its underlying rules in profound ways. In theoretical physics, the holographic principle enables new areas of investigation and discovery by questioning our standard notions of space, time, and information. The holographic principle is an endeavor to unite general relativity with quantum mechanics, two of the most influential but apparently contradictory physics ideas. It has been difficult to bring these two competing ideas into harmony, although they both explain how the cosmos operates at different scales. Subatomic particle behavior is described by quantum entanglement, uncertainty principle, particle wave duality, and the laws of quantum mechanics. However, black holes, gravitational waves, and the expanding universe are all explained by general relativity, which defines gravity as the curvature of spacetime induced by mass and energy. Applying both ideas at once becomes difficult, especially in extreme settings like black holes or the early cosmos. Inconsistencies between quantum physics and general relativity arise at these scales when the effects of gravity become prominent, with its suggestion that a three-dimensional volume's information content may be entirely recorded on its two-dimensional border. The holographic principle provides a possible solution to this dilemma. This implies that the data recorded on the surface of a given area may represent all the events that take place inside that space. Reconciling quantum physics with general relativity becomes much easier using the holographic principle, which reduces the description of a space volume to its border. It offers a shared structure for the consistent application of both theories, which may one day unite the seemingly disparate domains of general relativity and quantum mechanics. When it comes to black holes, the holographic principle states that the data about the energy and matter that goes into one is not annihilated, but rather stored on its event horizon, the limit beyond which nothing can be saved. The black hole information paradox, which results from the seeming loss of information during black hole evaporation, might be resolved by this notion. Facts about the vanishing of black holes. The holographic principle provides a quantum mechanical framework for understanding the relationship between the describing degrees of freedom of a spatial volume and the corresponding describing degrees of freedom of its border. This offers a fresh viewpoint on spacetime's nature and implies a profound relationship between geometry and quantum physics. The holographic principle, as seen through the lens of general relativity, implies that the geometry of spacetime may be deduced from the data recorded on its border. This suggests that quantum information may have an emergent structure from which gravity emerges. By offering a common framework in which both theories may be consistently applied, the holographic principle provides a viable approach to unifying quantum mechanics and general relativity. The holographic principle is a major breakthrough in our search for the essence of reality, even if its whole consequences have not yet been fully investigated. A major obstacle to addressing the black hole information paradox is the fact that it is among the most difficult problems in theoretical physics. Nevertheless, scientists have put out a number of possible explanations for the conundrum, each of which sheds light on black holes and what happens to data that falls into them from a different angle. The information dilemma surrounding black holes and what happens to data that falls into them may have a possible answer. The concept of black hole complementarity is one possible way to explain the black hole information paradox. Based on this theory, data seems to be lost from the viewpoint of an observer falling into a black hole, but is really retained from the viewpoint of an observer outside the hole. That is to say, rather than being discarded, the data is contained in the correlations between the particles that the black hole emits. Alternatively, one may suggest adjusting the laws of quantum mechanics or general relativity. Some physicists have proposed changes to general relativity to account for the preservation of information inside black holes during their evaporation, while others have proposed changes to quantum mechanics to achieve the same goal. One intriguing possibility is that black holes don't actually emit black light, but rather a type of radiation called Hawking radiation. This suggests that black holes can gradually evaporate over time, releasing particles and energy as they do so. This suggests that the dilemma may be resolved if the information stored inside a black hole is released gradually when the black hole dissipates. The existence of hidden sectors or degrees of freedom within black holes is another possible explanation for the black hole information paradox. If this theory is correct, black holes might store information about the matter and energy that falls into them in the form of hidden variables or structures. Information may be preserved in a manner that is not immediately obvious from the outside via these hidden sectors. Even more outlandish theories have been put forward by some scientists, such as the concept that black holes have firewalls at their event horizons. This theory postulates that the event horizon is a zone of very high radiation or energy that, once entered, renders any data falling into the black hole useless and unrecoverable. This notion is still controversial, but it's a new way to look at the black hole information paradox and maybe solve it. Holography and the holographic principle are both mentioned as potential solutions. Theoretically, the event horizon or the periphery of a black hole's gravitational field may contain all of the information that falls into the hole. The edge of the gravitational field around the black hole, in other words, it's not lost, but rather preserved in a lower dimensional form that doesn't seem good from the outside. In the end, it may take a mix of these concepts or new theoretical frameworks to solve the black hole information dilemma. Although the paradox is still one of the most difficult issues in theoretical physics, researchers are making steady headway and learning more and more about black holes and what happens to data within them. Let's explore some theoretical examples and case studies that show the holographic principle in action and its potential applications. A black hole, created when a huge star collapses, is the starting point for our discussion. The holographic principle states that the event horizon of a black hole, the threshold beyond which nothing can escape, encodes all the information about the matter and energy that falls into the hole. This points to the data still being there, although in a reduced form, on the black hole's surface. Our next stop will be at particles as they approach a black hole's event horizon. From the vantage point of an observer far away, a particle's apparent speed seems to decrease as it gets closer to the event horizon, as stated in general relativity. From the particle's point of view, however, everything seems to be moving along according to plan. The holographic principle, which states that the event horizon encodes information about the particle's state, is compatible with this disparity in the experience of time. The holographic principle provides a useful framework for analyzing quantum entanglement's behavior. Despite their physical separation, particles may become entangled in a manner that makes their states reliant on one other, a process known as quantum entanglement. This suggests a deep connection between cosmology and the holographic nature of reality. Quantum entanglement, according to this principle, could be a manifestation of this underlying structure of reality. Additionally, let's investigate what the holographic principle means for our understanding of the early cosmos. Inflationary cosmology postulates that, immediately after the Big Bang, the cosmos expanded at an accelerated rate. According to the holographic principle, the beginning of the universe's circumstances may be stored on its border, which would explain inflation and how the universe's structure came to be. Furthermore, under the framework of the holographic principle, let's analyze how gravitational waves behave. When large bodies accelerate, it causes ripples in spacetime called gravitational waves. A novel view on spacetime and gravity is provided by the holographic principle, which states that information on a system's gravitational waves may be recorded on its border. Another thing to think about is how the holographic principle may change how we approach quantum field theory. The most minute scales of particle and field activity are described by quantum field theory. The holographic principle states that the quantum fields within a given volume of space may be encoded on its border, implying a strong relationship between holography and quantum mechanics. Additionally, under the framework of the holographic principle, let's investigate how black hole mergers behave. Gravitational waves travel across space-time when two black holes combine. The holographic principle states that the border of the merging black hole may include information about the merger, which might explain how space-time and gravity work. By the end of this section, we will have looked at how the holographic principle affects string theory research. Instead of particles, according to string theory, the world is made up of little, vibrating strings. A fresh light on the underlying structure of reality and string theory is shed by the holographic principle, which states that information about strings in a volume of space may be recorded on its border. To better understand the holographic principle and its possible uses in theoretical physics, let's take a look at a few particular theoretical models and thought experiments. Many people are interested in the ADS-CFT correspondence, a theoretical model. Juan Maldacena put up this model in 1997, and it implies a strong relationship between string theory and quantum field theory. The ADS-CFT correspondence states that in higher dimensional anti-de Sitter (ADES) spacetimes, weakly interacting string theories may represent certain strongly interacting quantum field theories. By implying that a higher dimension string theory may completely encapsulate the information content of a lower dimensional quantum field theory, this duality gives a real illustration of the holographic principle at work. Within the framework of the holographic principle, the ERI-PR hypothesis is another theoretical model that has been investigated. Juan Maldacena and Leonard Susskind put out the ERI-PR hypothesis in 2013, which implies a strong relationship between wormholes and entanglement. This theory postulates that a wormhole, a hypothetical structure that would allow entangled particles to travel faster across spacetime, connects them. Further proof for reality's holographic character is provided by this notion. which implies that quantum entanglement of particles may be intricately tied to the geometry of spacetime. To further understand the holographic principle and its potential applications, thought experiments have been essential. The black hole firewall paradox is a well-known thought experiment that was put up in the early 2010s by many researchers, including Joseph Polchinski and Raphael Busoso. If this paradox is true, then quantum physics would be violated, and all data that fell into a black hole would be destroyed by a strong energy barrier that forms at the event horizon in the absence of any visible physical limit. This apparent contradiction calls attention to the need for alternative theoretical models and the difficulties of bringing the holographic principle into harmony with what is known about black hole physics at the moment. The thought experiment known as the Adsefti correspondence is another tool for investigating the holographic principle. Physicists contemplate a negative curvature hypothetical cosmos called anti-de Sitter, or ADS, space in this thought experiment. A quantum field theory residing on the edge of our world may explain its physics, as stated in the ADS-CFT correspondence. Here we see an example of how the holographic principle can be used to explain quantum field behavior and spacetime dynamics in a thought experiment involving black hole evaporation. In these experiments, physicists try to figure out what happens to the information inside a black hole as it slowly fades away from the universe as a result of Hawking radiation. Instead of being erased, the data is encoded on the event horizon of the black hole, as stated by the holographic principle. We learn more about black hole entropy and what happens to data when massive gravitational fields are present in this thinking exercise. Research into quantum entanglement as it pertains to black hole physics is another area that has provided insight into the holographic principle via the use of thought experiments. Physicists contemplate the actions of entangled particles in the vicinity of a black hole's event horizon in this hypothetical scenario. Insights into the quantum nature of gravity might be provided by the holographic principle, which states that the entanglement between these particles could be connected to the geometry of spacetime close to the black hole. To further investigate the ramifications of the holographic principle, thought experiments have been conducted using the operation of holographic displays. Overall, these theoretical models and thought experiments give valuable insights into the implications of the holographic principle and its potential applications in theoretical physics. In particular, they consider hypothetical screens that encode the information content of a volume of space. The physics of this volume can be fully described by the information stored on its boundary, according to the holographic principle. This thought experiment gives a concrete example of how the holographic principle can be applied to understand the dynamics of spacetime and the behavior of quantum fields. Physics researchers are interested in these concepts because they may lead them to new insights into the nature of reality and the relationship between quantum mechanics and gravity. Now let's look at experimental evidence and observational data that can shed light on the holographic principle and what it means for our knowledge of the cosmos. Cosmic microwave background radiation research is one field that might use observational data to back up the holographic principle. The cosmic microwave background, CMB, gives us a picture of the cosmos 380,000 years after it was born. It is the remnant of the Big Bang. The structure and development of the cosmos may be inferred from the analysis of minute changes in the CMB's temperature and polarization. Precise measurements of the cosmos have been made possible by observational data from investigations like the Planck satellite mission. Accurate measurements of the CMB have been obtained from experimental data, such as the Planck satellite mission, and may be used to evaluate theoretical predictions, especially those pertaining to the holographic principle. Looking at cosmic scale structure might also provide some observable evidence that is pertinent to the holographic principle. Through the process of charting the dispersion of cosmic scale structure, cosmologists may gain insight into the nature of spacetime and the distribution of energy and matter by creating large-scale maps of galaxy clusters, cosmic voids, and individual galaxies. Sloan Digital Sky Survey and Dark Energy Survey observational data have produced precise maps of the universe's large-scale structure, which may be used to evaluate theoretical theories, including holographic ones. The distribution of matter and energy is only one area that astronomers may research. Another is the behavior of astrophysical systems, which might provide indirect proof of holography. The holographic character of spacetime, for instance, may be better understood by investigating black holes and the accretion disks around them. Data collected by observatories like the Event Horizon Telescope, which just made history by capturing the first ever picture of a black hole's event horizon, could shed light on how these objects operate and the shape of spacetime close to their borders. In addition, at their frontiers, structure of spacetime may be revealed by studying gravitational waves. In addition, gravitational wave research could provide yet another way to put the holographic principle to the test. When large objects, such neutron stars or merging black holes, accelerate, it causes a ripple in spacetime called a gravitational wave. Astronomers may learn about the universe's dynamics and gravity's nature by monitoring gravitational wave features like polarization and frequency. The holographic spacetime and quantum field behavior may be better understood with the help of observational data from gravitational wave detectors like LIGO and Virgo. Additionally, holographic fingerprints may be searched for in the cosmic microwave background by astronomers. Photons scattered off free electrons in the early cosmos polarized the cosmic microwave background, CMB, and patterns of this polarization provide interesting details about the early universe. Anomalies that do not fit into current cosmological models, non-Gaussian characteristics, and other signs of holographic phenomena may be detected by analyzing the cosmic microwave background, CMB, polarization patterns. Furthermore, astronomical event observational data like cosmic rays, gamma-ray bursts, and supernovae might provide light on the holographic spacetime property. Spacetime's holographic properties may be better understood at this era. Astronomers may test holographic theory and learn more about how matter and energy behave in extreme situations by analyzing the characteristics of these high-energy occurrences. Cosmic inflation and cosmic microwave background research could also provide a new way to put the holographic principle to the test. The cosmic microwave background, CMB, provides important details about the cosmos immediately after inflation, a time of fast expansion that was likely to have happened in the early universe. To better comprehend the world and its possible ramifications for the holographic principle, let's take a look at a few cosmic discoveries that might point to a holographic reality. To start, let's think about the universe's big picture. Observations of the cosmos have shown a supercluster, galaxy cluster, or galactic web that stretches over billions of light years. This complex structure reveals information about the distribution of energy and matter in the cosmos and may give hints concerning spacetime's holographic properties. Our next stop will be at the Big Bang's aftermath, the cosmic microwave background, CMB. Cosmological studies of the cosmic microwave background, CMB, have yielded polarization and temperature maps, illuminating variations and subtle patterns that store important information about the early cosmos. These findings could provide light on where cosmic structure came from and how spacetime is holographic. Gravitational waves are ripples in spacetime that result from the acceleration of big objects. Let's investigate their behavior as well. Astronomers may learn more about the cosmos and gravity if they study gravitational waves emitted by cosmic events like neutron star collisions and black hole mergers. The holographic spacetime and quantum field properties may be better understood with the help of these findings. Consider gravitational waves with cosmic inflation, the study of which focuses on the early universe's fast expansion. Inflationary models' predictions for the cosmic microwave background, CMB, and cosmological measurements of these models may provide light on the holographic spacetime and cosmic structure's beginnings. In addition, we should look at how dark energy and dark matter are distributed across the cosmos. The characteristics of dark matter and dark energy, as well as their impact on the dynamics of the universe, have been better understood by cosmological studies of the cosmic microwave background, CMB, large-scale structure, and gravitational lensing. These findings could provide light on how matter and energy behave in the universe and on the holographic properties of spacetime. Furthermore, let's investigate how galaxy clusters act and what impact gravitational lensing has on them. The cosmological distribution of matter and energy, as well as the curvature of spacetime, may be better understood via studies of galaxy clusters and the ways in which they interact with light from faraway objects. These findings could possibly provide light on the geometry of spacetime and its holographic properties. Additionally, let's think about research into baryon acoustic oscillations, which are waves of sound that travel across the early cosmos. We may learn more about the cosmos's geometry and dark energy's properties from cosmological studies of BOO in quasar and galaxy distributions. Further information on the holographic properties of spacetime and the cosmic behavior of matter and energy may be gleaned from these findings. In addition, we will study the characteristics of the most powerful cosmic explosions, gamma-ray bursts. Additionally, we will study the characteristics of the universe's most powerful explosions, gamma-ray bursts. Insights into the universe's dynamics and the behavior of matter and energy in extreme conditions may be gained from cosmological investigations of gamma-ray bursts and the galaxies that host them. Further information on the structure of the universe and the holographic properties of spacetime may be gleaned from these findings. Also, how about we look into cosmic ray research? These are very energetic particles that are hurtling across space at almost the speed of light. Perhaps we can learn more about where cosmic rays come from and what mechanisms get them to such high energy if we look at them through the lens of cosmological data. The holographic spacetime and the mechanisms that accelerate them to such high energies may be better understood with the help of these discoveries. Further information on the holographic properties of spacetime and the cosmic behavior of matter and energy may be gleaned from these findings. Additionally, let's think about how supermassive black holes and galaxy cores behave. We may learn more about the galaxy's development and evolution over cosmic time if cosmologists study supermassive black holes and the gas and stars they interact with. Additionally, these findings could provide light on the dynamics of black hole horizons and the holographic properties of spacetime. We may learn more about the holographic nature of the cosmos from cosmological observations of galaxy clusters, cosmic rays, cosmic microwave background, gravitational waves, dark matter, dark energy, baryon acoustic oscillations, BAO, gamma-ray bursts, cosmic rays, and supermassive black holes. To test the holographic principle and investigate its possible consequences for our knowledge of the universe, astronomers compare theoretical predictions with empirical facts. Let's investigate the information retrieved from other places, such black holes in the cosmic microwave background, and see what we can learn about the holographic cosmos from it. To begin with, black holes are among the most mysterious celestial phenomena, but new observations have shed light on them like never before. For the first time, scientists have been able to directly visualize the silhouette of a black hole's event horizon, thanks to data from observatories like the Event Horizon Telescope. Important predictions of general relativity are confirmed by these findings, which also provide useful information for evaluating holographic principle-related theoretical models. Can provide useful information for evaluating holographic principle-related theoretical models. Information on the actions of neutron stars and black holes has also been uncovered by gravitational wave detectors such as LIGO and Virgo. Spacetime dynamics and the characteristics of these small objects may be studied by watching their mergers. These findings could provide light on how matter and energy behave near black holes and on the holographic properties of spacetime. Next, we have the cosmic microwave background, CMB, which has been extensively mapped in terms of temperature and polarization using data from investigations like the Planck satellite mission. These findings provide light on the early cosmos and how it has changed throughout cosmic history. Theoretical ideas pertaining to the holographic principle and spacetime structure may be tested by astronomers via the examination of CMB patterns and fluctuations. In addition, the distribution of galaxies, clusters, and superclusters has been substantially illuminated by data from investigations of cosmic structure at enormous scales. One way astronomers might learn about the universe's shape and energy distribution is by drawing a picture of the cosmic web, which is made up of filaments and gaps. The holographic spacetime and the behavior of matter and energy at the biggest scales may be revealed by these discoveries. Gravitational lensing data from galaxy cluster observations may also provide light on the cosmic distribution of dark energy and matter. Light bending around galaxy clusters allows scientists to deduce dark matter's impact on cosmic dynamics and map its distribution. Light bending around galaxy clusters allows scientists to deduce dark matter's impact on cosmic dynamics and map its distribution. These findings could provide light on how matter and energy behave in the universe and on the holographic properties of space-time. In addition, information on cosmic inflation and the early cosmos might provide light on spacetime's holographic properties. Astronomers may put theoretical concepts pertaining to the holographic principle and the formation of cosmic structure to the test by analyzing the characteristics and predictions of inflationary models for the cosmic microwave background, CMB. The early universe's dynamics and the geometry of spacetime may be better understood with the help of these findings. The behavior of matter and energy in extreme conditions may be better understood by analyzing data from gamma-ray bursts, supernova, and cosmic rays. Astronomers may get insight into the mechanisms that cause cosmic acceleration and influence the universe's history by analyzing the characteristics of these high-energy events. The mechanisms that cause cosmic acceleration and influence its development may be better understood with the help of these findings. These findings could provide light on how matter and energy behave on a cosmic scale, as well as the holographic properties of spacetime. Data from investigations of supermassive black holes and galaxy cores may also provide light on how galaxies have changed and grown throughout cosmic history. Black holes have a significant impact on the structure of the universe, and astronomers may learn more about this impact by studying their characteristics and how they interact with gas and stars. The holographic spacetime and the black hole boundary dynamics may be better understood with the help of these findings. Black hole, cosmic microwave background, large-scale structure, gravitational lensing, cosmic inflation, gamma-ray burst, supernova, cosmic ray, and supermassive black hole data may all add up to a useful picture of the universe's holographic nature. To test the holographic principle and investigate its possible consequences for our knowledge of the universe, astronomers compare theoretical predictions with empirical facts. To better understand where this intriguing area of study is right now, let's take a thorough look at all the current holographic principle-related experiments and studies. Principles that illuminate the present status of research in the intriguing domain of theoretical physics. A new mathematical framework for the holographic spacetime and its link to quantum mechanics and gravity is now under active development in theoretical physics. Efforts like this aim to learn more about holographic ideas and what they mean for comprehending how matter and energy behave on ranges from the microscopic to the cosmic. Additionally, experimental physicists are doing tests in the lab to verify the holographic principle's predictions by simulating the actions of black holes and other gravitational phenomena using analog systems. The basic principles regulating spacetime and gravity may be better understood, according to physicists, by investigating the dynamics of these model systems in controlled environments. In addition, state-of-the-art observatories and telescopes are being used by astronomers to analyze cosmic events that could reveal the cosmos' holographic properties. Data from missions like the Planck satellite mission and the Event Horizon telescope are helping to test theoretical theories of spacetime structure and the holographic principle. The holographic principle is also being investigated for possible links to other branches of physics, including quantum computing and quantum information theory. Physicists seek to understand the holographic cosmos and its basic structure by investigating the quantum information characteristics and the behavior of quantum systems. The holographic principle's predictions may also be tested in the lab by experimental physicists who are creating new technologies for that purpose. Researchers are studying the nature of information in highly regulated quantum systems utilizing methods like quantum teleportation and quantum entanglement. the holographic character of spacetime, the quantum mechanical nature of gravity, and the results of these experiments might give light on these topics. In addition, astronomers are extracting useful information from observational data acquired by telescopes and observatories by using sophisticated data processing tools. The holographic nature of the CMB and gravitational wave characteristics may be better understood if scientists examine galaxy distributions, CMB polarization, and gravitational wave characteristics. The holographic world and what it means for basic physics is a mystery that astronomers are hoping to solve by finding fresh evidence. The holographic principle is also being investigated for its uses in quantum gravity, string theory, and black hole physics, among other fields. To better understand the properties of matter and energy under harsh conditions, as well as the basic nature of spacetime, physicists are employing holographic methods to these fields of study. In addition, experimental physicists are trying to come up with novel ways to put the holographic principle's predictions to the test in controlled lab settings. Scientists are working on sophisticated detectors and sensors that can detect quantum fluctuations and gravitational waves, for instance, and their minute consequences. These innovations have the potential to provide light on the holographic world and the behavior of spacetime. On top of that, astronomers are putting holographic principle-related theoretical predictions to the test by studying the behavior of complicated astrophysical systems using numerical models and computer simulations. The holographic character of the universe and the fundamental rules regulating it may be better understood via the modeling of the birth and development of cosmic objects like galaxies and black holes. Because of its holographic quality, all things considered, the holographic principle is the subject of active research in many different fields, including as quantum mechanics, astronomy, experimental and theoretical physics, and many more. Physicists seek to understand the nature of reality and its mysteries by integrating theoretical studies with observational data, experimental methods, and the results of their research. Now, we'll talk about some of the problems and complaints people have voiced about the holographic principle and what it means for our knowledge of the cosmos. Questions about the holographic principle's theoretical foundations have been raised. Opponents of the holographic principle in the field of physics contend that it is based on unproven speculation rather than solid theory. This critique highlights the need for more research into the theory and testing of the holographic principle in order to prove its validity. In addition, a number of academics have voiced reservations over the holographic principle's potential real-world consequences for our knowledge of the cosmos and physics. Although general relativity and quantum mechanics have been very effective in explaining the behavior of matter and energy in the universe, critics of both theories contend that the holographic principle may cause them to undergo significant modifications. How the universe's matter and energy behave. This criticism stresses how important it is to think about how the holographic principle may change current ideas and results from experiments. On top of that, there are scientists who doubt it will be possible to conduct experiments to verify the holographic principle's predictions. Some think that the holographic principle is flawed because it uses assumptions that are hard to evaluate with the tools we have at our disposal in terms of both experimental methods and observational data. This difficulty highlights the need for novel, experimental, and observational approaches to thoroughly evaluate the holographic principle's predictions. Also, the holographic principle has some scientists worried about how it may change the way we think about black holes and other astronomical events. The holographic principle has its detractors who fear it may force us to rethink gravity and the universe as we know it by radically altering our perceptions of black hole behavior and the structure of spacetime close to their horizons. To further understand the holographic principle's consequences for black hole physics, more theoretical and experimental investigations are required, as this criticism shows. Some physicists have also raised doubts about the holographic principle's compatibility with other cornerstones of physics, such information conservation and the second law of thermodynamics. Some think the holographic principle makes us rethink our current knowledge of these principles and calls into question our assumptions about information theory and thermodynamics. To overcome this obstacle and answer the basic concerns that the holographic principle raises, multidisciplinary study is essential. Also, the holographic concept has some experts worried about how it may change our view of space and time. Some think the holographic principle might lead to a major rethinking of space-time, which would have far-reaching consequences for how we see the cosmos. In order to clarify what the holographic principle means for space-time, this criticism emphasizes the need for more theoretical and experimental studies. The applicability of the holographic principle to the whole universe or to certain areas or scales has also been a matter of debate among physicists. The holographic principle has its detractors who contend that it may not be applicable to all cosmological sizes and regimes, and might only hold water under certain circumstances. This difficulty highlights the need of thoroughly evaluating how the holographic principle may be applied to various physical systems and sizes. In addition, there are academics who are worried about what the holographic principle may mean for how we conceptualize reality. The holographic principle has its detractors, who fear it might force a fundamental rethinking of how we conceptualize ourselves in connection to the cosmos and what it means to be aware and subjective. The philosophical ramifications of the holographic concept need more multidisciplinary study, as this criticism shows. It has also been debated among physicists whether the holographic principle is compatible with other cornerstones of physics like locality and causality. The holographic principle, according to its detractors, might force us to rethink our assumptions about location and causation, as well as our current grasp of these ideas. Given this difficulty, it is clear that further theoretical and experimental studies are required to clarify what the holographic principle means for our comprehension of reality's essence. Ultimately, it will need the combined efforts of physicists, astronomers, mathematicians, and philosophers to resolve the objections and difficulties brought up by the holographic principle. Researchers may further our knowledge of the holographic world, its implications for basic physics, and reality itself by giving serious consideration to these criticisms and obstacles. To answer the questions put forward about the holographic universe theory's validity and its consequences for our knowledge of the world, let's examine some of the main objections and constraints leveled against it. Consequences on how we see the world. The dependence of the holographic universe hypothesis on unproven assumptions and speculative concepts is a key point of criticism against it. A number of people think the holographic principle is just a bunch of wild speculation and not founded on any real science at all. To prove the holographic universe idea is correct, further theoretical work and experiments are required, as this critique shows. Also, holographic universe theory has some academics worried about what it may mean for our knowledge of basic physics and reality in the actual world. Some think it may cause major changes to well-established theories like quantum physics and general relativity, which have been proven correct in practice. Those who are against the theory point out that it might cause major changes to well-established explanations for how the universe's matter and energy behave, such quantum mechanics and general relativity. This criticism stresses how important it is to think about how the holographic universe hypothesis may change current ideas and explain experimental results. Some have also raised concerns about how the holographic world idea squares with other cornerstones of physics, such the second rule of thermodynamics and the conservation of information. Some have voiced concerns that this theory might force us to reevaluate our current theories of information and thermodynamics and call into question our commonly held beliefs about these concepts. In light of this difficulty, it is clear that multidisciplinary studies are required to resolve the basic concerns brought up by the holographic universe hypothesis. Concerns over the holographic universe theory's consequences for our knowledge of black holes and other astronomical events have also been voiced by several scientists. A number of people are worried that this idea would cause a major shift in how we think about black holes and the structure of space-time close to their horizons, which would have far-reaching consequences for how we perceive gravity and the universe in general. This criticism emphasizes the need for more theoretical and experimental investigations to elucidate the consequences of the holographic universe hypothesis on black hole physics. Furthermore, skeptics have raised the issue of whether the holographic universe hypothesis is applicable to all cosmological scales, or is it conditionally or regionally restricted. Some think the hypothesis doesn't hold water at all sizes of the universe, and that it may only work in some regimes or under specific conditions. The relevance of the holographic universe hypothesis to various physical systems and scales has to be thoroughly examined in light of this problem. Also, the holographic universe idea has some scientists worried about what it may mean for how we perceive space-time and the universe's fabric. Opponents of the idea contend that it may lead to a significant rethinking of time and space, which would have far-reaching consequences for how we perceive reality's underlying structure. The need for more theoretical and experimental studies to clarify the consequences of the holographic universe hypothesis on spacetime's nature is emphasized by this criticism. A number of skeptics have also raised concerns about the compatibility of the holographic universe idea with disciplines like psychology and biology. Skeptics contend that the theory won't shed much light on the nature of consciousness or subjective experience, and may only be applicable to physics and related disciplines. The philosophical ramifications of the holographic universe idea necessitate multidisciplinary study to tackle this difficulty. Furthermore, a number of physicists have voiced reservations about the possible consequences of the holographic world hypothesis on our comprehension of locality and causation. Some have voiced concerns that this theory might force us to reevaluate our current notions of locality and causation, and call into question our commonly held assumptions about these principles. To overcome this obstacle, further theoretical and experimental research is required to clarify what the holographic universe hypothesis means for our knowledge of reality's essence. Ultimately, it will take the combined efforts of physicists, astronomers, mathematicians, and philosophers to resolve the most significant objections and shortcomings of the holographic universe idea. The holographic cosmos, its implications for basic physics, and the nature of reality may be better understood if researchers give due consideration to these objections and limits. In light of the holographic universe theory's detractors, let's take a look at several competing ideas that aim to explain the world from a different angle. The multiverse hypothesis is one attractive alternative explanation. It states that there may be more than one world, and that each of these universes has its own unique set of physical constants and rules. Many cosmologists still don't understand where cosmic inflation came from, or how the universe's basic constants were fine-tuned. Some think the multiverse theory may provide some answers to these and other mysteries. On top of that, there are scientists who have put out the simulation theory, which states that our cosmos is really an artificial simulation made by a technologically superior race. Those who believe in the simulation hypothesis say it can explain why the universe is the way it is, including why physical constants seem to be fine-tuned, and why there are mathematical rules that control how matter and energy behave. In addition, the concept of emergent spacetime has been investigated by scholars. This theory proposes that gravity and spacetime could originate from less geometrical, more basic principles. Those who believe in emergent spacetime say it sheds light on the cosmos and gravity in a different way, questioning the long-held belief in spacetime as an immutable prior foundation. On top of that, there are scientists who have put forward the concept of non-local hidden variables, which implies that underlying factors control quantum particle behavior and are not limited by causality or locality. A more comprehensive explanation of quantum physics, according to proponents of non-local hidden variables, might provide light on the nature of reality outside of the classical and quantum domains. Additionally, scientists have investigated quantum gravity, an idea that aims to integrate general relativity and quantum mechanics into a unified theory. Those who believe in quantum gravity say it sheds light on how energy and matter behave at the most microscopic scales and on the very essence of spacetime. In addition, a number of scientists have put forward the theory of a cyclic universe, which holds that there is an endless succession of cosmic cycles in which the Big Bang and the Great Crunch are both initiated and terminated, should conclude with a satisfying crunch. Those who believe in the cyclic universe theory say it explains the cosmic microwave background patterns and how the cosmos came to be in a more natural way. Furthermore, holographic duality has been investigated by researchers. This theory proposes that certain physical systems may be adequately explained by theories with varying dimensionalities. Some think holographic duality may provide light on the interplay between quantum physics and gravity, as well as the properties of space-time. In addition, there is a school of thought among physicists that places the early universe in a pre-geometric period when space-time may have developed from less formal, non-geometric concepts. Those who believe in the pre-geometric universe theory say it sheds light on where space-time came from and how the world is structured. In addition, scientists have examined quantum cosmology, an emerging field that aims to investigate the cosmos through the lens of quantum mechanics. Those who believe in quantum cosmology say it challenges long-held ideas about the structure and history of the cosmos and provides a fresh viewpoint on the universe's beginnings and development. Overall, it is instructive to examine competing ideas with the holographic world hypothesis because it provides a window into other points of view and ways of looking at the essence of reality. Researchers may advance our grasp of the cosmos and its fundamental principles by delving into these competing hypotheses, which in turn expand our horizons of scientific discovery. The holographic universe idea poses some serious philosophical concerns about our position in the world, the nature of reality, and consciousness. Let's take a look at some of those questions now. Holographic universe theory poses a serious challenge to our long-held beliefs about the nature of space, time, and reality itself, which has far-reaching philosophical consequences. Space and time, according to proponents of the holographic universe theory, are not the primary components of reality, but rather emergent characteristics of a more basic substrate. This theory also begs the question, what is the nature of consciousness and subjective experience in a holographic universe, and how does this relate to the physical world? There are philosophical schools of thought that hold that awareness may be an essential component of reality, bound up with the very fabric of the cosmos. We may learn a lot about determinism and causation from the holographic world idea too. Does a holographic world imply that there are hidden patterns in reality that dictate how events transpire and that causality is an illusion? We are prompted to delve further into the nature of free will and agency by these concerns, which also pose challenges to our conventional ideas of cause and consequence. Concerns about the boundaries of human understanding and the essence of reality are further prompted by the holographic universe idea. What prospect do we have of ever comprehending the nature of the cosmos in its entirety if it is holographic? Holographic universe hypothesis, according to some philosophers, shows how limited our knowledge of the world is and contradicts our narcissistic ideas about what we know. In addition, our knowledge of the connection between consciousness and physical reality may be impacted by the holographic world idea. Does the fact that awareness is central to the formation of physical reality follow from the holographic principle of the universe? A number of thinkers have proposed the idea that awareness is fundamental to the cosmos and its workings, which would have far-reaching consequences for how we conceptualize reality. The holographic universe idea also begs the issue of whether or not there are dimensions beyond our perception and the very essence of reality itself. Other dimensions beyond the ones we can see must exist if our reality is holographic. Does the possibility of a holographic cosmos mean that there are realities beyond our comprehension in higher dimensions? These inquiries provide fresh opportunities for philosophical debate by testing our accepted views of reality. Furthermore, our comprehension of the observer-observed dynamic is affected by the holographic world idea. Is the observer essentially responsible for molding reality if the cosmos is essentially holographic? It has far-reaching consequences for how we comprehend the essence of perception and experience, according to some philosophers, who contend that consciousness could be intrinsic to reality. In addition, the holographic universe hypothesis makes one wonder how time works, and if it is even possible to travel across time. Does the nature of the cosmos as a hologram imply that the past, present, and future are all equally real, and that time itself is an illusion? These inquiries raise fresh philosophical concerns and cast doubt on our commonly held ideas about time. Additionally, our comprehension of the essence of being and purpose in life might be impacted by the holographic universe idea. What does it mean for the meaning and purpose of human life if the cosmos is essentially holographic? There are philosophers who think that comprehending the nature of reality hinges on the question of consciousness and whether it holds the key to unraveling the secrets of the cosmos. In sum, delving into the holographic universe theory's philosophical ramifications paves the way for fresh avenues of investigation and reflection, calling into question our long-held assumptions about the world and offering up exciting new avenues for discovering the meaning of life. We can learn more about the universe and our role in it if we try to answer these big questions. Let's dive into the deep mysteries and ramifications that the idea of a holographic cosmos has for our comprehension of existence and reality as we explore the philosophical concerns it raises, deep enigmas, and consequences it offers for our comprehension of life and reality. First of all, a holographic cosmos would make us rethink our basic assumptions about the world and the meaning of life. How does the possibility of a holographic world affect our understanding of reality and its fundamental structure? We are compelled to ponder the very essence of being and the laws that govern the cosmos in response to these inquiries. What does the idea of a holographic universe mean for the connection between mental processes and physical reality? If our consciousness is so influential, then what does this say about our own nature and our position in the universe? In light of these questions, we are compelled to reevaluate the conventional dualism perspective on mental and physical processes, and to investigate the ways in which our consciousness is interwoven with the physical universe. More than that, however, a holographic cosmos makes us reevaluate our views on time, space, and perception. What does the holographic nature of the cosmos mean for the interaction between observer and observed, the nature of space and time, and everything else? These inquiries make us think about how we see the world and how far we may go in our quest to unravel the secrets of space and time. Furthermore, determinism and causality are brought to light by the idea of a holographic cosmos. Concerns about the fundamental aspects of determinism and causation. Do events transpire in accordance with planned patterns embedded in reality's fabric if the cosmos is holographic? These inquiries force us to reconsider our conceptions of free will and agency within the framework of a holographic universe, and to reevaluate our theories of cause and effect. The concept of a holographic world also makes us think about what it may mean for our perception of reality outside of space and time. Does the idea that the cosmos is essentially holographic rule out the possibility of realities beyond our present perspective, or perhaps of parallel universes? We ponder the nature of life beyond our daily experience and investigate the possibility of a multiverse or higher dimensional existence as a result of these inquiries. Additionally, time travel and the nature of time itself are brought up in discussions around the idea of a holographic reality. Does time travel ensure that everything from the past to the future is just as genuine as everything else in a holographic universe? Signify that all three eras are equally real? In the context of a holographic universe, these concerns make us doubt our traditional understanding of time and make us wonder about the secrets of our own temporal existence. Furthermore, the concept of a holographic cosmos forces us to reevaluate how we conceptualize the role of the observer. What does the nature of perception and experience suggest if awareness is fundamentally responsible for shaping reality? The answers to these questions invite us to ponder the subjective reality in a holographic universe and to investigate the relationship between the physical world and consciousness. Furthermore, holographic universe theory makes one wonder about the boundaries of reality and the scope of human understanding. The possibility that our cosmos is a holographic illusion prompts contemplation of the boundaries of reality and the scope of human understanding. How can we possibly comprehend the nature of the cosmos to its fullest extent if it is essentially holographic? These inquiries push us to consider the mysteries of the universe that are beyond our grasp and to face the limits of human knowledge. The concept of a holographic world also makes us think about what it may entail for our view of the cosmos and our place in it. What does it mean for the meaning and purpose of human life if the cosmos is essentially holographic? In light of these inquiries, we ponder the riddles of life and the desire for significance within the framework of a holographic universe. Furthermore, the idea of a holographic cosmos prompts inquiries on the essence of existence beyond the material world. Does the idea that the cosmos is essentially holographic rule out the possibility of realities beyond our present perspective, or perhaps of parallel universes? These questions make us wonder whether there are worlds beyond our present awareness, or if there are parallel universes. We ponder the nature of life beyond our daily experience and investigate the possibility of a multiverse or higher dimensional existence as a result of these inquiries. In addition, the concept of a holographic reality forces us to reevaluate how we conceptualize the role of the observer. What does the nature of perception and experience suggest if awareness is fundamentally responsible for shaping reality? The answers to these questions invite us to ponder the subjective reality in a holographic universe and to investigate the relationship between the physical world and consciousness. What about the subjective reality in such a holographic universe? That is an intriguing topic that arises from the idea of a holographic cosmos. Additionally, time travel and the nature of time itself are brought up in discussions around the idea of a holographic reality. Does time travel ensure that everything from the past to the future is just as genuine as everything else in a holographic universe? In the context of a holographic universe, these concerns make us doubt our traditional understanding of time and make us wonder about the secrets of our own temporal existence. Furthermore, the concept of a holographic cosmos forces us to reevaluate how we conceptualize the role of the observer. What does the nature of perception and experience suggest if awareness is fundamentally responsible for shaping reality? The answers to these questions invite us to ponder the subjective reality in a holographic universe and to investigate the relationship between the physical world and consciousness. Furthermore, holographic universe theory makes one wonder about the boundaries of reality and the scope of human understanding. How can we possibly comprehend the nature of the cosmos to its fullest extent if it is essentially holographic? These inquiries push us to consider the mysteries of the universe that are beyond our grasp and to face the limits of human knowledge. The concept of a holographic world also makes us think about what it may entail for our view of the cosmos and our place in it. What does it mean for the meaning and purpose of human life if the cosmos is essentially holographic? In light of these inquiries, we ponder the riddles of life and the desire for significance within the framework of a holographic universe. In sum, investigating the theoretical concerns that a holographic universe poses. Overarchingly, delving into the philosophical inquiries brought up by the idea of a holographic cosmos takes us on a voyage of introspection and revelation, testing our presumptions about reality and revealing new avenues of investigation into the essence of being at large. The idea of a holographic cosmos has far-reaching implications for how we conceptualize and make sense of the world around us. The first impact that a holographic universe theory has on how we conceptualize the world, our own minds, and our senses. To begin with, the holographic universe theory casts doubt on our long-held beliefs about the nature of reality by implying that everything in it is more malleable and interdependent than we had previously imagined. The idea that the universe is essentially holographic would mean that everything in it is interconnected, and that reality is not static but rather ever-changing. Furthermore, our comprehension of consciousness is greatly affected by the idea of a holographic cosmos. If awareness is central to the construction of reality, then our individual perceptions may influence the material universe. This begs the question, what is the nature of subjective reality? And casts doubt on the conventional wisdom that awareness is only an observer. In addition, our current understanding of human vision is called into question by the concept of a holographic reality. If the cosmos is essentially holographic, then our senses and minds may be the only filters through which we see the world. This makes us reevaluate how we see and think, and it casts doubt on the idea of an objective world. The idea of a holographic cosmos also calls into question the way we normally think about time and space. The possibility of non-local interactions and instantaneous communication over great distances arises if reality is holographic, which suggests that space and time may be more pliable and flexible than previously believed. In addition, our conception of reality might be affected by the holographic universe theory. Holography raises the intriguing possibility that our conceptions of the borders between ourselves and others, as well as between observer and observed, are more fluid and interdependent than we had thought. Because of this, we are forced to reevaluate our connection to the universe and our perception of ourselves as distinct. As an added bonus, holographic world theory makes one wonder what determinism and causality really are. If our perception of reality is distorted, then there may be more than meets the eye when it comes to the relationships between events. Because of this, we need to reevaluate the concept of causation and the universe's predictability. Furthermore, our comprehension of the interdependence of all entities is affected by the concept of a holographic cosmos. If the universe is really holographic, then all matter is entangled in an immense web of connections that goes beyond the limitations of space and time. The idea of a holographic cosmos also calls into question our fundamental assumptions about the world. If reality is essentially holographic, then our current understanding of space, time, and matter could not be sufficient to encompass the intricacy of the universe. We are forced to reevaluate our core beliefs on the essence of reality and the boundaries of human understanding in light of this. Our current notion of what it is to be aware is also affected by the possibility of a holographic cosmos. The holographic theory of reality raises the intriguing possibility that consciousness is an inherent part of the universe rather than just an effect of mental processes. Because of this, we need to reevaluate what awareness is and how the mind relates to matter. Furthermore, a holographic cosmos poses questions about how we perceive the world. If the cosmos is essentially holographic, then our conventional ideas of space, time, and matter may fall short of completely describing its complexity. A reevaluation of our perceptions of reality may be warranted in light of the fact that our subjective experiences and thoughts influence our perceptions of reality to a greater extent than our senses alone. We are forced to reevaluate our core beliefs on the essence of reality and the boundaries of human understanding in light of this. The idea of a holographic cosmos also calls into question what awareness is all about. Comprehension of how awareness works. The holographic theory of reality raises the intriguing possibility that awareness is an essential component of the universe rather than just an effect of mental processes. This forces us to reevaluate what consciousness is and how we conceptualize the link between mind and matter. Another problem with holographic world theory is that it calls into question everything we thought we knew about how our eyes work. If our vision of the world is influenced by more than simply our senses, our awareness and personal experiences may also play a role, according to the holographic theory. This makes us reevaluate how our minds shape our perceptions of the world and the nature of perception itself. Furthermore, our perception of reality is affected by the idea of a holographic cosmos. If reality is essentially holographic, then our current understanding of space, time, and matter could not be sufficient to encompass the intricacy of the universe. We are forced to reevaluate our core beliefs on the essence of reality and the boundaries of human understanding in light of this. The concept of a holographic cosmos also calls into question what consciousness is all about. The holographic theory of reality raises the intriguing possibility that awareness is an essential component of the universe rather than just an effect of mental processes. Because of this, we need to reevaluate what awareness is and how the mind relates to matter. Furthermore, a holographic cosmos poses questions about how we perceive the world. The idea that our awareness and subjective experiences, in addition to our senses, contribute to the formation of our view of the world raises the possibility that our reality is holographic. This makes us reevaluate how our minds shape our perceptions of the world and the nature of perception itself. In general, as we delve into the philosophical inquiries brought up by the idea of a holographic cosmos, we are forced to reevaluate our basic beliefs about what is real, what is awareness, and how we see the world. This, in turn, opens up new avenues for studying and pondering the essence of being. So let's take a look at how holography has impacted different technologies. how it has changed whole sectors, and how it has opened up new opportunities in areas as diverse as entertainment and science. To begin, holography is a game changer in healthcare, especially in the areas of imaging and diagnostics. Holographic imaging enables the production of very accurate three-dimensional representations of anatomical and pathological features of the human body, including organs and tissues. In addition, holography has revolutionized authentication and security by making extensive use of holographic technology in the manufacturing of safe goods and documents, including credit cards, passports, and currencies. Adding holographic elements to papers makes them even more secure, making it harder for counterfeiters to copy or alter the documents. Visual effects and other forms of immersive entertainment have also been profoundly affected by holography's revolutionary impact on the industry. Holographic projections and displays make it possible to create very realistic three-dimensional visuals and animations, which greatly enhances the immersion and realism that audiences experience in movies, theme parks, and live performances. Furthermore, holography has been an important tool for scientists to better understand and study complicated processes in domains like engineering, chemistry, and physics. Progress in fields like materials, science, nanotechnology, and biophysics has resulted from the development of holographic methods that enable the exact measurement and manipulation of subatomic structures and particles. The exploration of holographic methods for applications like holographic telepresence and three-dimensional video conferencing further demonstrates how holography has impacted the world of telecommunications. More immersive and engaging communication experiences may soon be within reach with the help of holographic displays and communication systems, which might eliminate geographical barriers and open the door to novel kinds of cooperation and engagement. Users, paving the way for novel ways of interacting and collaborating. Artists and designers have also been influenced by holography, which has enabled them to create interactive and inventive works of art and installations. Images and objects in holographic art seem to float in space and transform according on the viewer's viewpoint, providing a one-of-a-kind visual experience. Holographic displays and simulations have also revolutionized training and education by providing students and professionals with fully immersive learning environments. By providing a three-dimensional representation of abstract ideas and occurrences, holographic instructional materials make studying more dynamic and interesting for pupils. The development of holographic displays and gadgets for use in AR and VR is another way in which holography has impacted consumer electronics. By erasing boundaries between the virtual and real worlds, holographic augmented and virtual reality systems provide consumers with a more lifelike and immersive experience. In addition, holography has had an influence on the manufacturing and prototyping industries via the use of holographic methods in quality control and quick prototyping. In order to enhance the quality and efficiency of produced components, holographic imaging and measuring devices provide accurate inspection and analysis. The employment of holographic methods in astronomy has allowed for the visualization and study of complex formations like galaxies, nebulae, and black holes, which has shed light on the nature of the universe. In addition, holography has revolutionized marketing and advertising by allowing for the creation of eye-catching and engaging brand experiences via the use of holographic displays and projections, as well as engaging brand interactions. Holographic advertising provides a fresh and exciting medium for marketers to display their wares, drawing in customers and raising awareness of their brands. In addition, holography has had an effect on the preservation of cultural heritage, since holographic methods have allowed for the creation of three-dimensional reproductions of historical monuments and objects. To ensure that cultural heritage locations and objects may be studied and enjoyed by future generations, holographic imaging devices enable for their preservation and recording. The military and defense sector has also been impacted by holography, with holographic methods finding usage in tasks like target acquisition and reconnaissance. Holographic imaging is finding usage in fields including target acquisition and reconnaissance. With the use of holographic imaging equipment, soldiers may see the landscape and their enemies' locations in 3 dimensions, which aids in planning and execution of missions. Additionally, holography has revolutionized urban planning and design by allowing for the creation of more lifelike and immersive models of buildings and cityscapes via the use of holographic visualization methods. Designers and planners may use holographic architectural models to experiment with various layouts and see how their projects might affect the surroundings. In addition, holography has made waves in the gaming industry, as simulated holographic displays have allowed for the creation of more participatory and immersive video games. Thanks to holographic gaming systems' three-dimensional visuals and surroundings that react to player interaction in real time, gamers may enjoy a more realistic and immersive gaming experience. Holographic displays and simulations have also had an impact on the leisure and sports industry, particularly in the areas of training and performance evaluation. An athlete's technique and performance may be enhanced with the use of holographic training systems, which provide three-dimensional visualization and analysis of the athlete's motions. Additionally, holography has revolutionized urban planning and design by allowing for the creation of more lifelike and immersive models of buildings and cityscapes via the use of holographic visualization methods. Designers and planners may use holographic architectural models to experiment with various layouts and see how their projects might affect the surroundings. In addition, holography has revolutionized transportation by enhancing vehicle design and driver training via the use of holographic displays and simulations. Engineers and designers may enhance vehicle safety and performance by using holographic visualization systems to test and evaluate various configurations in 3 dimensions. Furthermore, holography has had an impact on the retail and fashion industries via the use of holographic projections and displays to develop new forms of interactive retail therapy. Sales are up because holographic displays let consumers try on and personalize things in 3 dimensions, which is a huge time saver for shoppers. The advent of holography has opened up new avenues of inquiry and innovation in many sectors of society, from the arts and entertainment to science and medicine. Even more groundbreaking developments and practical uses will emerge in the future of holographic methods. Let us now investigate how holographic principles might motivate future technical developments that usher in game-changing advancements in a wide range of industries. To begin with, cutting-edge medical imaging technologies may be sparked by holographic principles, which might lead to the production of very detailed, 3-dimensional representations of the human anatomy. Clinicians may get new understanding of diseased states and anatomical structures with the use of these holographic imaging devices, which have the potential to completely alter medical diagnosis. Furthermore, holographic principles may motivate the invention of new authentication and security systems, which in turn might lead to the production of very safe and tamper-proof goods and documents. To increase security and avoid counterfeiting, holographic authentication capabilities might be implemented into many applications, such as consumer items, currencies, and passports/identity cards, increasing safety and decreasing the likelihood of forgery. Also, next-gen display technologies could be influenced by holographic principles, which might lead to the production of more lifelike and immersive visual experiences. The potential for holographic displays to allow users to engage with 3-dimensional visuals and animations has the potential to transform the ways we play games, communicate, and enjoy entertainment by erasing boundaries between the virtual and real worlds. Furthermore, holographic principles may motivate the research and development of cutting-edge materials and production methods, resulting in the introduction of new optically exceptional goods. A plethora of new technological and aesthetic possibilities are presented by the holographic materials, which have the potential to revolutionize fields as diverse as adaptive camouflage, visual computing, data storage, and encryption. In addition, cutting-edge telecommunications innovations might be sparked by holographic principles, opening the door to holographic telepresence and 3D video conferencing. By enabling users to converse and work together in fully immersive virtual worlds, these holographic communication technologies have the potential to completely transform distant collaboration and engagement. In addition, holographic principles might pave the way for more sophisticated automation and robotics, allowing for the eventual production of machines and robots with superior perceptual and manipulative capacities. Robots equipped with holographic sensors and control systems have the potential to revolutionize industries including manufacturing, healthcare, and exploration by enabling them to navigate and interact with their surroundings in 3 dimensions. Furthermore, cutting-edge navigation and mapping technologies might be sparked by holographic principles, paving the way for the production of exceptionally precise 3-dimensional representations of both interior and outdoor settings. With the accurate, real-time information they provide, these holographic mapping systems have the potential to completely alter the way people navigate and pinpoint their exact location. Holographic principles may also motivate the creation of cutting-edge visualization and imaging tools for use in scientific inquiry. Researchers in astronomy, physics, and biology can benefit from holographic imaging systems by studying complicated events. This might lead to new understandings of the cosmos and life's fundamental components. Also, cutting-edge VR and AR technologies may take a page out of holographic principles when designing engaging and immersive digital experiences. With holographic virtual reality, VR, and augmented reality, AR systems, users may see digital items in 3 dimensions and explore virtual worlds, potentially transforming entertainment, education, training, and treatment. More sophisticated sensing and monitoring tools with potential industrial and environmental uses might be spawned from holographic principles. Holographic sensors have the potential to enhance safety, efficiency, and sustainability in a variety of applications, including the detection and analysis of changes in water and air quality, the monitoring of structure integrity, and the optimization of industrial processes. More efficient and long-lasting energy systems might be possible with the help of new technologies inspired by holographic principles that capture and store energy. Holographic batteries might store and release energy more efficiently and for longer periods of time, while holographic solar panels could concentrate sunlight more effectively. In addition, holographic principles have the potential to spark innovation in security and surveillance technology, leading to the production of more precise and less invasive tracking systems. The use of holographic cameras and sensors might improve safety in public areas, transportation networks, and essential infrastructure by detecting and tracking people and objects in 3 dimensions. Another potential benefit of holographic principles is that they might pave the way for more sophisticated automation and robotics, eventually leading to machines and robots with enhanced perceptual and manipulative capacities. Robots equipped with holographic sensors and control systems have the potential to revolutionize industries including manufacturing, healthcare, and exploration by enabling them to navigate and interact with their surroundings in 3 dimensions. In addition, cutting-edge navigation and mapping technologies might be spawned by holographic principles, opening the door to the production of very precise 3-dimensional maps of both indoor and outdoor settings. With the accurate, real-time information they provide, these holographic mapping systems have the potential to completely alter the way people navigate and pinpoint their exact location. In addition, holographic principles have the potential to motivate the creation of cutting-edge visualization and imaging tools for use in scientific inquiry. Researchers in astronomy, physics, and biology can benefit from holographic imaging systems by studying complicated events. This might lead to new understandings of the cosmos and life's fundamental components. Furthermore, cutting-edge VR and AR technologies may be influenced by holographic principles, opening the door to the production of interactive and immersive digital experiences. With holographic virtual reality, VR, and augmented reality, AR systems, users may see digital items in 3 dimensions and explore virtual worlds, potentially transforming entertainment, education, training, and treatment. There is a great deal of room for invention and discovery in many other domains, thanks to the holographic principles, which might lead to a great deal of technological progress. We may anticipate other revolutionary developments that will impact the trajectory of technology and culture as scientists and engineers delve further into the potential of holography. Discover the boundless potential of holography by delving into its many uses in computing, data storage, and VR. To begin, holography presents promising new avenues for computer science that may dramatically alter the ways in which data is processed and displayed. One potential use of holographic computing is the development of immersive user interfaces that provide users a three-dimensional experience while interacting with digital content. New methods of communicating with digital devices and computers, as well as simplification of formerly laborious processes, may be possible with the help of these holographic interfaces. Additionally, holography provides hope for data storage by presenting the prospect of three-dimensional storage medium with a high density. When compared to more conventional storage methods, holographic data storage devices have the potential to store far more data in a much smaller footprint. Unlocking new options for storing and accessing information, these technologies have the potential to revolutionize data archiving, retrieval, and administration. In addition, holography might revolutionize virtual reality, VR, by paving the way for the development of more lifelike and immersive simulations. With holographic virtual reality systems, users might have a more realistic and captivating experience, complete with interactive features that react to their input in real-time and three-dimensional images. In addition to enhancing the development of augmented reality, AR technologies, which blend digital information with the physical world, holographic AR systems could overlay virtual objects and information onto the user's view of the real world, improving situational awareness, productivity, and creativity. These systems have the potential to revolutionize entertainment, gaming, education, and training by giving users new ways to explore and interact with digital worlds. Potential areas of usage for these systems include navigation, manufacturing, healthcare, and entertainment, where they might aid users with everyday tasks and provide useful insights. In addition, holography allows researchers to examine complicated data sets in 3 dimensions, which opens up intriguing possibilities for scientific visualization. In order to better understand the interconnections and patterns in data, scientists may soon be able to use holographic viewing technologies to do real-time analyses and manipulations. Astronomy, physics, biology, and engineering are just a few of the potential domains that may benefit from these systems, which could provide scientists with potent new resources for discovery and advancement. In addition, holography has the potential to completely transform telepresence by opening the door to more lifelike and immersive distant communication. Holographic telepresence systems have the potential to connect users with remote surroundings and people in a way that seems like they're right there, opening up new possibilities for collaboration and engagement over great distances. Businesses, schools, hospitals, and even the entertainment industry might all benefit from these technologies, which would revolutionize human interaction. Furthermore, holography has the potential to advance holographic displays, which would pave the way for the production of realistic and interactive visual content. 3D pictures that seem to float in space and change viewpoint as the viewer moves might provide a more immersive and interesting viewing experience on holographic displays. These screens might revolutionize the way people engage with digital material in industries including advertising, education, design, and entertainment. The development of more lifelike and interactive holographic representations is another area that holography has the potential to transform. Holographic projection systems have the potential to create breathtaking illusions and visual effects by projecting 3-dimensional pictures onto real-world surfaces or even into empty space. The entertainment, advertising, art, and architectural industries are just a few potential places where these technologies may find use, revolutionizing our perception and interaction with the world around us. In addition, holography has the potential to advance holographic microscopy, which would allow for 3-dimensional high-resolution imaging of biological material. Holographic microscopy technologies have the potential to revolutionize the field of biology and medicine by revealing hitherto unseen details about the inner workings of cells and tissues. Biomedical research, diagnostics, and medication creation are a few areas that can benefit from these systems, which might enhance healthcare and people's quality of life. Furthermore, holography has the potential to completely transform holographic printing, opening the door to the fabrication of very precise and detailed 3-dimensional things. Holographic printing technology has the potential to revolutionize the design, production, and prototype processes by creating lifelike, tangible items from digital models. These technologies have the potential to revolutionize several industries, including product design, architecture, fashion, and art, by allowing creators to realize their concepts with breathtaking accuracy. In addition, holography has the potential to improve holographic sensor technology, which would allow for very sensitive and accurate three-dimensional measurements. There are several potential uses for holographic sensors, which might detect and evaluate chemical and physical aspects of things and situations. These sensors have the potential to improve data collecting and processing in areas including environmental monitoring, healthcare, industrial process control, and military. Also, holographic encryption has the potential to completely change the game by making data storage and transmission impenetrable and safe. Information might be encoded into three-dimensional holograms using a holographic encryption method, making it impossible for unauthorized users to intercept or decode. Cybersecurity, telecommunications, and financial transactions are just a few areas where these technologies might be useful, giving people peace of mind while interacting online. The potential for holography to revolutionize computing, data storage, and virtual reality is immense, and it will open the door to groundbreaking new experiences and technologies that will define how we interact with the digital world in the years to come. More and more, holographic technology is being investigated and used by engineers and researchers, and this bodes well for future innovations that will revolutionize our daily lives, careers, and interactions with technology. Here we are at the vanguard of invention and discovery, so let's look into the future and consider the limitless possibilities that await us in holographic research. First, because to technological advances and a better grasp of holography's fundamental principles, holographic research is set to make great strides in the years ahead. Everything from entertainment and communication to science and health stands to benefit from the new uses and advancements that will arise as a result of the ongoing quest to understand the nature of light and matter. Additionally, significant developments in medical imaging and diagnostics might be possible in the future thanks to holographic research. Holographic imaging has the potential to revolutionize healthcare by providing doctors with a picture of the inside of living organisms at a level of clarity never before seen. This might lead to better diagnosis, treatment, and overall patient experience, potentially shedding light on the intricacies of the human body and paving the way for novel approaches to medical research and development. These developments could have far-reaching consequences for healthcare. Also, with the creation of cutting-edge holographic communication technologies, holographic research is set to revolutionize the telecom industry. Systems. These technologies have the potential to change the way we engage with people by allowing them to communicate and work together in virtual, immersive worlds, regardless of their physical location. Holographic communication has the potential to revolutionize several industries, including commerce, education, the entertainment industry, and social networking, by opening up new ways for people to connect and work together remotely. Innovations in the gaming and entertainment industries may also be on the horizon thanks to holographic research. With its three-dimensional visuals and interactive features that react to human interaction in real time, holographic projections and displays might provide viewers with a more immersive and lifelike experience. These developments have the potential to radically alter our entertainment consumption habits by erasing barriers between the virtual and real worlds and opening up exciting new avenues for imagination and narrative. In addition, holographic research has the potential to revolutionize scientific visualization by opening up complicated information to three-dimensional exploration. Stacks in three spaces. In order to better understand the interconnections and patterns in data, scientists may soon be able to use holographic viewing technologies to do real-time analyses and manipulations. These developments might provide academics with potent new resources for discovery and innovation in domains as diverse as engineering, biology, and astronomy. Holographic research has the potential to pave the way for exciting new developments in engineering and materials science in the years to come. Advancements in areas like photonics, optoelectronics, and metamaterials might be possible with the help of holographic materials, which could be utilized to make surfaces and structures with novel optical characteristics. These innovations have the potential to open up new markets by facilitating the creation of high-performing, feature-rich gadgets and technologies. Research into holography also has the potential to propel developments in authentication and security. Many items and documents might benefit from holographic authentication capabilities, which would increase security and make it harder for counterfeiters to copy or alter important data. These innovations have the potential to improve security and prevent fraud in many different industries, including consumer products, healthcare, identity, and money. Education and training stand to benefit greatly from holographic research's potential in the future. By enabling pupils to see intricate ideas and occurrences in 3 dimensions, holographic instructional tools have the potential to provide a more captivating and immersive learning environment, improving learning outcomes and stimulating curiosity and creativity. These developments might have implications in domains ranging from art and history to science and engineering. Research into holography also has the potential to spur innovations in prototyping and production. Innovations in product design, architecture, and fashion might be possible using holographic printing processes that allow for the fabrication of 3-dimensional things with fine detail and accuracy. These innovations have the potential to radically alter the production and design processes, ushering in a new era of personalization, efficiency, and sustainability. Holographic research has the potential to improve sustainability and environmental monitoring in the future. The application of holographic sensors has the potential to improve resource management, track the state of ecosystems, and identify and assess changes in water and air quality. With these developments, we may be able to lessen the negative effects of human actions on the ecosystem and build a future that can withstand greater shocks. In addition, developments in holographic technology have the potential to propel innovations in transportation and navigation. In both urban and rural areas, holographic mapping technologies might improve navigation and wayfinding by providing travelers with comprehensive and precise 3-dimensional maps of their surroundings. Improving transportation system safety and efficiency, these innovations may find uses in sectors as diverse as aviation, logistics, and emergency response. In addition, holographic research has the potential to revolutionize the fields of architecture and urban planning in the future. Stakeholders would be able to see and assess planned developments in 3 dimensions, with the use of holographic visualization tools that might let architects and planners construct realistic and immersive models of buildings and cityscapes. Thanks to these innovations, we may be able to build cities that are better for the environment, society, and the economy, and that people really want to live in. Holographic research is also set to drive improvements in tourism and the protection of cultural assets. By using holographic imaging technology, it may be possible to build virtual versions of historical artifacts and monuments that are both detailed and immersive. This would open up the possibility of individuals from all over the globe being able to explore and engage with these cultural heritage places. While these innovations promote a better understanding and respect of other cultures and histories, they also have the potential to safeguard our common cultural legacy for the benefit of future generations. Also, astronomy and space travel could benefit from holographic study in the future. The development of holographic imaging technology has the potential to revolutionize our understanding of the cosmos and living organisms by allowing for the 3-dimensional study of faraway objects and processes. These developments have the potential to encourage the next generation to work in the scientific and exploratory fields, which in turn might lead to new understandings of the universe and exciting new discoveries. In general, holographic research has a promising future ahead of it, with many exciting chances for discovery and innovation in several domains. We may anticipate the emergence of new technologies and applications that will revolutionize our lives, livelihoods, and interactions with the world as holography continues to be explored by researchers. We can see into the future and see what the holographic research community has in store for us. So let's make some educated guesses. First, holography research in the future will likely keep expanding the limits of what light and matter are capable of. Holography has the potential to transform many industries, from healthcare and technology to the arts and entertainment, as our knowledge of its fundamental principles expands. Furthermore, it is reasonable to expect that medical imaging and diagnostics will benefit from forthcoming holographic discoveries. It is quite probable that new holographic methods and tools will be developed by researchers. These will allow doctors to see biological systems and processes with unmatched clarity and precision, which would enhance their ability to diagnose diseases, plan treatments, and care for patients. In addition, developments in communication and telecommunications technology are likely to be propelled by next holographic research. The way we communicate and do business will be completely transformed when engineers and scientists create new holographic communication technologies that let people work together in fully immersive virtual worlds. Further, we may foresee that holographic discoveries in the future will result in gaming and entertainment industry developments. The boundaries between the virtual and physical realms will undoubtedly become more porous as a result of researchers' efforts to perfect holographic projections and displays, opening up exciting new avenues for imagination and storytelling. Additionally, it is expected that scientific visualization and research will be advanced by holography research in the future. It is very probable that scientists will create innovative holographic imaging methods and systems. These would allow researchers to examine intricate data sets in 3 dimensions, perhaps uncovering previously unknown patterns and correlations in the natural world. Additionally, it is anticipated that holographic discoveries in the future may result in materials science and engineering breakthroughs. Novel holographic materials and structures with enhanced optical characteristics are anticipated to be created by researchers, resulting in advancements in areas including photonics, optoelectronics, and metamaterials. Furthermore, it is expected that holography research in the future would lead to improvements in authentication and security systems. New holographic authentication features, developed by scientists and engineers, will offer another degree of protection and make it harder for counterfeiters to reproduce or alter important data. In addition, we may foresee that breakthroughs in training and education will result from future holographic discoveries. To help students better understand complicated ideas and phenomena in 3 dimensions, researchers will most likely create new holographic instructional materials and methods. In addition, developments in manufacturing and prototyping are likely to be pushed forward by upcoming holography research. Holographic printing has the potential to revolutionize industries like architecture, fashion, and product design by allowing for the precise and detailed production of 3-dimensional things. This might be achieved via the development of novel printing processes and systems by scientists and engineers. We may also foresee that holographic findings in the future will improve sustainability and environmental monitoring. Improved resource management and conservation initiatives are anticipated outcomes of future research on holographic sensors and systems that allow for sensitive and accurate readings of environmental characteristics. In addition, developments in transportation and navigation systems are likely to be spurred by holographic research in the future. To improve transportation safety and efficiency, engineers and scientists will most certainly create new holographic navigation and mapping systems that provide users very precise and comprehensive 3-dimensional maps of their environment. Moreover, we may foresee that next holographic discoveries will result in improvements to city planning and design. More sustainable and habitable cityscapes will be the result of researchers creating new holographic visualization methods and technologies that allow planners and architects to generate immersive and realistic models of buildings and cityscapes. Furthermore, it is expected that holographic research in the future would propel improvements in cultural preservation, tourism, and heritage. It is highly probable that innovative holographic imaging methods and systems will be developed by engineers and scientists. These will pave the way for the production of extremely lifelike digital reproductions of historical monuments and artifacts, opening up the possibility of remote exploration and interaction with these sites. We also know that astronomy and space travel will benefit from holographic discoveries in the future. Holographic imaging technologies and methods are expected to be developed by researchers. These will allow scientists to investigate faraway objects and processes in 3 dimensions, which will provide light on the universe's nature and the beginnings of life. In addition, developments in robotics and automation are likely to be spurred by holographic research in the future. Manufacturing, healthcare, and exploration stand to benefit greatly from the next developments in holographic sensors and control systems, which will allow machines and robots to see and interact with their surroundings in 3 dimensions. We also know that holographic discoveries in the future will improve energy harvesting and storage technology. Holographic solar panels and batteries are expected to be developed by researchers to gather and store energy more efficiently and for longer periods of time. This would increase renewable energy systems and grid stability. In addition, developments in consumer electronics and wearable tech are likely to be propelled by holographic research in the future. In the future, holographic displays and technologies will most likely be created by engineers and scientists to provide consumers with a more engaging and immersive experience, improving communication, entertainment, and productivity in daily life. The potential for holographic study to pave the way for groundbreaking discoveries in many different areas bodes well for the field's future. We may anticipate the emergence of new technologies and applications that will revolutionize our lives, livelihoods, and interactions with the world as holography is further investigated and harnessed by scientists and engineers. Last but not least, the infinite mysteries that await us are echoed in the complex web of holography and its consequences for our knowledge of the cosmos. Although we have come a long way in knowing how light and matter work, there is a reality that goes beyond what we can currently comprehend. We are faced with serious concerns about the essence of existence and the structure of space-time when we explore the domains of holography, general relativity, and quantum physics. Does our world really exist, or is it just a projection of data inscribed on some faraway boundary? On the other hand, may there be hidden truths just waiting to be discovered by the inquisitive human mind? We may never know all there is to know about the cosmos, but that won't stop us from expanding our horizons via investigation. Scientific minds, philosophers, and dreamers have been enthralled by the secrets of the universe for ages, and with each new discovery, we get nearer to understanding them. Being modest in the face of the universe's enormity and complexity is crucial as we enter a new age of scientific investigation. There will always be mysteries that baffle us, and occurrences that refuse to be explained, no matter how far we can push the boundaries of what we can understand with our technology. And yet, it is this same awe and interest that motivates us to keep exploring, to push the boundaries of what we know and comprehend. Embrace the secrets of the cosmos with open minds and hearts as we continue our exploration and discovery adventure. The search for truth is an endless journey. Whether we are about to discover the universe's mysteries, or are just beginning to probe a reality that is far beyond our understanding, one thing is clear. The quest for knowledge is an admirable cause that deserves our utmost respect and admiration. Humanity will persist in venturing into uncharted territory in an effort to decipher the secrets of the universe and life itself, so long as there remain unresolved questions and riddles. The cosmic microwave background, CMB, is one of the most fascinating topics in contemporary cosmology, and we're excited to dig into it. This subtle, almost invisible light covers the universe and contains the key to understanding how it all began. Beginning with theoretical predictions made in the early 20th century and continuing through revolutionary findings and beyond, we are about to set out on an adventure. We will investigate the methods used to forecast, find, and study the CMB in great detail during sophisticated space missions. In reality, the CMB is much more than that. The cosmological data that it provides is crucial to the Big Bang idea. It gives us a look of the cosmos at a much younger age, 380,000 years, compared to the present day when it's around 13. 8 billion years old. In this movie, we'll meet the important people whose contributions have been crucial in deciphering the meaning of these old photons. Not only do their tales revolve on scientific breakthroughs, but they also include delightful surprises and an insatiable need for knowledge. From building sensitive sensors to interpreting complicated data, we will go into the technical aspects of how the CMB is examined. This involves studying the whole radiation spectrum and deciphering the minute variations with large cosmic consequences. Our story will also go over the major missions like COBE, WMAP, and Planck, which have molded our present-day knowledge of the CMB. We now have a more complete picture of the early cosmos because to the distinct contributions made by each of these missions. Cosmic ray observations have far-reaching consequences. In fact, they go much beyond the purview of theoretical physics and into philosophical and existential questions. What does the cosmic microwave background teach us about the universe's origin and ultimate destiny? How does it make us reevaluate how space and time work? Also, the CMB's history is still very much unfinished. The CMB will be explored with ever-increasing accuracy in future expeditions made possible by technological advancements. The questions we are only starting to raise will hopefully be answered by these future endeavors. When we talk about the future, we'll make wild guesses about what cosmic puzzles next-generation experiments could solve. Exciting new ideas and models are being put up to explain the data obtained from CMB measurements, making this an exciting period in cosmology. Finally, we consider the far-reaching consequences of CMB research on our cosmic knowledge. It has prompted fresh inquiries into the nature of the universe and altered long-held assumptions. If you want to know why the cosmic microwave background is a major finding in cosmology and astronomy, this video will help you understand it better. It's proof that people are insatiably curious and will stop at nothing to learn more about the cosmos. Come along as we delve into the captivating tale of light from the beginning of time, illuminating the evolution of the cosmos and its never-ending capacity to astound us with its complexity and magnificence. Along the way, we hope you'll think about how little we are in comparison to the cosmos and how much of an impact we can have. This is more than simply a space opera. This is a narrative about humanity as a whole, about our desire to know the universe on a deeper level and to push ourselves to our limits. This incredible adventure would not have been possible without you. Join me as we investigate the cosmic microwave background in search of Big Bang remnants. In essence, the cosmic microwave background, CMB, is the radiation left behind from the universe's violent beginning, the Big Bang. The radiation that makes up the cosmos provides a picture of the universe before stars and galaxies came into being, and it permeates the whole cosmos. With a history that begins at a mere 380,000 years after the Big Bang, the cosmic microwave background, CMB, is the earliest visible light in the cosmos. When the cosmos cooled down to a point where photons could move freely, a uniform light began to fill the whole cosmos. Although it includes minute temperature variations, this background radiation is amazingly homogeneous in all directions. These variations are fundamental because they stand in for the cosmic voids, clusters of galaxies and galaxies themselves, which are the building blocks of the cosmos. A weak, almost isotropic radiation unrelated to any star, galaxy, or other astronomical object is recognized as the cosmic microwave background, CMB. This is why it gives a distinct, unadulterated picture of the early cosmos, uncluttered by the complexity of later cosmic structures. Measured at a temperature of 7 degrees above zero, the CMB is a remnant of the Big Bang, when the universe went from being opaque to transparent. The temperature drop is due to the expansion of the universe over billions of years. As far as spectra go, the CMB is a model of black-body radiation, matching theoretical predictions nearly to the letter. This astounding agreement with theoretical models is a powerful piece of evidence that backs the Big Bang idea. It was a watershed moment in cosmology when the CMB was discovered in the middle of the 20th century. As a result, the steady-state theory and other competing theories were pushed to the background as the scientific community embraced the Big Bang idea. An incredible property of the cosmic microwave background, CMB, is its homogeneity, which points to a very homogeneous early cosmos. The distribution of matter and energy in the early universe may be inferred from the minute temperature changes. The study of the cosmic microwave background, CMB, also sheds light on the driving forces of the early cosmos. the most enigmatic components of the universe, dark matter and dark energy, are better understood as a result of these investigations. For more than 13 billion years, each photon in the cosmic microwave background has seldom touched matter as it has traveled across space. The cosmic microwave background, CMB, is now a unique instrument for studying the early cosmos because of this voyage. It provides information that is unavailable from other sources. All over the cosmos there is the cosmic microwave background, or CMB. The remarkable intelligence of astronomers and physicists is on full display in the complex technology and methodologies needed to detect and analyze this noise. Extremely accurate reconstructions of the early universe's circumstances are now possible because to precise observations of the cosmic microwave background, CMB. This allows us to comprehend the universe's evolution from its elementary state to its present-day intricate structure with more clarity. Accurate measurements of the universe's age, rate of expansion, and composition have been made possible by precision cosmology, which in turn has been made possible through CMB research. One cannot exaggerate the significance of the CMB. It validates many parts of the Big Bang model while forcing scientists to reconsider other parts, and it is a cornerstone of our present knowledge of the structure and history of the universe. Our expanding knowledge of the universe is a direct result of our ongoing exploration of the cosmic microwave background, CMB, using more advanced sensors. With every new discovery comes more questions and deeper understanding of the universe's fabric. Therefore, this path of discovery is far from complete. It would be an understatement to say that the cosmic microwave background is crucial to comprehending the cosmos. Our understanding of the universe's beginning, structure, and ultimate destiny hinges on it. We can see the early cosmos in this light from long ago, and it gives us a starting point from which to evaluate how the universe has changed since then. Critical mass billiard, CMB analysis, allows scientists to verify important Big Bang theory predictions. Everything related to dark energy, dark matter, and the expansion rate of the universe falls under this category. All of these things are essential to the universe as we know it now. Additionally, the cosmic microwave background, CMB, allows us to put general relativity to the test in a cosmological setting. The cosmological applications of Einstein's theory are reinforced by the correlation between the theory's predictions and the cosmic microwave background, CMB data, which show that the expansion of the universe is influenced by the gravity of all matter and energy. Additionally, the cosmic microwave background, CMB, gives the first ever image of the distribution of matter in the cosmos. Understanding the formation and evolution of galaxies and clusters of galaxies is possible via the study of the cosmic microwave background, CMB, and its minute temperature changes. The exact measurements of the temperature variations of the cosmic microwave background, CMB, allow cosmologists to deduce the universe's geometry. This study's unexpected finding that the universe is flat has far-reaching consequences for how we interpret the past and predict the future of the cosmos. The enigmatic cosmic inflationary era, during which the cosmos expanded rapidly for a very short time, is even touched upon in CMB studies. Inflation may have corrected for the early inconsistencies in the distribution of matter and energy immediately after the Big Bang, according to the cosmic microwave background, CMB features. Improving the standard model of particle physics is another important feature of CMB study. The cosmic microwave background, CMB, provides an environment for evaluating hypotheses of elementary particles and forces that are difficult or impossible to study in labs on Earth. Other cosmic events may be measured against the CMB as well. By tracking the motion of galaxies in relation to the cosmic microwave background, CMB, astronomers may learn about the effects of gravity over long distances and how dark energy behaves. Quantitative cosmology relies on the CMB as well. Cosmologists use cosmic microwave background, CMB, data to test hypotheses on the birth and development of cosmic structure by honing simulations of the expansion of the universe from its early phases to the current day. With the help of the CMB, we can put Earth in a cosmic perspective that is more expansive in terms of size. This proves once again that Earth is not special or at the center of anything, as the rules of physics are the same elsewhere in the cosmos. Computer and technological limits are being pushed by the continuing investigation of the CMB. More data is produced, and technology with wider applicability is stimulated with each new generation of CMB measuring telescopes and sensors. We want to resolve some of the most basic cosmic mysteries by maintaining our exploration of the cosmic microwave background, CMB. To illustrate the point, why does the cosmos consist mostly of matter and not antimatter? Dissecting the CMB in great detail could provide hints about this imbalance. A major mystery about the cosmos's connection is raised by the regularity of the CMB. If the speed of light prevents various areas from experiencing temperature equalization, then why is it isotropic? The key is to comprehend the fundamental structure of space-time. We anticipate that other missions that seek to investigate the CMB in more depth will reveal subtleties in the polarization of this long-lived light. Further information on the early stages of the universe and the characteristics of cosmic gravity may be uncovered by such investigations. To summarize, the cosmic microwave background is more than simply a reverberation of the Big Bang. It is a lighthouse that sheds light on our whole cosmic knowledge. It provides a unified tale of the origins of the universe by bridging the fields of thermodynamics, quantum mechanics, and relativity. Scientists are getting closer to the answers to the big questions about our existence and the nature of reality as scientists continue to uncover more of the cosmic microwave background. Astronomers and cosmologists have conjectured about the Big Bang's beginnings for a very long time. Early in the 20th century, several influential hypotheses emerged in an effort to explain the cosmos from its very beginning. That the cosmos originated from a single, endlessly dense point was the central tenet of the Big Bang hypothesis. The measured redshift of distant galaxies provide credence to the idea that the cosmos has been expanding ever since this first explosion, which is confirmed by this model. The steady-state hypothesis was an alternative that maintained the cosmos has always had the same shape and would always have the same shape. According to this hypothesis, the density of matter in the cosmos remains constant because new matter is constantly being generated as the universe expands. In the 1920s, Alexander Friedmann was the first to suggest that the cosmos was expanding, using his answers to Einstein's general relativity equations as a foundation. According to Friedmann's ideas, the total energy density determines whether the universe is expanding, shrinking, or static. In a parallel but separate development, the Belgian priest and physicist Georges Lemaitre postulated that the cosmos expanded from a primordial atom, which he called a cosmic egg, that burst open at the instant of creation. The concept of a cosmos that was constantly expanding was one that Einstein first rejected in favor of a more static one. But after Hubble's 1929 sight of the expanding cosmos, he subsequently referred to his inability to foretell its expansion as the worst mistake of his life. To back up these theoretical concepts with evidence, Hubble found that the cosmos was expanding. The redshifts in the light from faraway galaxies were measured by Hubble, who demonstrated that galaxies are receding from us in every direction. This suggests that the universe is expanding. Because of this expansion, scientists now know that the early cosmos was more hotter and denser. The concept that the early cosmos was drastically different from our modern-day view was born out of this epiphany. Gamow, Alpha, and Herman came up with the theory that the early cosmos was very hot and dense later on. They postulated that, as the cosmos grew, this heat would dissipate, leaving behind a lingering light that is now recognized as the cosmic microwave background. A turning point in the debate between the Big Bang and steady-state theories came in 1965, when Penzias and Wilson discovered the cosmic microwave background, CMB. To a T, the Big Bang model accurately anticipated the presence and characteristics of the CMB. A dynamic, developing universe was proposed as a replacement for the idea of an eternal, immutable cosmos in these early conceptions of the world, which had far-reaching consequences. With each new hypothesis, we learned more about the universe and how it all started. Cosmology has developed into a rigorous study from these humble origins, delving into the early cosmos using the mathematical tools of general relativity and the observational data from astronomy. scientific discoveries have shed light on the elements as well as the properties of galaxies, stars, and planets. By delving into the primordial soup of the cosmos, scientists have been able to piece together what happened in the moments after the Big Bang and how the atoms were formed. The inflationary model, which postulates a rapid expansion of the cosmos in the first fractions of a second, emerged as a result of the evolution of the Big Bang hypothesis. The regularity of the cosmic microwave background, CMB, across enormous distances is one of the many holes in the Big Bang hypothesis that this theory fills. Both theoretical developments and fresh findings are propelling modern research into the early cosmos. From the most theoretical physics to the most concrete astronomical observations, every new finding fits into the bigger picture and helps to explain the origins of our universe. When asked to explain the Big Bang, most people look to the theory. In its most basic form, it describes how our familiar cosmos inflated from a tiny singularity over the course of 8 billion years to become what it is today. The Big Bang hypothesis postulates that the cosmos grew swiftly from a condition of tremendous heat and density. Because of this expansion, the universe cooled and is still expanding now. This is an effort to shed light on the events leading up to and after that point in time. If you want to know what occurred after the Big Bang, you have to know that it wasn't an explosion, but rather the expansion of space. At its core, the Big Bang did not include an explosion, but rather the expansion of space. The first version of Hubble's law states that the whole cosmos is expanding at an exponential rate, with further away things expanding at a quicker rate. Constant cosmic microwave background radiation is one of the strong arguments in favor of the Big Bang. This radiation captures the universe when it was just beginning to form, since it is a relic of the heat from the Big Bang's first explosion. Theoretically, the cosmos was subject to very high pressure and heat in the immediate aftermath of the Big Bang. It cooled and expanded to the point that the first electrons, protons, and neutrons could be created. Hydrogen and helium, two of the lightest elements in the universe, were created via nucleosynthesis as the cosmos cooled and expanded. All of this happened in the very first moments the cosmos was born. From the beginning, when temperatures were billions of degrees, to the creation of elementary particles, the creation of light elements, and eventually the production of galaxies and stars, the Big Bang hypothesis lays out a blueprint for the cosmic chronology. The idea of cosmic inflation has been added to this model of the early cosmos, making it even more precise. The observable world was supposedly homogenized and smoothed down during the first minuscule fraction of a second of the universe's expansion, according to this idea. When seen from a great distance, the cosmos seems flat, homogeneous, and isotropic, all of which are significant mysteries within the Big Bang hypothesis. Cosmic inflation provides an explanation for these observations and more. The homogeneity of the CMB may also be better understood with its aid. Both theoretical calculations and data from the heavens lend credence to the Big Bang hypothesis. The predictions of the Big Bang hypothesis for the measured abundances of the elements are consistent with all observations and measurements of the cosmos at large. Using the Big Bang hypothesis as a starting point, we can understand how galaxies are distributed and how cosmic background radiation works. It explains not only the ongoing expansion of the cosmos, but also the relative proportions of its constituent components in its early stages. A hot Big Bang nucleosynthesis model predicts an abundance of helium, which is compatible with the Big Bang hypothesis. This provides more evidence in favor of the idea. Based on the idea, helium could only exist in very hot and dense environments, which explains why it makes up over 25% of the observable cosmos. Additionally, this idea has a clear empirical basis in the expanding universe, finding made possible by redshift studies. The fact that galaxies are receding from us in every direction lends credence to the theory that the universe is expanding. Since it offers the most satisfactory explanation for the findings of astronomers and physicists, the Big Bang hypothesis has grown into an essential cornerstone of cosmology. In doing so, it provides a unifying theoretical framework for a large range of phenomena. The Big Bang hypothesis is important to our knowledge of the cosmic past and expected future events in the universe, and it is continuously revised as study continues to integrate new findings and observations. Before the Big Bang, the cosmos was much denser and hotter than it is now. It was also far less expansive and frigid. A singularity in which the whole universe's matter and energy were condensed into one tiny spot is a common way to characterize this initial condition. During the cosmic inflationary period, the expansion of the cosmos was exponential. As a result of this acceleration, the cosmos shrank in temperature and density, and galaxies grew further apart in space. After inflation, the expansion of the universe slowed down, yet it nevertheless persisted. The formation of the first elementary particles, such quarks and electrons, was enabled by this cooling. Protons and neutrons were formed when these particles merged later on. Nucleosynthesis occurred in the few moments after the cosmos came into being. During this time, the cooling of the Earth's surface allowed the nuclei of hydrogen, helium, and a trace quantity of lithium to fuse together via nuclear fusion. Roughly 380,000 years after the Big Bang, a period called the recombination came to pass. Here, neutral atoms were formed when electrons fused with nuclei. Now that unbound electrons couldn't deflect the light, it could finally pass unimpeded, and the cosmic microwave background radiation could be released. As a result of this recombination phase, the cosmic microwave background radiation that we can see today was produced. The vast expanse it occupies provides a clear picture of the early cosmos, shedding light on its beginning circumstances and subsequent history. It fills the whole cosmos. Light from faraway galaxies is redshifted, which shows that the cosmos is expanding. Wavelengths and the length of light are both affected by the expansion of space. It is confirmed that the cosmos is still expanding, since this reddening of the spectrum is proportionate to the distance from Earth, with relation to Earth's distance, proving that the cosmos is continuing to expand. As areas with marginally greater density attracted more stuff, the cosmos was further shaped by gravitational forces. Gradually, stars, galaxies, and other bigger structures emerged from these minuscule oscillations that had grown over time as a result of gravity's pull. When dark matter and regular matter cool and congregate, structures like these are created. Invisible and unobservable dark matter interacts with gravity to support the growth of intricate structures. Stars were born from molecular clouds, which were made possible by the universe's cooling. The development of galaxies and new stars was triggered by the increasing density and gravity of these dust and gas clouds as they accumulated. The cosmos is shaped by the delicate balance of forces, including gravity and the expansion of space. Even though matter is pulled together by gravity, the expansion of space may have the opposite effect, changing the rate and structure of creation in the universe. Dark energy, an enigmatic force that seems to be pulling galaxies apart at a faster and faster pace, is now thought to be speeding up the expansion of the universe. This finding provides further evidence that dark energy's characteristics are crucial to the universe's ultimate destiny. New stages of cosmic development are ushered in by the ongoing cooling of the expanding and changing cosmos. This cooling trend affects stellar lifetimes, planet formation, and maybe even the universe's habitability in the future. Scientists have built models that can forecast the history and future of the cosmos by examining its expansion from a hot, dense state. From the smallest subatomic particles to the grandest cosmic structures, these models are essential for comprehension. The incredible tale of change guided by physical principles begins in a hot, dense state and ends in the present spacious and organized world. In addition to detailing the history of the cosmos, this story offers hints as to what the future holds. An important milestone in cosmology's development, the prediction of the cosmic microwave background radiation, exemplifies the predictive potential of theoretical physics. The hot Big Bang theory of the universe predicted it as an inevitable consequence at first. American-Soviet theoretical physicist George Gamow started to think about what a hot, dense Big Bang may mean for the cosmos in the 1940s. He postulated that the existence of radioactive remnants from this primordial era would serve as irrefutable proof of the Big Bang. Gamow and his colleagues Ralph Alpha and Robert Herman determined that this remnant radiation would have cooled in the vast expanse of time after the Big Bang, illuminating space with a subtle microwave radiation. According to their estimations, this leftover radiation would have a temperature of around 5 degrees Kelvin. This was an audacious forecast since there was zero empirical proof of this cosmic afterglow's existence back then. What is today known as cosmic microwave background radiation has its theoretical origins in the work of Gamow, Alpha, and Herman. The wider astronomical community, however, paid little attention to their forecasts for over 20 years. The core mass black hole, CMB, was unintentionally found by Robert Wilson and Arno Penzias in the 1960s. While playing about with a sensitive radio antenna, the two discovered an enigmatic isotropic signal that didn't seem to be coming from anywhere in the sky. When Penzias and Wilson first made their finding, it was puzzling since the signal's uniformity didn't fit any known sources, such stars or galaxies. It was only when an outside force, Robert Dicke and his colleagues, were involved that it was determined to be the Big Bang's projected remnant radiation. Based on his own gravitational physics research, Dicke had independently concluded that the CMB should exist, and he had been getting ready to conduct his own search for it. The missing empirical evidence corroborating the Big Bang concept was given by the accidental finding made by Penzias and Wilson. The discovery of the cosmic microwave background, CMB, was a major finding that supported the Big Bang hypothesis. It replaced a theoretical and speculative paradigm in cosmology with one based on real-world observations. The homogeneity of the CMB provided a unique insight into the early universe's environment, revealing that it was very homogeneous. This was a crucial clue that helped us put together the history of the universe and its evolution from a simpler state to the complex one we see today. Our knowledge of the Big Bang's beginnings has been further refined by subsequent CMB research. Through these studies, the hallmarks of the first density changes that would cause galaxies to form, the minute temperature fluctuations of the cosmic microwave background CMB, have been observed. Thanks to its ability to precisely map these anisotropies, the cosmic microwave background, CMB, has become an invaluable resource for comparing the early universe's circumstances to those predicted by cosmic inflation and the Big Bang theories. From COBE to WMAP to PLANET and beyond, each succeeding cosmic survey has deepened our comprehension of the CMB and yielded more exact information on the age, composition, and development of the universe. The Big Bang hypothesis was strengthened, and a new age of precision cosmology was inaugurated with the prediction and observation of the cosmic microwave background. This period probes the universe's grand structure's foundations to an unprecedented degree. Theoretical cosmologists Ralph Alpher, George Gamow, and Robert Herman were giants in the field, particularly when it came to understanding and predicting the cosmic microwave background radiation. Thanks to their combined efforts, our understanding of the early cosmos has advanced tremendously. Thanks to their combined efforts, our understanding of the early cosmos has advanced tremendously. George Gamow is well known for his advocacy of the Big Bang hypothesis. He transitioned from nuclear physics to cosmology. It was Gamow who first proposed the idea that there should remain traces of the primordial heat from when the cosmos was hot and dense. As a young physicist and one of Gamow's students, Ralph Alpha rose to the task of elaborating on these concepts. The Big Bang nucleosynthesis theory, which he helped establish, postulated that the primordial epoch of the cosmos occurred when the first elements were formed. The anticipated temperature of remnant radiation from the Big Bang was determined by Alpha and fellow physicist Robert Herman. Their models indicated that, with the help of background radiation, the cosmos should cool to just slightly over freezing point. Their groundbreaking work is the Alpha-Herman-Gamma paper, or the AVG paper for short, often known as the AVG report. An important part of the universe's development, the synthesis of light components at the Big Bang, was predicted in this seminal work, along with the presence of the cosmic microwave background, CMB. Even though their predictions were spot on, the scientific world as a whole failed to acknowledge Alpha and Herman's CMB work until Penzias and Wilson's unexpected discovery of the CMB. A combination of profound insight and a fondness for whimsical and instructive storytelling defined Gamow's approach to science. He contributed to the widespread acceptance of the Big Bang theory by making previously incomprehensible scientific concepts understandable. In order to describe the events that took place in the early minutes of the cosmos, Alpha and Herman collaborated using rigorous mathematical analysis and a solid grasp of nuclear physics and thermodynamics. Predictions made by Alpha, Herman, and Gamow were not fully acknowledged until the discovery of the CMB, despite their substantial contributions. This finding provided empirical support for their predictions and further established the Big Bang hypothesis as the preeminent cosmological paradigm. Their contributions were crucial to the development of contemporary cosmology and have since formed the basis for studies of the Big Bang nucleosynthesis and the cosmic microwave background. The trio's forecasts, which included information from nuclear physics, quantum mechanics, and astronomical data to provide a complete picture of the Big Bang, also demonstrated the value of multidisciplinary cooperation in the physical sciences. Even if they were often eclipsed by more famous names in cosmology, Alpha and Herman are now again rightfully recognized pioneers thanks to a re-evaluation of their work in recent years. Many of the methods utilized in contemporary cosmology research have their theoretical roots in their work. This is especially true in the fields of cosmic microwave background, CMB data interpretation, and the study of the thermal history of the universe. The work of Ralph Alpher, George Gamow, and Robert Herman, which was done in partnership, shows that theoretical predictions are still useful in research, and that ideas that were ahead of their time may change how we see basic facts. To sum up, Alpher, Gamow, and Herman's contributions provide the groundwork for a seminal cosmological discovery and serve as an inspiration to cosmologists both now and in the future. Among the most significant discoveries about the universe's makeup were the theoretical predictions of the cosmic microwave background, or CMB, which is a relic of the early universe. This new knowledge of the universe's beginnings, together with theoretical physics, led to these forecasts. After the Big Bang, cosmologists originally thought the cosmos would have been filled with a sea of neutrons, protons, electrons, and photons, since they believed the universe began from a hot, dense state. Atoms were formed and photons were released when the cosmos cooled as it expanded. It was anticipated that, as the cosmos expanded, this ocean of photons, which was originally at thermal equilibrium with matter, would cool down to a few degrees above absolute zero. The cosmic microwave background is currently being detected as these photons. It was originally thought that this radiation would be homogeneous and isotropic, much as the cosmos was intended to be right after the Big Bang. The mid-20th century discovery of the cosmic microwave background verified these predictions with astounding precision. With its current measurement of around 25 degrees above absolute zero, the cosmic microwave background temperature is in agreement with theoretical predictions obtained from estimates of the expansion and cooling history of the universe. As far as the Big Bang hypothesis is concerned, the CMB's existence is an essential litmus test. It shows us the cosmos as it was 380,000 years ago, before stars and galaxies were born, and gives us proof of the conditions that existed back then. To put it theoretically, the CMB is a necessary but not sufficient condition for the expansion of the universe. For models of the origin and evolution of cosmic structures, it aids cosmologists in setting beginning circumstances. The anticipation of small anisotropies, or temperature changes, was an interesting part of the CMB's forecast. It was thought that these anisotropies mirrored the early universe's density fluctuations, which would cause clusters and galaxies to develop on a grand scale. Later satellite missions like COBE, WMAP, and PLANTS were able to analyze these temperature changes in great detail, which led to new understandings about the nature and consequences of dark matter and dark energy, as well as the distribution of matter and energy in the universe. The mechanics of the early universe may be better understood via these anisotropies, and they may even provide clues to the inflationary era, a theoretically short time of fast expansion that happened just after the Big Bang. A key concept in Big Bang nucleosynthesis, the uniformity and precision of the CMB's blackbody spectrum provides strong support for thermodynamic models of the early universe. On the other hand, the nearly perfect isotropy and homogeneity of the CMB, given the causally disconnected regions it spans, pose a challenge to physicists trying to explain the theory behind Big Bang nucleosynthesis. As a result of this difficulty, inflationary theory, which offers a mechanism to account for these findings, has gained more traction. In general, the CMB's theoretical predictions highlight the predictive potential of cosmological models and the cosmic scale application of physical principles. They show how theoretical ideas may pave the way for empirical findings that both validate and broaden our cosmic view. Overall, the theory that anticipated the cosmic microwave background, CMB, exemplifies the breadth and depth of our interest in the cosmos and our dogged determination to grasp its most basic features. A prime illustration of the power of chance in scientific inquiry is the finding of the cosmic microwave background, or CMB. This study highlights the power of unexpected discoveries to bring about significant changes in our view of the cosmos. Two young radio astronomers working at Bell Laboratories in New Jersey in 1964, Arno Penzias and Robert Wilson, were tinkering with a huge horn antenna that had been made for satellite communications. Performing experiments in satellite communication and radio astronomy was their simple objective. On the other hand, a uniformly weak microwave signal that did not seem to have come from any known astronomical source was a constant background noise that Penzias and Wilson encountered in their observations. It didn't matter which way they aimed their antenna, this cacophony persisted. They searched high and low for interference sources, including pigeon droppings in the antenna, which they cleaned thoroughly, but to no avail. The noise persisted. None of the typical explanations, including urban radio interference or atmospheric effects, fit the data. Penzias and Wilson, perplexed by the sound, sought the advice of other physicists and astronomers. An informal discussion with MIT professor Bernard Burke led them to a revolutionary insight. According to Burke, Robert Dicke once made the proposal that observable microwave radiation pervaded space as a residue of the Big Bang in a lecture he gave at Johns Hopkins University. Penzias and Wilson's enigmatic notes rang true with this proposal. Penzias and Wilson approached Dicke, who, with colleagues at Princeton University, had been planning an experiment to look for this radiation. After realizing their results may have significant implications, it became evident that Penzias and Wilson had already discovered the signal that Dicke and his colleagues were looking for when they shared their data with Dicker. This accidental finding offered the first concrete proof of the Big Bang hypothesis. This finding has far-reaching consequences. It was the linchpin piece of data that finally cemented the Big Bang theory's position as the standard cosmological framework. There had previously been a schism in the scientific community between those who believed in the steady-state theory and those who believed in the Big Bang. A watershed event in cosmology came in 1965 with the publishing of Penzias and Wilson's results and a theoretical explanation by Dicke's group. It altered the status quo and determined the course of future studies. The Nobel Prize in Physics was bestowed to Penzias and Wilson in 1978 in recognition of their seminal but unintentional discovery. Awarded the Nobel Prize in Physics in 1978. One of the most important scientific discoveries of the 20th century was their discovery of the cosmic microwave background, CMB. In addition to shedding light on the early and later stages of the universe's history, this finding ushered in a new age of cosmology that centered on the exact measurement of the background radiation of the cosmos. Even now, cosmological studies are shaped by the legacy of this unintentional finding. It laid the groundwork for other satellite missions, including ESCOBE, WMAP, and Planck, which improved our CMB measurements and expanded our understanding of the universe. The tale of Penzias and Wilson exemplifies how scientific investigation may yield surprising outcomes, which in turn can lead to groundbreaking discoveries about the cosmos. The cosmic microwave background radiation, proof of the universe's explosive origins, was discovered by two radio astronomers, Arno Penzias and Robert Wilson by accident. This discovery is among the biggest in the history of cosmology. Just as interesting as the finding itself is the path they took to get there. Penzias, who was born in Germany but escaped Nazi persecution, discovered physics as his passion after coming to the United States. He went on to get a PhD from Columbia University. He ended up in the renownedly creative Bell Labs in New Jersey, thanks to his research interests. Robert Wilson, a radio astronomer from the United States who attended Caltech for graduate school, joined Bell Labs after finishing his degree. There he zeroed in on radio technology and its astronomical uses, an area bursting at the seams with untapped promise for discovery. Penzias and Wilson collaborated to conduct experiments using a huge horn antenna that had been constructed by Bell Labs for testing satellite communication. The feeble radio waves sent off by the Milky Way and other heavenly bodies were their original target. A continuous, unexplained noise, a mild static that seemed to come from all directions, was experienced when they were testing the antenna. No previously identified radio source from space produces noise of this uniformity. Thus, it was definitely out of the ordinary. The unexplained sound remained after thorough troubleshooting, which included cleaning the antenna of pigeon droppings. From technical issues with the equipment to environmental factors, they checked every potential source of influence. Still, the sound persisted. Penzias and Wilson, both interested and frustrated, sought out the opinions of other specialists in the subject in their quest to find a solution. As they continued their journey, they were led to a team of academics at Princeton University who were delving into the theory of cosmic radiation. Robert Dicke was at the head of this group that speculated that the cosmos should be filled with remnants of the Big Bang's radiation. Actually, Dicke and his colleagues were getting ready to do their own experiment in order to detect this radiation. It wasn't until Penzias and Wilson heard about Dicke's theory that things started to click. The constant din they'd been picking up may have been the radiation that Dicke's crew had been chasing, they concluded. They contacted Dicke and informed him of their discoveries. Their findings confirmed Dicke's theoretical expectations about the remnant radiation from the Big Bang, so he didn't take long to appreciate their significance. Penzias and Wilson's empirical data and Dicke's theoretical explanation were published at the same time as a consequence of the subsequent cooperation. Combining theory and observation in this way strengthened the scientific consensus around the Big Bang idea. Penzias and Wilson were awarded the Nobel Prize in Physics in 1978 in recognition of their contributions to this seminal finding. This award is a tribute to how much their unintentional finding changed our view of the cosmos. Though their careers were capped off with their discovery of the CMB, both scientists persisted in astronomy study in the years that followed, making further contributions to the subject. Not only is the narrative of Penzias and Wilson a tale of scientific discovery, but it is also a tale of curiosity and endurance. It shows how seemingly insignificant outcomes may occasionally lead to discoveries in previously unexplored areas of study. Their unexpected turn from perplexing noise to a Nobel Prize-winning discovery exemplifies how scientific investigation may be filled with fortuitous events, whereby apparently little abnormalities can provide profound understandings of the universe. At Bell Laboratories in Holmdel, New Jersey, Arno Penzias and Robert Wilson were using a big horn-shaped antenna. An improbable location for a groundbreaking cosmological finding was this antenna, which was initially constructed for early satellite communication studies. For their delicate astronomical investigations, the antenna's design prioritized reducing radio noise. Perfect for studying the galactic plane and other astronomical phenomena, it could detect microwaves at a wavelength of 7.35 centimeters. It wasn't too difficult to set up their experiment. An essential component for receiving feeble communications from space without introducing substantial interference was the low-noise radio receiver, which was coupled to the antenna. An annoying background noise persisted throughout Penzias and Wilson's investigations. Unlike celestial signals, which usually fluctuate in strength and source, this noise seemed to emanate equally from all directions in space. This property is known as isotropy. The exact blackbody temperature of the noise was around 3.5 Kelvin. A prominent theoretical idea in astrophysics is blackbody radiation, which is released by an object or environment that flawlessly re-radiates energy after absorbing all of it. The noise continued even after they searched for and removed every possible interference. In an effort to eliminate any potential interference from bird poop, they adjusted the sensors, tested the receiver, and even cleaned the antenna. I didn't understand the signal's consistency. Known sources such as the Earth's atmosphere, faraway galaxies, and the Milky Way did not provide the predicted traces. The possibility of atmospheric impacts or radio interference from neighboring New York City was thoroughly investigated and dismissed. At first, they thought the anomaly was just an annoyance, some kind of strange relic that may have anything to do with their machinery. It didn't fit, however, with the usual electrical hiccups or outside radio interference. It was too steady and continuous. As they spoke with additional specialists, the riddle became even more complex. An inexplicable din that appeared to fill the cosmos uniformly eluded all attempts at explanation. Penzias and Wilson didn't start to think their noise may be a big scientific breakthrough until they spoke to Bernard Burke and Robert Dicke. According to Dicke's theory, the cosmos should be filled with microwave radiation left over from the Big Bang. Thus, his group was aggressively searching for it. With the possible ramifications in mind, Penzias and Wilson recorded their results in great detail, outlining the noise's properties and their thorough attempts to disprove traditional theories. The scientific community took notice of their documentation and subsequent publishing right away. It was consistent with what other scientists were starting to postulate independently based on the Big Bang hypothesis on the thermal history of the cosmos. The fact that their discovery was made by chance in no way diminished its significance. However, it did show how even unintended consequences may lead to major advances in science, illustrating the serendipitous nature of the scientific process. Their research offered the first hard proof that the cosmos has been expanding from a single, very hot, and dense point in its history. Theoretical ideas on the beginning of the universe were transformed into quantifiable science with this finding, which marked a watershed moment in cosmology. Wilson's experimental equipment had unintentionally gazed back approximately 14 billion years to the Big Bang's aftermath, despite its primary purpose of more ordinary astronomical observations. A pivotal point in cosmology's history occurred when the unusual signal identified by Penzias and Wilson was explained. Its importance could only be appreciated with the help of the theoretical framework that was then being considered by a small group of scientists. Penzias and Wilson first didn't know what to do when they encountered the constant microwave signal. Robert Dicke's Princeton University research group offered the theoretical explanation that was required, determining that the noise was the cosmic microwave background radiation resulting from the Big Bang. According to Dicke's theory, the cosmos would have been heated to a uniform temperature if the Big Bang had really happened. Microwave radiation would seem to permeate the universe as this leftover heat from the early cosmos. This description was spot on for the finding made by Penzias and Wilson. A search for this background radiation has already been planned by Dicke's group. After learning about Penzias and Wilson's finding, Dicke's team was already gearing up to look for this background radiation independently. Upon learning of Penzias and Wilson's finding, they instantly identified it as the signal they had been hoping for. The scientific method was at work here in a perfect example of theory meeting experiment. A key piece of evidence supporting the Big Bang theory, that the universe had started out in a very hot and dense state and has been expanding ever since, was the discovery of the cosmic microwave background, CMB. Other observations started to fit with the CMB's existence after its discovery and interpretation. Similar tests were soon underway by radio astronomers all around the globe, and they proved time and time again that the microwave background radiation was real. What really sold it was how consistent the CMB was. It provided evidence that the early cosmos had been in thermal homeostasis, which is essential for the Big Bang theory to be correct. A perfect black body is a theoretical construct in physics that absorbs and re-emits all radiation with full efficiency. The CMB's spectrum measurements confirmed this. Unprecedented among astronomical sources, this fit well with post-Big Bang forecasts. The accuracy of CMB observations improved substantially in the years that followed. The radiation was confirmed to be isotropic, and small fluctuations were detected, which related to the early matter distribution by satellite missions like COBE and WMAP, which produced precise maps of the radiation. About 380,000 years after the Big Bang, before stars and galaxies started to develop, these changes or anisotropies in the cosmic microwave background, CMB, offered a picture of the cosmos. They were fundamental for deducing the cosmos's grand architecture. We have learned more about the universe's age, composition, and pace of expansion thanks to fresh measurements taken as the study of the cosmic microwave background, CMB, has progressed. The LCDM model, which incorporates dark matter and dark energy, is the mainstream model of Big Bang cosmology. It was developed when theoretical models of the universe were revised to integrate the results of CMB research. The CMB has had a huge effect on cosmology. It has enabled cosmologists to probe hitherto inaccessible epochs of the cosmos and has verified some features of the Big Bang. A great accomplishment in astrophysics was the interpretation and confirmation of the CMB as an artifact of the early cosmos, which translated theoretical notions into physical components of the visible cosmos. Here we see the iterative process at work in science, wherein new hypotheses are developed from previous data, which in turn direct future observations and so on, until we have a complete picture of the universe. Evidence of the efficacy of multidisciplinary research and investigation is shown by the CMB tale. The intriguing tale of scientific reasoning and cooperation that led to the identification of the cosmic microwave background, CMB radiation, as the source of the enigmatic signal found by Penzias and Wilson is worth reading. Penzias and Wilson were first confused about the relevance of the consistent noise picked up by their antenna. They had sensed something strange, but the meaning was eluding them at the moment. The defining moment occurred after a fortuitous conversation with other scientists investigating theoretical elements of the Big Bang. Penzias was apprised by MIT's Bernard Burke of a talk given by Robert Dicker, who had postulated that microwave radiation may persist as a remnant of the Big Bang. As soon as Penzias saw the link, he got in touch with Dickey, who was assisting a Princeton team. Jim Peebles and other specialists were already thinking about ways to detect the Big Bang's afterglow when they joined this team. Upon hearing about the results, Dickey and his colleagues were shocked. The two scientists from Bell Labs rapidly deduced that the uniform microwave radiation they had been attempting to eradicate was really the cosmic background radiation they had been seeking to uncover. In order to verify that the signal was coming from the cosmic microwave background, CMB, we examined its spectra and isotropy. We found that the radiation had a perfectly black body spectrum, which fits with our theoretical expectations of the radiation left over from the Big Bang. What's more, we found that the radiation was uniform across the sky, which led us to believe that it came from a hot, dense period just after the Big Bang, before stars and galaxies existed. Because of the radiation's high temperature, this identification was confirmed. It was predicted by previous theorists like Alpha and Herman that the remaining heat from the Big Bang would be a few degrees above absolute zero, and the observed temperature of the CMB at around 7 degrees Kelvin closely matched these predictions. The fact that the cosmic microwave background, CMB, is isotropic further suggests that it was unaffected by galactic or intergalactic objects, suggesting a cosmological origin consistent with the Big Bang's afterglow. After Penzias and Wilson had a firm grasp on their findings, they set out to document them in a formal report. Theoretical study outlining the cosmic background and relevance of the CMB was being produced at the same time by Dickey's group. Both articles appeared simultaneously in 1965's Astrophysical Journal. This joint paper brought together theoretical cosmology and empirical facts, proving without a reasonable doubt that the universe did, in fact, start with a fiery Big Bang. After battling with the steady-state hypothesis for some time, the Big Bang theory scored a huge win when the CMB was recognized as the Big Bang's echo. The subsequent observations and investigations have further shown that the signal is coming from the CMB. Our knowledge of the early cosmos and its development has been enhanced with each new piece of evidence. Cosmology is now a precise science where theories can be evaluated against observations by the discovery and identification of the CMB, which radically changes the field. This discovery laid the groundwork for decades of cosmological study that aimed to comprehend the universe's composition and development from its early beginnings and validated a key component of the Big Bang hypothesis. Theoretical and practical knowledge of the cosmic microwave background, CMB, owe a great deal to Robert Dicker. In addition to the theoretical predictions, he helped propel the development of cosmology by creating an environment where collaboration was encouraged. The lingering effects of the Big Bang were a topic of speculation for Dickey due to his background in experimental physics and his fascination in the universe's underlying dynamics. If the Big Bang had really happened, according to his theory, there would be background radiation left behind in the cosmos. The Princeton University team that included Dickey, David Wilkinson, and Peter Roll started working on a device to detect this microwave radiation in the early 1960s. A cooled but visible imprint of the explosive origin of the cosmos would be left behind as the universe expanded, which was the prediction upon which their efforts were founded. The central mass black hole, CMB, was not found by Dickey at first, but the theoretical model and detector he was building were significant in explaining and validating the relevance of the noise that Penzias and Wilson found. Even Dickey's pupils and co-workers felt the impact of his teachings. A doctorate student of Dickey's, Jim Peebles, was instrumental in laying the theoretical groundwork for the radiation remains of the Big Bang. The study of Peebles was crucial in defining the characteristics of the radiation that might be utilized to learn about the early cosmos. John Mather was another major player. He oversaw the COBE satellite project, which measured the CMB in great detail. An appreciation for and expansion upon the work of Dicker and his colleagues was crucial to the success of Mather's work, which resulted in his Nobel Prize. Philip James Edwin Peebles, better known as P.J.E. Peebles, was an influential figure in cosmology and the study of cosmic background radiation. His work improved our knowledge of the CMB's function within the Big Bang hypothesis and contributed to its refinement. The examination of COBE data was also greatly aided by another important individual, George Smoot. Further validation of the Big Bang hypothesis and greater insights into the texture of the cosmos at enormous scales were offered by his work on the intricate texture of the cosmic microwave background, CMB. The multiplicative effect of scientific knowledge is shown by the cooperation of these and several other researchers. The foundational theories put out by Dickey, followed by the empirical findings of Penzias and Wilson, laid the groundwork for a succession of developments that would enrich and hone our comprehension of the universe. Not only did Dickey make important strides in cosmology, but he also advanced gravitational physics, linking cosmology with quantum physics in novel and significant ways. His work paved the path for studies that tested Einstein's theory of general relativity. The significance of precise measurement and experiment in physics is another aspect of Dickey's cosmological legacy. Much of current cosmology may trace its roots back to his guiding philosophy, which favored a method that combined theoretical investigation with empirical verification. The significance of Dickey and colleagues' contributions to cosmology and the cosmic microwave background, CMB, is immeasurable. In addition to making important theoretical predictions and contributions, they were instrumental in creating technologies and methodologies that have had and will have lasting impacts on the discipline. The collaboration between theoretical physics and observational astronomy is shown by their efforts, which enhance our comprehension of the cosmos via the intersection and complementarity of both fields. The impact of these scientists' perseverance and teamwork on cosmology is immeasurable. The discipline has grown into a dynamic and exact science that challenges our preconceptions about the cosmos. The extensive study conducted by Dickey and others in this area has laid a solid foundation for future studies into the universe's beginnings and its eventual destiny. In 1989, the National Aeronautics and Space Administration deployed a satellite called the Cosmic Background Explorer, or COBE. With its precise observations, it aims to examine the cosmic microwave background radiation, CMB, that existed after the Big Bang and put ideas about the early cosmos to the test. COBE's primary objective was to provide the most precise measurements yet taken of the early universe's diffuse infrared and microwave radiation. The Big Bang hypothesis and our understanding of the universe's basic structure depended on this. Anisotropies, or temperature changes in the CMB, might be better mapped with the help of the differential microwave radiometer, DMR, a key instrument on COBE. Shows a map of the CMB's anisotropies, or temperature changes. These minuscule temperature fluctuations describe the dispersion of stuff in the early cosmos. The far-infrared absolute spectrophotometer was another important equipment on board COBE. The cosmic microwave background, CMB spectrum, was to be measured by this device to see how well it agreed with the theoretical prediction of a perfect black body. The very exact confirmation of the CMB spectrum being a nearly perfect blackbody spectrum was provided by the data acquired by FIRIS. The confirmation that the cosmos did indeed begin in a hot, dense state was a major victory for the Big Bang theory. COBE's results on the anisotropies of the cosmic microwave background, CMB, were the first definitive proof of the waves that would cause galaxies and other large-scale structures to develop. In order to comprehend the formation of structures in the cosmos, these fluctuations were crucial. Cosmology went from being a highly speculative field to a discipline known for its accuracy because to the groundbreaking findings from COBE. The CMB had been identified before to COBE, but its frequency spectrum had not been precisely studied across a wide range. The 2006 Nobel Prize in Physics was bestowed to John Mather and George Smoot, who played crucial roles in the COBE project for their contributions to the CMB observations. Their research was crucial in proving the Big Bang hypothesis. COBE also studied the cosmic infrared background, which helped us understand how galaxies formed and how the cosmos has changed over time. The gaps on the early star activity of the cosmos were filled up by these findings. The impact of COBE goes beyond the scientific findings it has produced. Its groundbreaking work in cosmology paved the stage for subsequent missions to probe the cosmic microwave background to unprecedented depths. Continued efforts by missions like WOMAP, the Planck satellite, and the Wilkinson microwave anisotropy probe expanded upon the work of COBE, enhancing our knowledge of the cosmos by more precise measurements of the CMB anisotropies. The theorist's comprehension of the intricate dynamics governing the cosmos has been aided by the refined models of the universe's development made possible by the extensive data acquired by COBE. The sustained investment in space missions devoted to studying the origin and structure of the universe is a direct result of the success of COBE, which established the value of space-based instrumentation in cosmology. It is impossible to exaggerate the significance of COBE to cosmology. In addition to providing empirical evidence for the Big Bang, the expedition also paved the way for future research into the cosmos. Cosmologists and astronomers were able to better understand the universe's evolution over billions of years thanks to COBE's observations, which allowed them to depict the universe in its early stages. Among the many goals of the Cosmic Background Explorer mission was the determination of the universe's composition and its history from the Big Bang to the current day. In its mission, COBE sought to study the structure of the cosmic microwave background radiation, CMB, and identify any large-scale anisotropies present in it. The very precise measurement of the CMB's spectrum was the primary goal of COBE. Until COBE, scientists had no way of knowing if the cosmic microwave background, CMB, displayed a flawless black-body spectrum, an essential but unproven prediction of the Big Bang hypothesis. The mapping of the CMB's variations or anisotropies was another important goal. There was a belief that these temperature swings may reveal something about the density fluctuations in the early universe, which would cause galaxies and other big cosmic structures to develop. In order to better understand the structure of the early universe and the circumstances that led to the birth of cosmic bodies, the differential microwave radiometers on board COBE were assigned the mission of mapping these temperature changes throughout the sky. In order to confirm that the CMB is a black body, the Far Infrared Absolute Spectrophotometer, or FIRS, was installed on COBE. This was critical for confirming the Big Bang model's predictions about the universe's thermal history. COBE made groundbreaking discoveries. According to FIRS, the cosmic microwave background, CMB spectrum, is an almost perfect black body, matching theoretical expectations to an unprecedented degree of accuracy. The evidence for the Big Bang hypothesis was greatly enhanced by this discovery alone. In the CMB, the DMR instrument detected small but notable anisotropies. These temperature differences were in the range of 1 part in 100,000, which is in agreement with the early universe homogeneity predicted theoretically. These anisotropies laid the groundwork for bigger formations, like galaxies, to emerge as a result of gravity. This groundbreaking finding established a connection between the early universe's quantum fluctuations and the large-scale structure of the universe. Our knowledge of the shape and pace of expansion of the universe was also enhanced by the data collected by COBE. Inflation theories and the overall density of matter and energy in the universe are affected by the implications of the observations that support a flat universe. One alternative cosmological model anticipated distinct types of radiation in the early cosmos. COBE helped rule it out by proving the CMB had a black body spectrum. Because of this, the Big Bang hypothesis became much more grounded in reality. Star formation and galaxy development over cosmic timeframes were both illuminated by the mission's examination of the cosmic infrared background. Astronomers were able to create a fuller picture of the early cosmos as a result of this. In light of COBE's results, cosmological models had to be fine-tuned and updated, particularly to account for the ways in which the early universe's circumstances developed into the intricate structures seen today. Success with COBE prompted increased research into cosmology, which in turn led to more sophisticated missions that sought to learn more about the CMB. Inspiring a new generation of astronomers and physicists to study the universe's earliest moments and biggest sizes. COBE's significance extends beyond its scientific achievements. In sum, COBE's goals and results greatly improved our knowledge of the cosmos, ushering in a new age in cosmology, wherein empirical evidence could be used to evaluate and hone theoretical predictions about the universe. The impact of COBE's discoveries on the spectrum and homogeneity of the cosmic microwave background radiation is immense. Our knowledge of the Big Bang and the universe's basic characteristics has been greatly influenced by these discoveries. Among the most important pieces of evidence supporting the Big Bang hypothesis, COBE confirmed that the CMB possesses a nearly perfect black body spectrum. A crucial tenet of the Big Bang theory, its verification suggested that the early cosmos was in a condition of thermal equilibrium. The accuracy with which COBE measured the CMB's spectrum contributed to the settlement of long-running cosmological disputes over the early universe's makeup. Everything pointed to the cosmos starting off in a hot, dense state, which has since cooled and expanded. The cosmos is highly homogeneous on vast scales, as shown by COBE's observations of the CMB homogeneity throughout the sky. The cosmological principle, which states that, when seen from a far enough distance, the universe is isotropic and homogeneous, predicts, among other things, that the cosmos would be uniform. On the other hand, COBE did find some minor CMB changes called anisotropies. Even though these anisotropies are very small, about 100,000th of a part, they are very important in cosmology. The first building blocks of the cosmos are shown by these minute changes in temperature. Galaxies, galactic clusters, and the enormous cosmic web that we see today all originated from very small density changes in the early cosmos, which expanded due to gravity. Anisotropies provide credence to inflationary hypothesis, which postulates an exponentially fast expansion of the early cosmos. This hypothesis is able to account for the homogeneity and flatness of the cosmos, as well as the variations that COBE noted. COBE's research laid the groundwork for the conventional cosmological model, the LCDM, which incorporates dark energy and dark matter. From the Big Bang inception to the current day, this model traces the structure and history of the universe, outlining its general geometry and composition. Constraints on the Hubble constant, baryon density, dark matter density, and spectral index of primordial fluctuations, among other parameters of the LCDM model, have been heavily applied using COBE data. Theoretical speculations on the nature and characteristics of primordial particles, which may persist as dark matter in the cosmos today, stand to benefit greatly from these findings in the field of particle physics. In terms of technology, the results obtained by COBE proved the usefulness of astronomy equipment housed in space. Improved cosmic microwave background, CMB, monitoring missions like the Wilkinson Microwave Anisotropy Probe and the Planck satellite were directly inspired by COBE's performance. The results from COBE have added fresh information and data to astrophysics and cosmology courses all across the globe, which is great for education. A more profound philosophical comprehension of our position in the cosmos is one of the social impacts of COBE's findings. Our understanding of humanity's role in the universe has been shaped by COBE's contributions to a more precise image of the Big Bang. One cannot overlook the cultural importance of comprehending the origins of the cosmos. A portion of the public discourse around science and the cosmos now includes COBE's discoveries, which have made it into popular science. Overall, the results from COBE have changed cosmology since we know the structure, origins, and ultimate destiny of the universe, more better thanks to the data on the CMB's uniformity and spectrum. Launched in 2001, the Wilkinson Microwave Anisotropy Probe, WMAP, was a giant leap forward in our understanding of the cosmic microwave background, CMB. We can learn more about the geometry, composition, and development of the universe thanks to WMAP, which builds on COBE's findings by providing a more precise picture of the cosmic microwave background, CMB. The primary goal of WMAP, as compared to its predecessor COBE, was to monitor the CMB temperature changes with greater sensitivity, precision, and resolution. These readings are critical for deducing the basic physics of the early cosmos and the driving forces behind its formation. Several important cosmological parameters have been fine-tuned with the help of WMAP data, such as the age of the universe, atomic density, matter density, and the density of dark energy, which is responsible for the universe's accelerating expansion. The exact calculation of the universe's age at about 13.77 billion years was one of the hallmark results from WMAP. The more precise timescale for the development of cosmic structures was given by this measurement. The fact that the universe is flat was also more precisely verified by WMAP, with a margin of error of just 0.4%. Inflationary theories of the early cosmos are supported by this flatness, which has far-reaching consequences for the universe's destiny. The more accurate WMAP images corroborate inflationary theories of the early cosmos and show that the CM has richer textures. The WMAP detailed map showed that the CMB anisotropies had richer textures. The distribution of matter and energy during the early universe's birth, when these textures were created, provide light on the cosmic structure's origins at a mere 380,000 years old. The lambda cold dark matter LCDM model, which incorporates dark energy as a substantial part of the universe's present energy budget, was confirmed by WMAP's data to be an existing mainstream model of cosmology. By verifying that the distribution of temperature variations in the CMB is compatible with this hypothesis, the measurements of the probe have contributed to the strengthening of the theory of inflation. The rapid expansion of the cosmos in the immediate aftermath of the Big Bang, known as inflation, smoothed out any imperfections in that time. Additionally, WMAP revealed fresh details about the ionization era, when the intergalactic medium was ionized and the first stars and galaxies were born. Around 400 million years after the Big Bang, ionization took place, as seen by WMAP data. New insights into the cosmos were added to our canon by WMAP's studies of the CMB's polarization. This three-dimensional view of the early universe is made possible by polarization measurements, which aid in mapping the motion of light from that time. Neutrino hypotheses were also limited by the accuracy of WMAP's findings, which cast doubt on their properties and potential cosmic impacts. It implied that neutrinos constitute a tiny but substantial fraction of the total mass energy in the cosmos. Important to our knowledge of basic particle physics, the satellite's results advanced the notion of cosmic neutrino background and hinted to neutrino oscillations. WMAP's mission lasted much longer than anticipated, collecting an abundance of data for 9 years prior to its retirement in 2010. Our cosmological models were revised, and fresh theoretical material was given with each data release from WMAP. Even now, modern cosmology is shaped by the work of WMAP. The data it contains is being utilized by scientists all around the globe to test and improve cosmological theories. In conclusion, WMAP has added to our cosmic knowledge while also casting fresh doubt on long-held assumptions about the Big Bang, the universe's initial state, and its ultimate destiny. It demonstrates how careful observation may change our views of the universe. In order to verify the predictions of the Big Bang model and inflationary theory, as well as to discover the geometry, content, and development of the universe, the Wilkinson Microwave Anisotropy Probe, WMAP, set out to create a comprehensive map of the cosmic microwave background radiation. The goal of WMAP was to get very precise measurements of the sky-sky temperature gradients in the CMB. With this information, astronomers would be able to piece together a more complete picture of the early universe's matter and energy distribution, which would be crucial for building a comprehensive cosmic history chronology. Additional proof that the enigmatic factor responsible for the universe's rapid expansion, dark energy, exists was given by the probe's in-depth study of the CMB anisotropies. Researchers determined that dark energy accounts for about 71.4% of the total energy in the cosmos. Dark matter makes up around 24% of the universe according to WMAP, whereas conventional baryonic matter accounts for about 4.6%. This changes prior estimations and paints a better picture of the universe's makeup. The conventional model of Big Bang cosmology, the lambda cold dark matter model, was confirmed by the WMAP data. Fitting the WMAP data surprisingly well, this model posits a universe dominated by cold dark matter, lambda, and dark energy. The measurement of the CMB's polarization was another major accomplishment of WMAP. This observation shed light on a crucial period in the universe's history, the era of ionization, when the primordial gas was ionized by the first stars. By confirming that the distribution of fluctuations in the CMB agrees with the predictions of inflationary models, WMAP's measurements helped to refine the size of cosmic inflation. This data lends credence to the theory that the early cosmos grew at an exponential rate. The probe's results contributed to a more definite chronology of cosmic events, including the birth of stars. Past estimates indicated ionization started around 400 million years after the Big Bang, according to WMAP. The findings of WMAP also limited the theories of cosmic structure development, which explains how the large-scale structures seen today evolved from quantum fluctuations in the early cosmos. Astronomers were able to better comprehend the early universe's gravitational forces and how they contributed to galaxy formation thanks to the data, which improved our knowledge of the texture and structure of the anisotropies. The observations of the temperature changes in the CMB taken by WMAP have shed light on the primordial soup from which all cosmic structures emerged, and this has contributed to our current knowledge of the universe's large-scale structure. The precise picture of the cosmos in its infancy, 380,000 years ago, and the groundwork it laid for future investigations of the cosmic background radiation are both provided by the satellite's extensive map of the CMB, which is still considered a crucial tool for cosmologists. In sum, WMAP's aims and findings have substantially improved our knowledge of the cosmos, confirming several parts of the Big Bang model and delivering fresh insights that impact cosmological theory and study to this day. The Wilkinson Microwave Anisotropy Probe, WMAP, was an important step forward in cosmology since it helped us better grasp the universe's age and composition. Data from WMAP's accurate measurements of the cosmic microwave background, CMB, provide light on a number of important cosmological parameters. Cosmologists were able to determine the universe's age with previously unattainable precision because to WMAP's meticulous measurements of the CMB anisotropies. While previous estimates were all over the place, WMAP data settled on an age of 1377 billion years for the cosmos, with an incredibly small margin of uncertainty. Since the variations in the CMB include information on the universe's expansion rate, this exact measurement was feasible. The WMAP mission contributed to the application and refinement of the Hubble constant calculations, which quantify the expansion rate of the universe, by providing insight into these irregularities. The results from WMAP also had a major effect on how we think about the building blocks of the cosmos, greatly affected how we see the makeup of the cosmos. The WMAP results strongly indicate that the cosmos is flat because they measure the curvature of the universe using the CMB data. The total density of matter and energy in the universe is approaching the threshold density required to stop its expansion, according to a flat universe theory. According to what the probe found, the mass-energy content of the cosmos is made up of a mere 6% ordinary matter, which includes everything from stars and planets to galaxies. Understanding the development and evolution of cosmic structures is affected by this more exact measurement compared to earlier estimations. In addition, WMAP supplied precise data that proved the presence and development of cosmic structures. Dark matter is an unseen material that does not release light or energy. WMAP also gave precise measurements proving its existence and amount. Gravitational forces that bind galaxies together are helped to explain by dark matter, which, according to WMAP, makes up around 24% of the universe. Most importantly, WMAP data confirmed that dark energy, an enigmatic factor, is the primary driver of the universe's accelerating expansion. Aligning with and improving upon earlier findings from supernovae investigations, WMAP determined that dark energy constitutes about 71.4% of the universe. The polarization of the cosmic microwave background was measured as part of the probe's CMB study, which improved estimates of the overall energy content and distribution in the cosmos. Additional information on the expansion rate and early phases of the cosmos was revealed by this polarization measurements. The basic theoretical model of cosmology, the lambda-cold dark matter model, was fine-tuned with the use of WMAP data, which provided a thorough mapping of sky temperature changes. In this model, the amounts of dark energy, dark matter, and regular matter have been precisely calculated. Additionally, WMAP clarified the ionization era, when the first stellar and galactic ionization of the medium took place. Relative to prior estimations, WMAP's analysis of polarization and temperature data indicated that ionization happened around 400 million years after the Big Bang. The WMAP results were applicable to the inflationary model of the cosmos. Patterns in the cosmic microwave background variations were in agreement with inflationary predictions, lending credence to the idea that the cosmos expanded rapidly in the early post-Big Bang period. Additionally, the cosmological principle that, when seen from a great enough distance, the universe is homogeneous and isotropic, has been strongly backed by WMAP's precise cosmic measurements. With its groundbreaking discoveries, WMAP laid the groundwork for several theoretical models and opened up new avenues of investigation into the universe's basic structure, leaving an indelible mark on cosmology. To sum up, WMAP has not only helped us better comprehend the age and makeup of the universe, but it has also provided us with a better grasp of the physical mechanisms that have driven its development from the Big Bang to the current day. The work of WMAP has laid the groundwork for further investigations into the cosmos, and its legacy is still having an impact on modern astronomy. Our knowledge of the cosmos is now more complete and coherent thanks to its discoveries. In 2009, the European Space Agency launched the Planck satellite to carry on the investigation of the cosmic microwave background that had begun with missions such as COBE and WMAP. Planck hoped to improve our knowledge of the universe's makeup and development by providing a more precise picture of the cosmic microwave background using more sophisticated equipment. With its improved sensitivity and resolution, Planck was able to study the CMB across a broader spectrum of microwave frequencies than its forerunners. Planck was able to measure the CMB temperature and polarization with hitherto unseen accuracy because of this capabilities. The validation and enhancement of cosmological models developed by previous missions was a key objective of Planck. The parameters of the lambda cold dark matter model, the mainstream model of cosmology, were constrained by the more accurate data provided by Planck. The early universe's inflationary phase was better understood because to Planck's measurements. According to the satellite's findings, the cosmos saw a quick expansion in the instant after the Big Bang, which accounted for the homogeneity of our modern universe by eliminating any anomalies. Furthermore, the results obtained by Planck improved the measurements of the cosmic microwave background anisotropies, which are small temperature changes that are the precursors of future cosmic structure. It is impossible to comprehend the early universe's matter and energy distribution without these precise observations. Two of the most enigmatic aspects of the cosmos, dark energy and dark matter, were also extensively studied thanks to Planck's work. They had an impact on the structure and expansion pace of the cosmos, and the data from the satellite helped to explain it. By detecting several irregularities in the CMB that were not anticipated by conventional cosmological theories, Planck's measurements cast doubt on some parts of the inflationary model. Among these irregularities were a larger than anticipated cold spot and a little asymmetry in the CMB's temperature distribution over the sky. With the help of Planck's meticulous maps, astronomers were able to more precisely trace the history of the universe from the Big Bang up to the current day. Theories about the expansion pace of the universe and the creation of cosmic structures must be tested using this all-encompassing vision. Our knowledge of the cosmic neutrino background and the number of neutrino species, which are crucial to the thermal history of the universe, was also improved by Planck's mission. The fields of cosmology and particle physics both benefited greatly from this development. The cosmic infrared background radiation, which reveals details about the first stars and galaxies, was also studied by Planck. New information on the development of stars and the emergence of massive structures in the cosmos was uncovered by these investigations. There is a lot of information available in the Planck satellite's data archive, which has become an invaluable resource for scientists throughout the globe. This data is being used in a variety of research initiatives. There have been talks and new research focused on finding a solution to the tiny but considerable differences between observations and model predictions, since Planck's results have forced some changes to the theoretical framework of cosmology. Not only did Planck have an impression on cosmology, but also on astrophysics and basic physics. Theories about gravity and the basic forces of nature have been impacted by the mission's increased knowledge of the cosmos. Finally, the Planck spacecraft has greatly improved our understanding of the early cosmos and the cosmic microwave background. Our cosmic models have been revised, current ideas have been questioned, and new pathways for understanding the most basic components of the universe have been opened by its exact observations. The Planck success story highlights the significance of ongoing technical development and global collaboration in our pursuit of cosmic exploration and the discovery of its secrets. The goal of the Planck mission was to probe the cosmic microwave background more thoroughly than any other satellite, including WMAP and COBE before it. In order to provide a clearer picture of the first light in the cosmos, its designers prioritized obtaining high sensitivity and angular resolution over a larger frequency range. In comparison to earlier probes, Planck's capacity to monitor the CMB over 9 distinct frequency bands was a major advance. Planck was able to successfully isolate the CMB signal from background emissions from sources inside our galaxy, including as dust and synchrotron radiation within this range. Both the low-frequency instrument, which covered 3070 GHz, and the high-frequency instrument, which spanned 857 GHz, were the principal scientific instruments at Planck. This configuration improved the precision of cosmological observations by covering a wider spectrum than WMAP's 5 frequency bands. In order to reduce background noise and increase sensitivity, the equipment on board the satellite were chilled to almost room temperature. For instance, In order to get very accurate readings of the CMB's minute temperature variations, the HFI was chilled to a level barely 0, 1 degrees above absolute zero, which was the lowest temperature ever reached in space at the time. Planck's improved angular resolution made it possible for it to detect celestial objects as tiny as 1/10 of a degree, roughly twice the size of the full moon, on the sky. With this capacity, Planck was able to detect more nuanced variations in the CMB than WMAP, which led to new discoveries about the early universe's characteristics. We now have a better grasp of the early universe's mechanics and its composition, thanks to Planck's accurate observations, which have also placed more severe limits on the parameters of the lambda cold dark matter hypothesis. The Hubble constant, dark matter density, and dark energy density are all examples of such quantities. Our understanding of the age of the universe was further enhanced by Planck, who provided a more precise estimate of 13.8 billion years. This correction was derived from more exact measurements of the cosmic microwave background, anisotropies, and the general cosmic bending radius. Planck enriched our knowledge of the early cosmos by unveiling the CMB's polarization in more detail. Planck made substantial contributions to the fields of cosmology and inflationary physics, and polarization measurements are particularly sensitive to these histories. In addition, scientists were able to thoroughly evaluate ideas of cosmic inflation using Planck's data. All future structure building was seeded by quantum fluctuations in the early cosmos, according to the most basic inflation theories, which the observations were in agreement with. Additional information on temperature field abnormalities in the CMB was also uncovered by the mission. Characteristics like as the cold spot and a small degree of temperature imbalance were among them, and they posed ongoing challenges to the prevailing cosmological paradigm and motivated new theoretical investigations. In order to better understand how structures in the universe were formed, Planck was able to detect the isotropic background light that was not connected with stars. This light came from the very beginning of star formation. The satellite's findings solidified our knowledge of the timing for the universe's first reionization, which occurred around 550 million years after the Big Bang. The spectral index of primordial fluctuations was refined by Planck's results, which helped to alter the size of cosmic disturbances. The structure of the universe was formed by density fluctuations, and this measurement is essential for comprehending those fluctuations, potentially leading to new insights into topics like the composition of dark matter and neutrino characteristics. The Planck mission produced a plethora of data that is still being studied. In conclusion, the cosmic microwave background research community may look forward to Planck's mission as a giant leap forward. We learned more about the characteristics of the cosmos's foundations than with earlier probes, because to its superior sensors and wider frequency coverage, which mapped the early universe more thoroughly and precisely. The early cosmos, and cosmic inflation in particular, were illuminated by Planck's meticulous measurements of the cosmic microwave background. These discoveries have contributed to a better understanding of the early universe's evolution. According to the hypothesis of cosmic inflation, the cosmos expanded exponentially in the seconds after the Big Bang. The expansion evened out the universe's attributes at the biggest scales and eliminated any imperfections. Among the important predictions of inflationary theory that Planck's data verified was the almost complete scale invariance of the CMB temperature variations. Includes the almost complete scale invariance of the cosmic microwave background, CMB temperature variations. This feature, which is typical of the inflationary hypothesis, shows that the fluctuations in the primordial gas were constant at various sizes. Additionally, the satellite recorded spectral tilt, which refers to the small departures from complete scale invariance. The most basic inflation theories predict that the density fluctuations of the early cosmos were not uniform across all scales. Our discovery lends credence to that prediction. Data collected by Planck also provide credence to the idea that, some 550 million years after the Big Bang, the cosmos began to reionize. The irregularities seen in earlier CMB data were also resolved by Planck's findings, including the somewhat bigger temperature variations at large angular scales. Although the exact causes of these abnormalities are yet unknown, the high-precision measurements collected by Planck have been critical in ruling out cosmic variations and new physics as possible explanations. The verification of gravitational lensing in the CMB was one of the interesting parts of Planck's results. The bending of cosmic microwave background, CMB, photons by large objects causes this effect, which in turn provides evidence for the existence of dark matter and helps to map the distribution of mass in the universe. The quantity of relativistic species, like neutrinos, in the early cosmos is likewise limited by the comprehensive Planck data. This presents a crucial connection between cosmology and elementary particles, which has consequences for the field of particle physics. The energy scale of inflation has been constrained more strictly by Planck's results, implying a lower energy level than some earlier estimations. High energy scale predictions of the unification theories of the basic forces are affected by this. Alternatives to the traditional model of inflation, which postulates various behaviors for inflation at different periods or under different situations, have also been tested using Planck's data. A more precise measurement of the optical depth owing to reionization, a measure of the thickness of the cosmic fog of ionized photons, was achieved by the satellite's extensive investigation of the cosmic microwave background, CMB. The time and process of reionization may be better understood using this measurement. The isotropy of the cosmic microwave background, CMB, has been better understood thanks to Planck's results. Although the cosmos is uniform on a broad scale, Planck verified the existence of statistically significant anisotropies that need a re-evaluation of existing cosmological theories. One area where Planck's mission has weighed in is the ongoing discussion over the precise nature of the universe's structure. The data it provides is so precise that it challenges cosmologists to refine their theories and measuring methods. However, it does indicate a flat universe. Numerous investigations have been prompted by the abundance of data from Planck, which will remain an essential component of cosmological study. Its impact will last as long as our cosmological models are studied and improved. Last but not least, the Planck satellite has helped us comprehend the cosmic microwave background, CMB, and cosmic inflation more better, which in turn has helped us answer basic questions about the early universe, its composition, and its ultimate destiny. Observations of the cosmic microwave background, CMB, have given us a plethora of evidence that has drastically altered our conception of the early cosmos. The evolution of the universe from its early stages into the complex cosmos we see today may be better understood with the help of these new findings. A record of a period not long after the Big Bang, when the universe went from being opaque to being see-through. The cosmic microwave background, CMB, provides a glimpse into the early days of our cosmos. During this time, the cosmic microwave background, CMB, was formed by the emission of photons, which gave us a first-hand look into the state of the universe back then. Analysis of the CMB's minor imperfections is an important part of understanding the early cosmos. All cosmic formations from galaxies to large-scale superclusters were formed as a result of density fluctuations, as these temperature anisotropies indicate. Inflation, a fast expansion believed to have happened a fraction of a second after the Big Bang, is another topic that has to be explored in order to understand the early cosmos. This idea resolves several issues with the Big Bang scenario and provides an explanation for the flatness and homogeneity of the cosmos. The cosmological principle states that the world seems uniform when seen from a wide distance, and data from several cosmic microwave background (CMB) investigations have provided support for the hypothesis that the early cosmos was very homogeneous and isotropic. We can learn more about the early cosmos from the polarization patterns seen in the cosmic microwave background, CMB. Potentially providing a glimpse into quantum gravitational phenomena, these patterns are shaped by gravitational waves, which are disturbances in space-time that would have been created during inflation. Further improvements in our understanding of the early universe's matter and energy composition have resulted from CMB studies. For example, accurate measurements of the cosmic microwave background, CMB, have shed light on the nature and quantity of dark energy and matter, which make up the bulk of the universe's density. Extremely precise measurements of the cosmic microwave background, CMB, temperature have allowed cosmologists to calculate the rate of expansion of the universe from its inception, and this temperature is quite uniform throughout the sky. A reionization era occurred around 550 million years after the Big Bang, according to cosmological models that have been fine-tuned using cosmic microwave background, CMB, data. As the first stars burst into flame, they released enough energy to ionize the medium around them. Prior to this, the medium had cooled and created neutral atoms via recombination. We can learn more about the basic forces and particles that were at work in the early cosmos, thanks to the CMB data. Understanding how the early cosmos functioned as a natural accelerator for particles and combining cosmology with particle physics depend on this. Additionally, our knowledge of the cosmic microwave background, CMB, is heavily related to nucleosynthesis, the creation of light components in the early cosmos. It is consistent with predictions derived from the CMB's temperature and density conditions that the relative abundances of hydrogen, helium, and lithium as seen today are accurate. Standard cosmological models fail to anticipate abnormalities and inconsistencies in the cosmic microwave background, CMB, which poses a challenge to scientists trying to understand the early cosmos. Some asymmetry and cold patches may indicate novel physics or complicated, as yet ununderstood occurrences. We should expect to learn more about the early cosmos as CMB observational equipment and methodologies continue to advance. In order to learn more about the early cosmic circumstances, future missions will try to measure the CMB even more precisely. In addition to creating a picture of the universe's past, cosmologists are pushing the boundaries of physical laws in an environment that no Earth laboratory can match by putting together this data. Overall, as more evidence becomes available, our knowledge of the early cosmos, which is mostly based on the CMB, is constantly changing. Our understanding of the universe's origins and evolution over the course of billions of years is being further refined with each new finding. Crucial to cosmology, studies of the cosmic microwave background show what the cosmos looked like 380,000 years after the Big Bang, long before galaxies and stars were born. An era when the universe looked quite different from what it does now is shown in this image. The cosmos was originally hot and dense, as the regularity of the cosmic microwave background, with its small fluctuations, confirms the Big Bang idea. The study of this afterglow provides a basic picture of the early moments of the cosmos, since it is a glow that permeates the whole universe and was left behind when the cosmos expanded. The cosmic microwave background temperature variations are very important since they are the building blocks of everything in the cosmos right now. When galaxies and other large-scale structures were being formed by gravity, these minute changes in density were crucial. Due to the accurate measurement of these fluctuations by missions such as COBE, BUMAPI, and Planck, cosmologists have been able to infer the composition of the universe, including the relative amounts of normal matter, dark matter, and dark energy, as well as the age of the universe and the rate of its expansion. The inflationary idea, which states that the cosmos experienced a fast exponential growth in the initial minuscule fraction of a second, has also been supported by CMB research. This hypothesis not only forecasts the statistical pattern of temperature changes seen in the CMB, but it also explains the flatness and homogeneity of the cosmos. By putting several inflation ideas to the test using the scale-dependent oscillations in the CMB, scientists have learned not only when inflation happened, but also how and why it was driven. Important for linking the physics of subatomic particles with those of cosmic objects like galaxies. The cosmological premise that the cosmos is homogeneous and isotropic on vast scales has been further clarified by CMB studies. A prominent evidence for this concept is the uniformity of the cosmic microwave background throughout the sky, which implies that the same physical rules are applicable everywhere in the cosmos. Scientists may learn more about the reionization of the early cosmos via polarization studies, which look at how electrons scattered light from the cosmic microwave background. Following the recombination phase, the neutral hydrogen existent in the cosmos was ionized during this era by the first stars and galaxies. In addition, gravitational lensing effects, which include the bending of CMB light around large objects, have been extensively studied with the use of CMB data. Indirectly supporting the existence of dark matter, this occurrence aids in the distribution of mass across the cosmos. The cosmic microwave background is also used to estimate the velocity of our local group of galaxies. This sheds light on the motion of our galaxy across space and gives background for the strange phenomena in our cosmic surroundings. Research into the cosmic microwave background may provide light on the early cosmos and put gravity theory to the test, among other things. If there are discrepancies in the cosmic microwave background data, it might be a sign of physics that goes beyond the current particle physics and cosmology models, which could lead to new research. Combining cosmic microwave background data with other astronomical observations, such as galaxy surveys, improves our knowledge of cosmic development from the early universe to the present, painting a whole picture of cosmic past and present. When dealing with cosmic background radiation abnormalities and irregularities, this cooperation between CMB measurements and other cosmological data is crucial. This might lead to the discovery of hitherto unknown facets of the cosmos, which in turn could cast doubt on long-held beliefs and propose new physical laws. As our understanding of the cosmic microwave background grows, we are able to test long-held assumptions and propose novel physical laws. We are getting closer to the answers to the most basic questions about the cosmos with each new development in CMB research. What gave rise to it? Could you tell me what materials it is composed of? How does it intend to change over time? Our knowledge of the universe and the governing rules of physics are both enhanced by these investigations. Finally, understanding the universe and the governing rules of physics requires investigations of the cosmic microwave background. Finally, CMB investigations are crucial for building a complete picture of the early universe, since they provide a glimpse into the past that lets us piece together the universe's development and history with incredible accuracy. According to cosmic inflation, the cosmos expanded exponentially quickly after the Big Bang, which explains why the cosmos is so flat and uniform. The cosmic microwave background that we can see now is a reflection of this phase, which flattened out the early cosmos and dispersed energy evenly. Inflation is the direct cause of the small temperature variations in the CMB. These variations stand for the original tiny density abnormalities in the cosmos that inflation blew out of all proportion. All of the formations in the universe, from galaxies to clusters and superclusters, have formed as a result of cosmic evolution driven by gravity, and these objects provide a rare glimpse into this early stage of cosmic history. To comprehend the emergence of complex structures from a quite homogeneous initial state, one must examine the intricate pattern of these oscillations as recorded by the cosmic microwave background. Examining the mechanics of the early cosmos is also a part of studying inflation, which may have connections to quantum gravity theories. By studying the scale dependence of the CMB variations, which reveal the relative expansion of various space areas, we may get insights regarding inflation. More information regarding inflation may be derived from the polarization of the cosmic microwave background, which has been detected by Planck and other spacecraft. Light was scattered in the early cosmos, which led to polarization, which in turn may be affected by gravitational waves, which are ripples in space-time that are created during inflation. Another phenomena examined via these studies is the gravitational lensing of the cosmic microwave background. This helps to map the distribution of all matter in the universe, including dark matter, which does not produce light. Thanks to this lensing effect, we now know that massive structures developed from tiny inflationary oscillations that persisted for billions of years. Observations of the cosmic microwave background corroborate the almost Gaussian distribution of temperature variations predicted by cosmic inflation. The inflationary hypothesis has substantial support from both theory and observation. Nevertheless, cosmologists still don't have a good answer for the precise process that causes inflation. Ongoing study and controversy surround the energy scale of inflation, which is believed to be connected to the potential of the inflatant field. The expansion of perturbations was caused by the gravitational pull of matter as structures evolved throughout the cosmos. As time passed, overdense areas absorbed more matter and grew in size, while underdense areas emptied out. Consistent with CMB measurements, this mechanism is supported by simulations. One of the most important factors in the expansion of the universe is the interaction between dark and regular matter. By gravitationally drawing in ordinary matter, dark matter, which does not interact with electromagnetic forces, forms the framework of clusters and galaxies. Some anisotropies and cold patches, which are not predicted by typical inflationary theories, may be present, according to advanced CMB investigations. Based on these characteristics, we may be able to extrapolate more complex inflationary models that include many fields and interactions. Our knowledge of inflation is intimately related to Big Bang nucleosynthesis, the process by which light components were created in the early cosmos. Cosmologists continue to study the cosmic microwave background, CMB, and its implications for cosmic inflation and structure growth in the hopes of answering basic questions about the universe, like why it looks uniform on large scales, and what drove its initial expansion. The relative abundances of light elements, such as hydrogen, helium, and others, are determined by inflation and are consistent with CMB measurements. Future observations and experiments will investigate the CMB's division further in order to detect signs of gravitational waves from inflation. If such findings are made, they could serve as the smoking gun testimony for inflation and provide light on the energy scale at which inflation occurred. Last but not least, cosmic microwave background, CMB research, has shed light on cosmic inflation and the expansion of cosmic structures, which has improved our knowledge of the early cosmos and kept our theories of cosmic development in flux, helped us better comprehend the early universe and its fundamental structure, but it also uncovered a number of strange phenomena that cast doubt on our current cosmological theories. The scientific community is captivated by these unusual findings, which prompt vigorous discussion and investigation. The cold spot is a highly discussed anomaly. It is a huge, out-of-the-ordinary region on the CMB map that is far colder than its neighbors. Some have argued that this is just a statistical fluke, while others have proposed more outlandish explanations, such as the impact of a parallel world within the framework of the multiverse paradigm. The fact that the ecliptic plane coincides with the greater scales of the CMB temperature changes is another strange occurrence. The traditional cosmological model cannot account for this alignment, which implies that the universe's isotropy is violated, or that some other unknown cause is at work. Another feature of the cosmic microwave background, CMB, is its hemispherical asymmetry, which makes temperature variations seem more pronounced in one sky half compared to the other. Because of this imbalance, the cosmological principle that states the cosmos should be uniform in size and shape is called into question. We find that the CMB temperature anisotropies quadrupole and octupole moments are less than predicted by theoretical models based on inflationary cosmology. Unexpected values of these moments cause cosmological theory modifications, yet they are critical for comprehending the universe's shape and substance. Aspects such as the so-called axis of evil also perplex astronomers. The data seems to show an odd correlation between the solar system's velocity and orientation and the biggest patterns of CMB temperature anisotropy, which goes against the expectation that the CMB should be uniform in all directions. What these outliers mean is rather significant. They may propose changes to the theory of inflation and other parts of the standard model of cosmology. They could also suggest previously unrecognized physical principles that have not been included in the current framework. These outliers are still there in the data from various CMB observations, even after all the research. The traits seem to be more than merely instrumental faults or data processing aberrations, which adds to the interest, since they are consistent over numerous trips. These outliers, according to some cosmologists, point to a cosmos that is more complicated than what our current model predicts. They might point to altered gravity or early universe expansion theories, interactions with other universes, or previously unexplained matter or energy forms. We need new theoretical frameworks and more accurate data to solve these issues. Constantly expanding the frontiers of astronomy and physics, new models and theories are being refined and tested. Resolving or further probing these abnormalities is the goal of future CMB observing missions. Either these outliers will be shown to be significant, or they will be attributed to statistical variances, thanks to improved measuring methods and new technology. Looking at these outliers also shows how cosmology is related to other branches of physics. The fact that developments in particle physics, quantum mechanics, and general relativity may be required to comprehend them highlights the interdisciplinary character of cosmological research. If these outliers can be included into a unified theory, it may result in a rethinking of the cosmos on par with the transition from Earth-centric to heliocentric theories at the dawn of astronomy. As cosmologists continue to probe these enigmas, the significance of dark energy, dark matter, and maybe other undiscovered cosmic components grows. The observed abnormalities in the CMB could be best explained by these components. All things considered, the cosmic microwave background studies unexplained phenomena and riddles present a rich environment for future research. They make us question what we already know, motivate us to dig more into the universe, and ultimately further our quest for a complete comprehension of it all. The axis of evil is a fascinating alignment of the solar system's plane with the biggest scales of the cosmic microwave background, CMB anisotropies. The cosmological principle states that the universe should be isotropic and homogeneous, yet its surprising alignment casts doubt on that assumption and may point to a cosmic preference. Data from the Wilkinson Microwave Anisotropy Probe, WMAP, were the first to detect this anomaly, and further observations by the Planck spacecraft verified it. This feature's consistency across CMB research suggests a major departure from the traditional cosmology model, which may point to novel physics or the need to reevaluate our knowledge of the large-scale structure of the universe. According to certain theories, the axis of evil may represent a number of different possibilities. Cosmologists have speculated that this might point to the potential impact of other worlds in a multiverse theory. On the other hand, others think it may be the product of some mysterious early universe physical event, or even a basic error in our knowledge of the physical laws. The cold spot, a huge area of the cosmic microwave background, CMB sky that is far colder than predicted, is another prominent outlier in the CMB dataset, alongside the axis of evil. People are talking about where this trait came from, and if it's related to supervoid structures, or whether it's just a statistical anomaly. The scale-dependent damping tail in the CMB power spectrum is another oddity. It suppresses the amplitude of fluctuations more than the mainstream cosmological model predicts, potentially including neutrinos and other dark sector particles in their interactions. This suppression may suggest physics beyond the standard model. Another concern is hemispherical asymmetry, which means that there seems to be larger temperature swings in one half of the CMB sky compared to the other. This casts doubt on the idea that on cosmic scales, the universe ought to seem uniform in all directions, and may point to novel processes during the inflationary era of the early cosmos. These outliers have great significance since they may provide glimpses into the fundamental structure of the universe. Theorists are compelled to reevaluate and rethink basic assumptions about the homogeneity of the cosmos, inflation, dark matter, and dark energy. In order to make sense of these outliers, researchers use sophisticated statistical tools to find out whether these characteristics are signs of novel physics or just the result of data processing mistakes or contamination in the background. Data analysis techniques or artifacts of background pollution. For the ramifications of the CMB to be better understood, this kind of careful analysis is necessary. More accurate results should be forthcoming from CMB observing experiments and missions like the Simons Observatory and the CMBS-4 project. By making these observations, we may learn if these abnormalities are statistically significant enough to be attributed to observational biases or whether they have a cosmic cause. Integrating ideas from particle physics, quantum field theory, and general relativity, the continuing discussion around these anomalies emphasizes the need for multidisciplinary methods in cosmology. In order to build a more comprehensive theory that can explain all cosmic occurrences, this integration is vital. Researchers improve computational techniques and theoretical models while also challenging current paradigms by delving into these outliers. Every anomaly adds a piece to the cosmic evolution jigsaw, providing hints that might lead to discoveries about space, time, and matter. Tackling these CMB outliers involves thinking about the philosophical ramifications of finding out the universe could not be as uniform as previously believed, in addition to making adjustments to cosmological models. Our position in the universe and the nature of reality at large are profoundly affected by these discoveries. The axis of evil and other cosmic microwave background (CMB) anomalies are still hotly debated topics, which is typical of the ever-changing nature of scientific research. More questions are raised with every solution. These conversations inspire a never-ending quest for knowledge by prompting us to reevaluate our assumptions about the cosmos. Further investigation into these outliers may reveal that they hold the secrets to hitherto unexplored areas of physics, opening the door to a cosmic rethinking on par with the original discovery of the cosmic microwave background, CMB. To summarize, investigating these outliers is a key step in expanding our understanding of the cosmos. It compels researchers to question established assumptions in the hopes of elucidating the universe's origins, basic forces, and ultimate destiny. A number of competing hypotheses, some of which introduce new physics and others which modify current cosmological models, have been put forth to account for the abnormalities seen in the cosmic microwave background, CMB. All of these competing theories attempt to explain these out-of-the-ordinary results while maintaining the advantages of the current cosmological model. A cosmic texture, a remnant of phase transitions in the early cosmos, may be the cause of the axis of evil and other large-scale oddities, according to one idea. The alignment with the ecliptic may be explained by the non-uniformities introduced by these textures, which may have acted as seeds for the anisotropies seen in the CMB. Topological flaws in spacetime, like cosmic threads, might be another explanation for the oddities, according to another theory. Interacting with inflationary perturbations, these flaws, predicted by some early universe models, could cause CMB disruptions. The cold spot and hemispherical asymmetry are seen by some to be signs of an unconventional inflationary hypothesis. One possible variant in these ideas is a more uneven expansion of the cosmos as a result of inflation that happened at various speeds in different regions. Some of the CMB anomalies have been proposed to be explained by modified gravity theories. Different patterns of fluctuation in the early cosmos might result from these hypotheses, which change Einstein's general relativity at cosmic scales. Some of the strange occurrences may be explained by the existence of parallel universes. Our visible universe might be only one among several in this scenario, each with its own unique set of physical constants and characteristics. We may be able to discover traces of these universes' collisions or interactions in the cosmic microwave background, CMB. Another possible explanation is quantum entanglement on a galactic scale. According to this idea, anomalous correlations in the CMB temperature field might have their origins in large-scale quantum events that occurred in the early cosmos. One possible explanation is the function of dark flow, which is the gravitational pull of things beyond the visible universe on galaxy clusters on a massive scale. The CMB anisotropies might be affected by this movement, which could distort the distribution of matter and energy. The function of dark energy and how it may change throughout space and time is another topic of study. Inconsistencies in the expansion rate, as seen in the cosmic microwave background, CMB, may result if dark energy was not a constant, but changed during the universe's history. An anisotropic world, in which the rules of physics could vary somewhat in various directions, is a more contentious hypothesis. This may have originated from the observed abnormalities being the result of less than uniform beginning circumstances in the early cosmos. Also taken into account are the effects of astronomical objects that cannot be seen, such as supervoids or huge clusters. These gigantic objects may cause anomalies like the cold spot by gravitational lensing CMB photons that go through or around them. While the cosmos is mostly uniform, statistical flukes imply that the CMB may exhibit seemingly random patterns or characteristics that may or may not have profound cosmic relevance. Another possible explanation is the integrated Sachs-Wolf effect, which is based on the interaction of cosmic microwave background, CMB photons with gravitational fields that evolve over time. Additional variations in the CMB may be caused by this phenomenon when photons travel through potential wells of different depths. Simulations of the early cosmos that include the intricate physics of the plasma and its interaction with radiation imply that some irregularities may emerge organically from intricate dynamics that were absent from less comprehensive models. We will be able to examine the hypotheses put out to account for these outliers with more precision and data as observational methods advance. Understanding the cosmos and its underlying rules requires a continuous back and forth between theory and observation. There are a number of ambitious next-generation studies that are going to revolutionize the future of CMB research. These endeavors will push the limits of our present cosmological models and seek to answer unanswered issues in an effort to deepen our knowledge of the cosmos. The Simons Observatory is one such endeavor. It is a ground-based effort with the goal of improving upon earlier results by measuring the temperature and polarization of the cosmic microwave background, CMB, with greater accuracy. The specifics of cosmic inflation, neutrinos, dark matter, and dark energy will be the primary areas of study for the observatory. There has been yet another giant stride forward with the CMB-S4 project. The goal of this joint venture is to spread hundreds of thousands of detectors out across various high-altitude locations. By analyzing the most weak signals from the early cosmos, it hopes to build the most comprehensive map of the cosmic microwave background, CMB, to date, which will provide light on inflation and the universe's particle concentration. In the 2020s, the Japanese-led Lightbird project will launch its satellite with the goal of measuring the CMB polarization throughout the sky. A possible smoking gun signal of inflation might be found in the B-mode polarization pattern, which is closely associated with gravitational waves from the inflationary period. Additional capabilities to explore the CMB's fine characteristics are being added to the Atacama Cosmology Telescope, ACT, via ongoing upgrades. With these improvements, we hope to get a better read on the Sunyaev-Zeldovich effect, which reveals details about galaxy clusters and the universe's large-scale structure. This new era of cosmic microwave background research also include the South Pole Telescope. With a newly upgraded camera that makes it far more sensitive, the telescope is now able to study the cold dark matter, CMB, polarization in great detail, which will provide light on the early universe's dynamics and the reionization process. Modern technological developments, such as more sensitive detectors, wider frequency coverage, and better polarization capabilities, provide the basis for each of these studies. Minimizing noise and distinguishing the CMB signal from foreground emissions are made much easier with these technological advancements. Importantly, data from these different next-generation trials must be integrated. The goal of cosmologists' efforts to integrate data from many sources is to cross-verify results and lower data uncertainties. Additionally, the small-scale anisotropies in the CMB will be investigated in greater detail by these investigations. The development and structure of the cosmos may be better understood by examining these finer features, which provide light on the interactions of cosmic microwave background, CMB photons with intervening matter. In addition, the enigma of dark energy will be further investigated by the subsequent CMB experiments. In order to test hypotheses on the characteristics and effects of dark energy on the expansion of the universe, these studies will trace the distribution and historical development of cosmic structures. In addition to testing the boundaries of the mainstream cosmological model, these initiatives may reveal previously unknown physical phenomena. Their goal is to find new particles, forces, or dimensions by expanding the boundaries of what can be seen in the cosmic microwave background, CMB. Along with these experimental breakthroughs, efforts will be made to enhance data analysis approaches. In order to sift through the massive volumes of data that these studies are likely to produce, sophisticated statistical approaches and machine learning will be essential tools for discovering hidden relationships and patterns. One distinguishing feature of these next-generation CMB initiatives is the global cooperation. By pooling knowledge, assets, and information from all across the globe, these joint ventures expand the breadth and depth of cosmological studies. Additionally, these initiatives have a substantial educational effect. They play an important role in advancing knowledge in astronomy, physics, and related disciplines, and they also provide opportunities for students to learn these disciplines. In conclusion, next-generation studies will continue to study the cosmic microwave background, CMB, which will expand our knowledge of the early universe, answer basic cosmic problems, and pave the way for new discoveries in cosmology. Looking forward, a number of planned missions and cutting-edge technology will greatly improve studies of the cosmic microwave background. Through these endeavors, we hope to learn more about the early universe and the basic mechanisms that have influenced its development. Launch of the LightBird satellite by JAXA and international partners is one of the most talked about missions. The goal of LightBird is to identify the cosmic microwave background's primordial B-mode polarization. The polarization signature is associated with gravitational waves produced by cosmic inflation, which may provide light on the rapid expansion of the cosmos immediately after the Big Bang. The Simons Observatory, situated in the Atacama Desert of Chile, is another important project in the pipeline. In order to explore the CMB with unprecedented accuracy, this observatory will integrate the capabilities of many telescopes. More precise signs of the dynamics of the early cosmos will be produced by its state-of-the-art equipment, which attempts to enhance measurements of the E-mode and B-mode polarization, making the dynamics of the early cosmos more clearly visible. The next big thing in observational cosmology is the CMBS-4, which is the fourth ground-based CMB experiment. All across the globe at great altitudes will be set up this massive array of telescopes and ultra-sensitive detectors. To better understand dark energy and neutrino physics, CMBS-4 will probe the CMB anisotropies and polarization in more detail. The core mission, which is being planned by the European Space Agency, ESA, is an additional lofty endeavor with the goal of accurately mapping the CMB's polarization across a broad frequency spectrum. By taking a holistic view, CORE hopes to answer important cosmological puzzles about anything from the nature of inflation to the characteristics of the most basic particles. New detection technologies are radically altering the field of cosmic microwave background, CMB research. More sensitive and less noisy new superconducting detectors like kinetic inductance detectors and transition edge sensors are enabling more accurate measurements of the weak signals from the cosmic microwave background, CMB. These detectors can now be read out in bulk because to advancements in multiplexing methods, which greatly increases the quantity of data that can be gathered and analyzed. Future large-scale CMB investigations, expected to use tens of thousands of detectors, will depend on this scalability. One such field where technology has advanced is digital signal processing. The massive data volumes produced by contemporary CMB investigations need data processing methods that are both faster and more efficient. The capacity to remove background signals and noise has also been improved by these developments, which speed up data processing. To manage the complicated data analytic requirements of CMB research, new software frameworks are also being created. These tools are built to handle a wide variety of data formats, gathered from various experiments and sensors. They are durable and versatile. New prospects for space-based CMB observations are opening up as a result of cost reductions brought about by improvements in satellite technology and launch capabilities. In order to reduce atmospheric interference and have a clean picture of the CMB throughout the sky, these missions are crucial. In the field of cosmic microwave background, CMB research, balloon-borne studies like SPIDER and EBEX are still very important. These missions have the capability to send equipment to the periphery of space, offering a budget-friendly way to gather top-notch data with little interference from the atmosphere. There are new approaches to measure the fine-scale structure of the CMB thanks to the advancements in interferometry techniques used in CMB research. By separating the signal from cosmic background and other microwave radiation sources, these methods may improve the clarity of the data. More and more, people from all over the world are working together, sharing knowledge and resources. Not only are scientists from all around the world working together to solve the universe's riddles, but they are also combining their financial and technical resources. These prospective missions also include public involvement and educational outreach. Projects like this hope to pique more people's interest in cosmology and science in general by bringing people together and teaching the future generation. Finally, forthcoming missions and new technology should allow CMB studies to continue expanding our knowledge of the cosmos. By delving farther into the universe's most basic energies and components, these endeavors aim to reveal its mysteries. New discoveries in the field of cosmic microwave background, CMB research, could change the way we see the cosmos forever. With each new theoretical and technological development, we get closer to solving the most basic cosmic mysteries. Finding the B-mode polarization patterns in the cosmic microwave background, CMB, is one of the hotly contested frontiers. Gravitational waves produced by cosmic inflation, a rapid expansion that happened a few hundredths of a second after the Big Bang, are seen in these patterns. By validating these signals, we may find the energy scale of inflation and have conclusive proof for it. Better observations of the CMB's fine-scale anisotropies might also lead to a major discovery. Insights on the nature of the quantum fields that powered inflation may be gleaned from these meticulous measurements, which might provide light on the kinds of fluctuations that happened in the early cosmos. An improved comprehension of ionization might be achieved with the exact mapping of CMB polarization. This may provide light on the timing of structure building in the cosmos and the function of dark matter in the production of cosmic structures when the first stars and galaxies ionized the universe some 550 million years after the Big Bang. Recent developments in cosmic microwave background, CMB, research have the ability to expand our neutrino understanding by illuminating the mass distribution and number of neutrino species. This data is fundamental for comprehending the role of neutrinos in cosmic structures and general universe dynamics. The enigmatic dark energy is another possible frontier for discovery. Future CMB measurements may provide light on its nature and potential development by analyzing its influence on cosmic structure evolution and the expansion rate of the universe. If telescope and detector technology continues to progress, new abnormalities in the cosmic microwave background, CMB data, may be found, which would cast doubt on current theories and maybe point to physics that goes beyond the mainstream cosmological model. Additional CMB explorations may help us better comprehend the Hubble tension, the disparity between various estimates of the pace of cosmic expansion. New ideas in astrophysical theory may emerge from this, or the current cosmological model may need to be rethought. These findings may potentially lead to a clearer picture of cosmic inflation. Scientists want to get a better understanding of the field that induced inflation and its possible links to other elementary particles and forces in physics by studying the CMB's specific characteristics. We anticipate a more complete picture of the cosmos as a result of merging CMB data with findings from other cosmological instruments like galaxy surveys and gravitational wave detectors. The evolution of the universe's large-scale structure may be better understood with the help of this synthesis. Research into the cosmic microwave background, CMB, has the potential to influence our knowledge of basic physics by either supporting or refuting ideas like string theory or general relativity with modifications, since these theories may be mirrored in the CMB's structure. A better grasp of the universe's early state, as shown by the cosmic microwave background, CMB, may also provide light on the universe's ultimate destiny. The characteristics of dark energy and matter may dictate whether it will collapse, continue expanding endlessly, or achieve a stable state. The CMB may potentially be a tool to explore the furthest reaches of the visible cosmos, if new technology make this possible. This may lead to uncharted territory in our understanding of the universe's boundaries and the nature of the universe beyond our visible spectrum. We might rethink the particle zoo in particle physics if we find previously unseen particles or fields that interact with the cosmic microwave background, CMB. This would add new dimensions to or significantly alter the standard model. Finally, advances in cosmic microwave background, CMB research, might lead to new insights into cosmology and closer ties to particle and astrophysical physics, as well as to theories of basic forces and matter. These findings have the potential to shape future scientific investigations, which will both test and broaden our understanding of the cosmos. Theoretical advances and new observational evidence, especially from investigations of the cosmic microwave background, CMB, are driving cosmology's ongoing evolution and enhancing our knowledge of the universe's most basic features. The evolution of inflationary theory is among the most noteworthy theoretical achievements of the last several years. To explain the cosmos's flatness and homogeneity, this concept suggests a fast-expanding phase immediately after the Big Bang. Identifying the specific quantum fields that cause inflation and exploring their possible relationships to other physical forces and particles is the main focus of current study. Dark energy, an enigmatic factor that is speeding up the expansion of the cosmos, is another important area of theoretical advancement. For the sake of explaining its characteristics and temporal behavior, theorists are investigating a number of hypotheses, among of which include quintessence and the cosmological constant. Additionally, dark matter remains an important area of theoretical investigation. We know that dark matter has gravitational effects, but we don't know what kind of particles it is. Weakly interacting massive particles, WIMPs, are one theory, while axions and sterile neutrinos are two more outlandish examples. A more unified model of cosmology is being built using CMB data integrated with other cosmological observations. In order to provide a unified picture of the structure and history of the cosmos, this synthesis integrates data from galaxy surveys, supernovae, and gravity waves. Theories involving extra dimensions and modifications to general relativity are being considered as potential solutions to the problems of quantum mechanics and the incompatibility of cosmological observations with Einstein's theory of relativity. The idea of a multiverse has recently gained popularity as a possible explanation for many phenomena, such as the values of the physical constants and the precise conditions required for life. According to this hypothesis, there are several universes in the cosmos, and each one has its own unique set of physical rules and constants. A new area of study, quantum cosmology, is expanding the scope of quantum mechanics to include the cosmos as a whole. As part of this effort, we must learn about the Big Bang and its immediate aftermath by analyzing the universe's wave function. Theory on the energy scales of the early universe is being driven by the possibility of detecting primordial gravitational waves via measurements of the cosmic microwave background, CMB polarization. This may provide light on unification theories that seek to unite all primary forces. Emerging from the continuing Hubble tension, new theoretical models are being developed to address the disparity in observations of the expansion rate of the cosmos. To account for this variation, these models investigate the possibility of additional particles or changes to the gravitational rules. Since neutrinos influence the expansion pace and structure creation of the cosmos, neutrino cosmology has also become an important component of theoretical advancements. Cosmology and particle physics promise to benefit greatly from an understanding of their mass and variety. Cosmological reionization research is providing fresh insights into the Big Bang and the origins of galaxies. Complicated models of star formation, galaxy history, and feedback loops are required to speculate on the ways in which these primordial objects impacted the expansion of the universe. Examining cosmic voids or vast empty areas in the cosmos is another fascinating theoretical advance. Current hypotheses about the distribution of matter and energy may be challenged by the information these gaps can provide on the characteristics of dark energy and the structure of the universe on a grand scale. Cosmic entropy and the arrow of time theories are investigating the effects of the expanding cosmos on time and complexity development. By bridging the gap between thermodynamics and cosmic expansion, these investigations provide light on the ultimate destiny of the cosmos. Finally, our knowledge of the cosmos is being drastically altered by the latest theoretical advances in cosmology. With every hypothesis that is refined and new information that is discovered, we get closer to understanding the beginnings and end of the universe and the fundamental questions that surround it. New cosmological models and theories are rapidly expanding our knowledge by filling in knowledge gaps and offering fresh perspectives on long-lived events. These advancements are changing the way we think about the universe and its basic workings. Modifying the conventional model of particle physics to account for dark matter is an intriguing area of theoretical study. New particles, postulated by theories like supersymmetry, might explain dark matter. They could be detectable either directly in subterranean experiments or indirectly by cosmic ray anomalies or other indirect ways. Models such as quintessence, which are dynamic scalar fields, are part of the growing body of literature on dark energy. These theories imply that, in contrast to the cosmological constant, the intensity of dark energy may vary throughout the course of the universe's history. Beyond the well-known 3 spatial dimensions and 1 temporal dimension, the search for additional dimensions is another uncharted territory in theoretical cosmology. String theory models suggest that these extra dimensions may account for the relative weakness of gravity and other basic forces. Our world may be a mere bubble amid a vast multiverse, according to the inflationary multiverse hypothesis, which is why it is gaining popularity. A possible solution to the fine-tuning issues in cosmology might be for each bubble to have its own unique set of physical laws, driven by its own unique rate of inflation. As an alternative to string theory that can account for the quantum features of gravity, loop quantum gravity is quickly gaining traction. In proposing a distinct structure of spacetime, it offers a framework for the Big Bang conditions and may even eliminate singularities. Another fresh perspective is the merging of cosmology and information theory. This viewpoint interprets the cosmos as an information processing system, which has consequences for our comprehension of the holographic principle and black hole thermodynamics. New models that include several inflationary scenarios, rather than simply one fast expansion, are also improving the understanding of cosmic inflation. These models include elements such as field potential fluctuations resulting to distinct observable fingerprints in the CMB or numerous fields driving inflation. The impact of quantum effects on cosmic structures in the early universe, especially quantum fluctuations, is a topic that cosmologists are delving into more and more. As part of this, we will investigate the mechanisms, such as quantum decoherence, that convert these fluctuations into macroscopic events. The dynamics of galaxy and galaxy cluster dynamics may be explained by theories of gravity other than dark matter, which are gaining popularity. Not need dark matter in order to elucidate the dynamics of galaxy clusters and galaxies themselves. At low accelerations, which are usually seen at galaxy scales, these altered Newtonian dynamics, MOAND, and theories like TVS propose changes to gravity. Modern structure formation models include intricate baryonic physics, including as feedback from stars and active galactic nuclei, which impact the development and creation of galaxies in addition to gravity. The idea of dark fluid integrates dark energy and dark matter into a single hypothesis that attempts to explain the acceleration of the expansion of the universe as well as the emergence of structure in the cosmos. The neutrino mass, which affects the cosmic expansion rate and structure development, is being included in neutrino cosmology to improve it. To do this, we need fresh theoretical insights and improved methods for measuring the cosmic microwave background, CMB, and large-scale structure. An underappreciated method, causal set theory, represents space-time as an ordered collection of discrete occurrences. It opens us a possible way to interpret space-time on the Planck scale and to reconcile general relativity with quantum physics. These new cosmological ideas and models are constantly being evaluated and improved as observational capabilities increase and more data becomes accessible, expanding our understanding of the universe. This never-ending process guarantees that our cosmological models will always be accurate representations of the universe as it really is. Even though we have learned a lot about the cosmic microwave background, cosmologists still have a lot of concerns and problems that keep them stumped and motivate them to study the subject further. Accurately measuring the polarization of the CMB is one of the main obstacles. Noise and foreground source pollution have made it very difficult to detect the weak B-mode polarization, which might yield evidence of gravitational waves from cosmic inflation. There is ongoing controversy about the precise composition of the cosmic microwave background, CMB, anomalies, including the cold spot and the axis of evil. More data and more advanced analytic methods are needed to determine whether these patterns are statistical flukes or hints of novel physics. There are new difficulties in combining CMB data with other astronomical observations. In order to maintain a coherent cosmological model, it is necessary to overcome discrepancies, such as the controversy around the Hubble constant as measured by supernova and the cosmic distance ladder compared to CMB-based observations. Although dark matter and dark energy's gravitational effects are visible in the cosmic microwave background, CMB, and large-scale structure, what exactly these substances are and how they interact with regular matter and one another is still a mystery. The results of CMB research have far-reaching consequences for gravity theory. For instance, adjusting general relativity to explain observed phenomena without mentioning dark matter or dark energy necessitates a thorough re-evaluation of cosmology's theoretical underpinnings. Another area that lacks complete understanding is the process of reionization and when it occurs. Even while the cosmic microwave background, CMB, gives us a clue as to when the universe was initially reionized, we still don't know much about the specifics of how this process happened or how it affected cosmic development. Neutrino mass and their impact on the early cosmos is a challenging yet delicate part of cosmic microwave background, CMB investigation. Pinning down the exact contribution of neutrinos to the rate of expansion and structure development needs exceedingly accurate measurements. Understanding the physics of the inflationary period requires quantifying the non-Gaussianities in the CMB. The interactions and dynamics of the inflationary field may be better understood with the help of these non-Gaussian characteristics, but their reliable detection requires very high levels of accuracy. A difficult, uncharted territory is the hunt for primordial non-Gaussianity, which may point to early universe interactions that don't fit the simplest inflationary theories. These fingerprints are so weak that they can only be detected by tests of the future generation. Additional difficulties arise when trying to calibrate and understand results from various CMB investigations. To construct a consistent picture of the universe, it is necessary to reconcile the systematic biases and uncertainties that exist in each experiment with those present in other data sets. The statistical uncertainty that comes from looking at the cosmos from just one angle, known as the cosmic variance issue, has to be addressed as well. This makes it harder for cosmologists to get reliable readings of the universe's large-scale features. It is an ongoing struggle to create new technology and instrumentation for CMB study. Difficult task. The cosmic data might be distorted if these instruments do not reach previously unseen degrees of sensitivity and accuracy while reducing the impact of biases and mistakes. Theoretical considerations on particle physics are greatly affected by CMB investigations. The integration of cosmological data with particle physics experiments, such those at particle accelerators, is a formidable multidisciplinary task that calls for a sophisticated grasp of both disciplines. Not to mention the enormous philosophical and educational ramifications of CMB study. Bringing these intricate ideas to light and incorporating them into our larger cosmic perspective calls for strategic outreach and thoughtful communication. Ultimately, cosmology is a field that is constantly evolving and pushing the limits of science and our role in the universe. The study of the cosmic microwave background, CMB, has played a crucial role in transforming our understanding of the cosmos. But there are still many challenges and questions that need answering. As a remnant of the Big Bang, it captures the cosmos 380,000 years after it began, before galaxies and stars were born. The cosmic microwave background, CMB, is crucial to cosmology. This light has been essential in establishing the Big Bang hypothesis, which states that the universe began as a hot and dense state, as it is the earliest light that humans can witness. It also carries information about the early cosmos. Accurate measurements of the cosmic microwave background have allowed cosmologists to deduce important cosmological constants. The age, expansion pace, and matter-energy makeup of the cosmos are all part of these factors. Additional support for the inflationary early universe concept has been offered by the cosmic microwave background, CMB. The cosmos seems flat and uniform in this hypothesis, which postulates a quick expansion just after the Big Bang. The idea is backed up by the CMB's small temperature variations. Particularly noteworthy are these variations, or anisotropies, seen in the CMB. All the structures in the cosmos right now originated from them. Cosmologists may learn how massive objects like galaxies and clusters came to be by charting these minute temperature variations. Investigating the cosmic microwave background, CMB, also crosses over into experimental physics, where gravity and the early cosmos are put to the test. The most enigmatic components of the universe, dark matter and dark energy, are both tested and improved by this discovery. Through studies of the cosmic microwave background, CMB, we now know that dark matter and dark energy make up the vast majority of the universe, whereas conventional stuff, which includes stars and planets, makes up a negligible proportion. The polarization of the cosmic microwave background, CMB, is another important feature as it sheds light on the cosmos during the recombination period, when photons were no longer bound to matter. This polarization provides information on the early universe's environment and the forces that caused it to expand. In addition to confirming the cosmological principle, the idea that, on a vast scale, the cosmos seems the same in all directions, the cosmic microwave background, CMB, has shown the scale of homogeneity of the universe. Recent developments in CMB observational technology have expanded the frontiers of astronomy and cosmology. With the advent of increasingly advanced telescopes and detectors, our knowledge of cosmic processes has grown, and our picture of the early cosmos has become clearer. Inconsistencies and outliers seen in the cosmic microwave background, CMB, including the cold spot and the axis of evil, are pushing the boundaries of accepted cosmological theory and opening up new lines of inquiry into their possible explanations. Also, CMB research has a huge effect on the classroom. Its impact on physics and astronomy courses and the general public's curiosity in the cosmos' beginnings and ultimate destiny have made it an essential piece of contemporary cosmology. In an effort to unravel the secrets of the universe, researchers from all around the world have joined forces thanks to CMB studies, which have encouraged worldwide partnerships. For the purposes of resource pooling, data sharing, and technology development, these alliances have proven vital. Constantly probing the cosmic microwave background, CMB, sheds light on the cosmos while simultaneously testing long-held assumptions about its building blocks and driving forces. It is proof that people are inherently inquisitive and eager to learn. To summarize, the cosmic microwave background is an essential component of cosmology, since it provides evidence for the structure, composition, and development of the universe, as well as a window into its early history. The more we learn about the cosmic microwave background, CMB, the more mysteries it will reveal about the cosmos and how we fit into it. As we wrap up our investigation of the cosmic microwave background, CMB, and its significant influence on our knowledge of the cosmos, it becomes evident that this area of research stands at one of the most exciting junctions of theory and observation in contemporary science. Our incredible progress in comprehending the universe is reflected in the trip through cosmology, which begins with theoretical predictions from the early 20th century and continues with startling discoveries and comprehensive maps of the cosmic microwave background, CMB. The insatiable need for information and the inquisitive nature of humans are shown here. The study of the universe's big-picture structure and beginnings is only one subfield of cosmology. Part of it is realizing where we stand in the universe. The cosmic microwave background, CMB, provides information about the early cosmos and the universal rules governing matter and energy. Although it has pushed the limits of astronomy, mathematics, and physics, studying the CMB has produced more puzzles than solutions. In their own ways, anomalies and irregularities force us to reevaluate our assumptions and open our minds to new avenues of inquiry and potential outcomes. There is a treasure trove of information just waiting to be found for individuals who are fascinated by these secrets. No matter whether you are a student thinking about a future in science, a teacher seeking resources to motivate your students, or just someone with an insatiable curiosity for the cosmos, cosmology offers limitless potential. As for individuals who want to learn more about the universe, there are plenty of resources for them, accessible to those who want a more profound exploration of the universe. Resources for education such as public lectures, open-access research papers, movies, and textbooks are more widely available than ever before. Getting involved in astronomy clubs and community science initiatives is another great way to get your hands dirty with stargazing and make a meaningful difference in scientific research. By participating in these events, one may get a more tangible comprehension of the cosmos and connect with others who share their passion. Even more mysteries about the universe may be solved in the future thanks to new technology and space missions. Keeping up with these changes may be quite beneficial, since it gives you a front-row seat to the newest discoveries as they happen. A huge difference may be made by fostering a love of science and encouraging young people to learn about the cosmos. For the sake of continuing the quest to understand the cosmos, it is essential for training the scientists of tomorrow. Cosmology and the cosmic microwave background, CMB, spark more than simply academic debates and discussions. Cosmology and the cosmic microwave background spark discussions and arguments outside of the academy. They make passing reference to metaphysical concerns like the beginnings of the cosmos, the purpose of life, and the nature of reality itself. In light of what we still don't know about the cosmos, the door to developing better theories and models to fill in the gaps is wide open. Cosmology serves as a constant reminder that our understanding of the universe and its workings is dynamic and ever-changing. The narrative of the cosmic microwave background and the cosmos as a whole is captivating, and viewers are urged to remain interested, keep learning, and ask plenty of questions. Our knowledge of the cosmos and our role in it is constantly expanding thanks to new observations and theoretical advancements. The study of the cosmos and our role in it is known as cosmology. As a field that spans both time and space, cosmology research unites people of all backgrounds and cultures. This is a trip that blends scientific precision with existential and philosophical questions about who we are and where we fit in the universe. Last but not least, cosmology provides a fresh viewpoint on the cosmos for all astronomers, from amateurs to professional. It challenges us to think beyond our current capabilities and encourages us to gaze upwards into space. We appreciate you coming along on this amazing cosmic adventure with us. As our knowledge of the cosmos grows, we want you to join us on this thrilling journey by sharing your thoughts, asking questions, and making discoveries of your own.